to some eras leave behind towering cities and carved stories. Others leave almost nothing at all, just ice, wind, and bones buried in frozen ground. The Ice Age wasn't one single moment, but a series of long, brutal cold spells that came and went, shaping the planet each time. It didn't leave behind palaces or libraries. Instead, it gave us clues hidden in glaciers, scattered fossils, and ancient stone tools dropped in the middle of nowhere. For a long time, people thought of it as a distant, frozen past that didn't matter much anymore. But the more we've uncovered, the more it's changed how we see human history, climate, and the world itself. The Ice Age didn't just test the survival of animals and early people. It shaped where they could go, what they could eat, and how they adapted. And when it ended, it didn't slip away quietly. It forced everything to change, fast. Forests grew over icy plains. Rivers moved. Species vanished. The Ice Age never really disappeared. It left marks everywhere. We just had to know where to look. The term Ice Age refers to periods in Earth's history when large parts of the planet were covered in ice sheets and glaciers. Scientists tend to use this phrase to describe long spans of time when the global climate was cold enough to allow these thick ice sheets to form and persist, often blanketing entire continents. Although the phrase might sound like a single specific event, it actually encompasses multiple episodes of significant cooling separated by warmer interludes. Over the course of Earth's history, there have been several ice ages, some so ancient that their traces are only evident through the most detailed geological records. When people refer to the Ice Age in casual conversation, they usually mean the most recent one that peaked roughly 20,000 years ago, a period scientifically known as the last glacial maximum. During that time, huge portions of the Northern Hemisphere, including much of North America, Northern Europe, and parts of Asia, lay under immense sheets of ice that could exceed 2 or 3 kilometers in thickness. This made for a very different world than the one seen today. The reasons behind these cold periods lie in a mix of various factors, which include changes in Earth's orbit around the Sun, shifting continental configurations, and changes in greenhouse gas concentrations. When temperatures drop enough and snowfall outpaces snowmelt over tens of thousands of years, glaciers expand, eventually merging into massive sheets. These ice sheets grow outward from regions where the climate is consistently cold enough that yearly snowfall never melts completely. As time goes on, layers of accumulated snow compress into dense glacial ice, inching forward under their own weight. It might seem impossible that sheets of ice could stretch as far as the eye can see, but the geological and fossil evidence scattered across multiple continents leaves little doubt that the Earth has been through these cycles multiple times. At their most extensive, these ice sheets reshaped landscapes in powerful ways. They scoured bedrock, carved out valleys, and left behind distinctive landforms like moraines, drumlins, and eskers. Evidence for the Ice Age also turns up in features such as polished rock surfaces and scratched stones called glacial striations, which point to the direction of ice flow. Even beneath modern seas, scientists find clues in sediment cores that preserve ancient pollen grains, microscopic organisms, and other indicators of past climate conditions. Through these tiny pieces of evidence, researchers reconstruct the story of how widespread the cold was, how organisms adapted, and how the world at large managed to persist even under such harsh conditions. When discussing the question, what was the Ice Age? It helps to know that an ice age, in a broad sense, is any extended interval of time when there are permanent ice sheets somewhere on Earth. By that definition, some experts say the planet is still technically in an ice age today, because large ice sheets exist in Antarctica and Greenland. However, these modern sheets are nowhere near the scope of what existed during the most recent major glaciations of the Pleistocene epoch. The Pleistocene, which began about 2.6 million years ago and ended roughly 11,700 years ago, contained numerous cold cycles called glacials and comparatively warmer intervals called interglacials. The repeated expansion and contraction of the glaciers across that period shaped the evolution and migration patterns of many species, including human ancestors, and left an indelible mark on the surface of the Earth. The concept of an ice age also becomes clearer when considering the enormous influence it had on sea levels. So much water was locked up in these glacial masses that sea levels around the world fell by well over 100 meters in some cases. This drop revealed vast stretches of land that are currently underwater, such as the Bering Land Bridge between Siberia and Alaska. That land connection allowed groups of animals and humans to cross from Asia into North America, which had profound effects on the distribution of life across continents. Once the world warmed again, glaciers melted and sea levels rose, submerging those land bridges and reshaping coastlines in ways that continue to affect humanity's distribution and cultural development. The impacts of the Ice Age stretched far beyond the placement of glaciers. Many regions that were not directly covered by ice still experienced dramatic changes to their climate, leading to shifts in ecosystems and forcing various species to adapt or perish. Forests might transform into grasslands, and grasslands could morph into deserts, depending on regional precipitation and temperature changes. Plant life, animal life, and even early human societies had to stay on the move to survive. Some populations of humans found refuge in milder zones where resources were accessible enough to wait out the cold, while others decided to follow the migrating herds of game animals to new territories. Over generations, these shifts shaped cultures, technologies, and social structures. Understanding the science behind these freezing epochs has come a long way since the 1800s, when early geologists noticed strange rock deposits and boulders in places where no known geological process at the time could have left them. The so-called erratic boulders baffled researchers until the glacial theory was proposed, suggesting that massive ice sheets had transported them across great distances. Initially, the idea of an ice age seemed almost unbelievable. Today, it's widely accepted, and the evidence for multiple glaciations is hard to miss. Scientists now sift through ice cores from Greenland and Antarctica, drilling deep below the surface to uncover trapped air bubbles that provide snapshots of the atmosphere's composition from tens or even hundreds of thousands of years ago. By analyzing these air bubbles and other data, researchers can chart fluctuations in greenhouse gases like carbon dioxide and methane, and see how closely they correlate with temperature changes. The knowledge gained from these studies also underscores how dynamic Earth's climate can be. It isn't a static system. It has a rhythm influenced by subtle shifts in the planet's orbit, known collectively as Milankovitch cycles, as well as by tectonic movements and volcanic events. If continents move into positions that redirect ocean currents and trap heat differently, or if a spike in volcanic eruptions pumps enough dust and ash into the atmosphere, global temperatures can drop noticeably. Over the extended timeline of the planet, these variations can accumulate into significant cooling phases or warming phases. The Ice Age is an overarching term that captures these massive cooling phases, but it's important to remember that conditions weren't uniformly cold everywhere. Some areas remained surprisingly temperate, or at least milder than one might expect in an ice age, becoming refugees for diverse forms of life. The presence of ice at lower latitudes also forced dramatic changes to landscapes. In places like North America and Northern Europe, once glaciated terrain bore signs of glacial erosion. Rivers that once ran in different paths were rerouted by the ice, and the weight of the ice sheets pressed the land downward. Even today, parts of Canada and Scandinavia are rebounding in elevation because they're no longer weighed down by billions of tons of ice. This phenomenon, known as isostatic rebound, demonstrates just how heavy and extensive the ice was. Another astonishing impact is visible in the Great Lakes region of North America, where massive glacial movements carved out basins that later filled with water. The same can be said for the fjords of Norway or the glacial valleys in mountainous regions around the world, which are direct results of those long-ago ice movements. What the phrase Ice Age captures at its heart is the story of a planet in flux. Earth wasn't always locked in cold. There were warm interglacial periods, such as the Eemian, which saw sea levels higher than what is observed today, and widespread forests in many areas that are now cooler. The planet swung between colder and warmer phases, providing repeated challenges for the organisms that called it home. Mammoths, saber-toothed cats, giant ground sloths, and other megafauna flourished in some of these colder spells, only to face extinction when climates shifted. Early human species also witnessed these swings and found themselves innovating to cope with dramatic environmental changes. Research into the Ice Age is an ongoing effort. Paleoclimatologists, geologists, archaeologists, and other specialists continue to collaborate, pooling discoveries from different corners of the world. Fossil records, ancient DNA, sediment layers, and advanced modeling techniques all combine to offer an increasingly detailed picture. Despite these breakthroughs, there's still plenty that remains uncertain about specific events or timelines. Debates continue about what exactly caused certain surges in glaciation or sudden warm spells, and these discussions shape our understanding of the Earth's capacity for rapid climate change. This knowledge also offers insight into current climate patterns, reminding people that while the planet has seen fluctuations in the past, the rate and causes of today's warming are distinct and linked to human activity in ways that differ from natural cycles. It's also worth recognizing that the Ice Age was not a single uniform event. Within the Pleistocene, there were multiple glacial periods, each with its own characteristics and timelines, punctuated by interglacials when the ice retreated, temperatures rose, and ecosystems rebounded. Some glacial periods lasted tens of thousands of years, building enormous ice domes and drastically lowering sea levels. Then interglacials, which could last for shorter spans or occasionally tens of thousands of years, allowed forests, grasslands, and animals to reclaim territory. Each shift paved the way for new species to thrive or old species to adapt in surprising ways. Evolution is a powerful force, and in the continuous dance between cold and warm climates, it shaped everything from the types of plants that could survive in certain regions to the morphological traits that helped animals endure severe conditions. Looking back, it's fascinating to realize that the Ice Age landscape would have seemed alien to modern eyes. Mammoths roamed regions that now host dense cities and farmland. Lions, hyenas, and rhinoceroses lived on what is now European soil. At certain points, the Sahara Desert was far less harsh because of global climatic shifts associated with these colder periods. Further north, a thick shield of ice covered most of Canada, leaving only some parts of Alaska's interior free of glaciers because they were too dry for the ice sheets to form extensively there. The distribution of land, water, plants, and animals was so different that it challenges any assumptions about permanence in nature. The question, what was the Ice Age, prompts a reflection on how interconnected the systems of our planet truly are. Ice sheets influenced wind patterns, ocean currents, and precipitation. These changes, in turn, dictated the habitats available to wildlife and shaped migration routes for humans. The difference between a region being hospitable or inhospitable often came down to a few degrees in temperature. Over thousands of years, these seemingly small temperature changes accumulated into huge shifts in global climate, proving that Earth's environment can toggle dramatically given enough time and triggers. Many people might imagine a bleak, frozen world that offered little hope for life during these times, but the reality was more complex. Even at the glacial maxima, life found ways to persist. Tundra areas, steppe environments, and other ecosystems spread around the edges of the ice sheets. These environments supported large herbivores like mammoths and bison, along with the predators that hunted them, such as saber-toothed cats and dire wolves. Human communities, resourceful and adaptable, learned to exploit these animals for food, clothing, and materials for shelter. They also utilized plants and other resources wherever they could find them. Over time, some groups developed sophisticated tools and cultural expressions, from the carving of figurines to the painting of images on cave walls. This period laid the groundwork for the spread of Homo sapiens and had lasting impacts on genetic lineages, cultural innovations, and human society. Studies about Ice Age megafauna often highlight the massive extinctions that occurred as the planet emerged from its last big freeze. Large animals like woolly mammoths, mastodons, giant ground sloths, and saber-toothed cats disappeared over a relatively short window. Scientists debate how much of this was driven by the changing climate versus the impact of human hunters. These discussions reflect the broader narrative that the Ice Age wasn't simply about ice, it was about how life, climate, geology, and even astronomical cycles all come together to form the tapestry of Earth's history. This complexity is why the question, what was the Ice Age, remains so intriguing. It's not a single story, but a series of chapters that collectively shaped the modern world. From a purely geological standpoint, the Ice Age rearranged the surface of the planet. Rivers cut new pathways once the glaciers retreated. Coastal regions shifted as sea levels rose and fell. Mountain ranges experienced erosion on a grand scale, creating some of the most dramatic landscapes seen today. This era also left behind thick deposits of loess, which is fine-grained sediment carried by the wind and derived from glacial grinding. These nutrient-rich soils now support intensive agriculture in many regions. In that sense, the Ice Age had a profound effect on the resources that modern societies rely upon. Without the glaciers that ground up rocks and spread mineral-rich dust far and wide, certain farmland might not be as productive as it is now. Further reflection on the Ice Age reveals how it wasn't just about cold, it was about the balance between precipitation and temperature. An area needs consistent snowfall that doesn't melt entirely in summer for ice sheets to grow. Desert regions, even in high latitudes, can remain relatively ice-free because they don't receive enough snowfall to accumulate ice. This explains phenomena like Alaska's interior or Central Asia, where high peaks might be glaciated, but the basins or plains remain largely free of ice if the climate is too dry. Understanding these patterns helps clarify why certain zones became epicenters for large ice formations, while others stayed more open to human settlement and animal life. Finally, the significance of the Ice Age can't be overstated when it comes to humanity. Modern Homo sapiens evolved during the Pleistocene, navigating the challenges of shifting climates and competing species like Neanderthals and Denisovans. The harsh conditions likely spurred technological and cultural innovations, from more advanced hunting tools to the control of fire, tailored clothing, and even early forms of social cooperation and symbolic expression. The legacy of the Ice Age lives in every aspect of civilization today. People still find their ancestors' footprints and artifacts in what used to be Ice Age landscapes, revealing how resourceful humans could be. Although it's common to look back on those periods as entirely inhospitable, the evidence of surviving communities, along with the sophistication of their stone tools and artwork, underscores that life thrived in ways modern observers might find surprising. Ice ages begin and end due to a series of natural processes that change the amount of solar energy reaching Earth's surface, as well as processes that affect how that energy is retained or reflected back into space. Although no single factor operates in isolation, one of the most prominent theories about why these massive cooling and warming cycles occur involves changes in Earth's orbit around the Sun, collectively known as Milankovitch cycles. These cycles are named after Milutin Milankovitch, who proposed in the early 20th century that variations in Earth's tilt, the shape of its orbit, and the wobble of its axis, precession, influence the distribution of sunlight across the planet's surface. Even small shifts in these parameters can lead to big changes over many thousands of years. They alter how much solar radiation reaches higher latitudes during the summer, which affects whether snow and ice from the previous winter can fully melt. When summers in the northern latitudes become slightly cooler because of a change in Earth's tilt or orbital shape, more snow persists year after year. Over decades and centuries, that snow compacts into ice. As the ice thickens, it reflects more sunlight back into space because ice has a high albedo, meaning it's very reflective. That causes temperatures to drop further, allowing ice to expand even more. This feedback loop can lead to the growth of massive glaciers and ice sheets. While this is happening, lower sea levels and shifts in ocean currents can redistribute heat around the planet, intensifying the process. It's a gradual build-up that takes thousands of years, but eventually, large expanses of the Earth end up under thick layers of ice, which characterizes the glacial periods of an ice age. However, these glacial expansions don't last forever. Just as certain orbital alignments favor cooler summers in the north, other alignments can result in slightly warmer summers. When summer warmth is enough to melt most of the accumulated snow, the balance tips in the other direction. Ice sheets begin to shrink, exposing darker land or ocean surfaces that absorb more solar energy rather than reflecting it. That absorption accelerates the warming process in a reverse feedback loop. The retreating glaciers also release water back into the oceans, causing sea levels to rise. Over time, this warming phase transitions the planet from a glacial period to an interglacial period. Earth has swung between these two extremes multiple times over the last few million years. Orbital cycles aren't the only factors that cause ice ages to begin or end. Tectonic activity can gradually shift the configuration of the continents, altering ocean currents and wind patterns. When continents are arranged in a way that blocks or channels major ocean currents toward the poles, conditions for ice sheet formation can become more favorable. For instance, the formation of the Isthmus of Panama millions of years ago redirected ocean currents, influencing global climate patterns and arguably setting the stage for future glaciations. Similarly, the ongoing northward drift of continents like Antarctica into polar regions contributed to the formation of permanent ice caps, tipping Earth into a more ice-friendly state. Volcanic activity also plays a role, though usually on shorter timescales. Large eruptions can spew ash and sulfur compounds high into the atmosphere, reflecting sunlight and causing temporary cooling. If a series of significant eruptions takes place over centuries, they might help tip the balance toward glaciation. Alternatively, volcanic activity can also release greenhouse gases like carbon dioxide, contributing to warming. The net effect over long periods depends on the balance between these cooling aerosols and warming greenhouse gases. Greenhouse gas concentrations play another crucial part. Carbon dioxide, methane, and other gases trap heat in the atmosphere. Over geological timescales, levels of these gases can fluctuate due to processes like changes in ocean chemistry, plant growth, rock weathering, and volcanic emissions. When greenhouse gas concentrations drop, less heat is retained, aiding the onset of glaciation. Conversely, when greenhouse gas levels rise, they trap more heat and help melt existing ice. The ice core records from Antarctica and Greenland show a close correlation between greenhouse gas concentrations and temperature over the past 800,000 years or so. During glacial periods, carbon dioxide and methane levels tend to be lower, while in interglacial periods, they are higher. Another factor relates to feedback mechanisms involving ice and snow. Once ice starts to accumulate, its reflective surface creates a self-reinforcing cycle of cooling. Meanwhile, when ice melts, newly exposed ground or ocean absorbs more heat, further accelerating the melting. These feedbacks can be powerful, sometimes making climate shifts happen more abruptly than a simple linear progression would suggest. Evidence from geological records indicates that while the buildup of ice sheets might take tens of thousands of years, deglaciation can occur relatively quickly when critical thresholds are crossed. It's worth mentioning that ice ages and their glacial periods are not uniform or unbroken episodes of extreme cold. They consist of a series of advances and retreats. Scientists studying past climates use the term glaciation for the times when ice sheets are at their greatest extent and interglacial for the warmer spans in between. Within these broader categories, there can be brief but significant warmer or colder spells. For instance, during the last deglaciation, there was a sudden return to near-glacial conditions for about 1,200 years, known as the Younger Dryas, before the climate warmed again. This brief cold snap highlights the complexity of Earth's climate system and how multiple forces can interact to produce unexpected temperature shifts. Understanding how ice ages begin and end is not just an academic exercise. It provides valuable perspective on the processes that drive Earth's climate over long periods. This context can help people appreciate the difference between the natural cycles that cause glacial and interglacial phases and the much faster rate of change that is currently being observed in the modern era. Natural cycles unfold on timescales of tens of thousands of years, whereas the increase in greenhouse gases in recent centuries has been rapid compared to these geological rhythms. Learning about ice ages also illustrates the planet's sensitivity to seemingly small triggers. Slight variations in orbital parameters or atmospheric composition, when sustained over many centuries, can accumulate into immense transformations. Glacial expansions mark times when life's distribution shifts drastically. Species that can handle cold climates extend their ranges, while species dependent on warmer conditions retreat or adapt in refuges. When ice begins to retreat, new land opens for colonization. Vegetation returns first, followed by herbivores that feed on it, and then carnivores. Humans have frequently been part of these waves of recolonization, using new pathways created by changes in sea level or newly unveiled landscapes. The cyclical nature of these expansions and contractions plays a critical role in speciation, extinction, and the overall evolution of life on Earth. Some theories also connect these climatic swings with pulses of human innovation, as groups had to develop new strategies, technologies, or social systems to cope with changing environments. Shifts in ocean currents during ice ages further illustrate how interconnected the planet's systems are. For example, changes in the thermohaline circulation, often referred to as the global conveyor belt, can redistribute heat around the globe. If fresh water from melting ice disrupts the salinity balance in the North Atlantic, this can weaken or alter the Gulf Stream, leading to cooling in some areas and warming in others. Such feedback loops can reinforce or counteract the conditions that started the glacial expansion in the first place, creating regional discrepancies in how the ice age is experienced. Even if the global average temperature drops, there may be pockets that remain relatively warm or become surprisingly cold, depending on oceanic and atmospheric circulation patterns. The end of an ice age isn't simply about melting ice, it's about transforming entire environments. As glaciers retreat, the water that was previously locked in them raises sea levels, flooding coastal regions. That can drown river valleys, creating features like fjords and estuaries, which become new habitats for marine life. Glacial melt can also form proglacial lakes, which may temporarily exist before they breach natural ice or sediment dams, releasing catastrophic floods that reshape landscapes downstream. These dramatic events leave behind traces in the geological record, often puzzling researchers for decades until they piece together the puzzle of how such floods could have occurred. Near the tail end of an ice age, warmer conditions encourage vegetation growth across areas that were once barren. Over centuries, forests might reclaim vast tracts of land, bringing a surge of biodiversity. Animals follow, including humans who take advantage of the newly available resources. Cultures develop around fishing in newly flooded coastal areas or hunting animals that graze on fresh grasslands. Human settlements often flourish in these transitional environments as there is a wealth of resources available. Over the course of thousands of years, what was once a harsh, glaciated zone evolves into a thriving region teeming with plants, animals, and the seeds of complex human societies. Each ice age has its own characteristics, shaped by the interplay of orbital changes, tectonics, greenhouse gas levels, and feedback loops. Some may be more intense than others. The planet has even experienced periods referred to as snowball Earth events, far back in the Proterozoic eon, when it's hypothesized that ice reached nearly to the equator. The climate system has tipping points. Changes in orbital parameters, greenhouse gas concentrations, or ocean currents can set off chain reactions. Before passing a threshold, conditions might be relatively stable for thousands of years, but once crossed, the system moves rapidly toward the new state, whether that's a glaciation or a deglaciation. Ice and snow reflect solar radiation, while open ocean and land absorb it, and this interplay can dramatically accelerate shifts in climate states. These transitions remind observers that Earth's climate can respond swiftly when certain triggers are activated. Scientists continue to refine their models of ice age cycles, using more detailed proxies and more sophisticated computing power to simulate past climates. Every new drill core from Antarctica or the Arctic, every new sediment core from the ocean floor, and every new fossil discovery adds a piece to the puzzle. The story becomes richer, but so does the recognition that Earth's climate might be even more complex than previously thought. Although the general outlines of how glaciations start and end are reasonably well understood, the specifics can be incredibly intricate. How does volcanic activity modulate greenhouse gases over these timescales? How do changing ocean currents interact with orbital cycles? The answers to these questions deepen the understanding of the entire Earth system. During the Ice Age, the planet looked quite different from what it does now. Vast ice sheets covered huge swaths of the northern hemisphere, reaching down into much of North America and northern Europe. In North America, a single gigantic ice mass called the Laurentide ice sheet extended over present-day Canada and parts of the northern United States. Across the Atlantic, the Scandinavian ice sheet stretched over northern Europe, while other smaller ice sheets and alpine glaciers capped mountain ranges. The thickness of this ice could be measured in kilometers, weighing so heavily on the land that the surface actually sank under the colossal mass. This depressed crust is still rebounding in modern times, a geological phenomenon evident in places like Scandinavia and Canada, where the ground gradually lifts each century. Farther south, conditions were not always as frozen, but still colder and drier than today. Tundra landscapes covered large regions, supporting hardy plants adapted to short, cool summers. Grassy steppes spread across Europe and Asia, providing habitat for animals such as woolly mammoths, rhinoceroses, and herds of bison. These open expanses stretched for miles, occasionally broken by rivers or stands of stunted trees. The cooler climate even reached into areas that are now temperate, causing shifts in vegetation zones. Forests that exist today in many parts of Europe and North America were smaller or replaced by more cold-tolerant species. At the same time, deserts in lower latitudes might have been less harsh, benefiting from different wind and weather patterns associated with the cooler global temperatures. Sea levels dropped significantly because so much water was locked in ice. Coastal areas extended far beyond their modern shorelines, revealing land bridges that connected what are now separate continents and islands. One of the most famous examples was the Bering Land Bridge between Asia and North America. This open corridor allowed animals, and eventually humans, to migrate across what is now the Bering Strait. In northern Australia, lower sea levels connected that continent more closely to New Guinea, allowing ancient migration routes that influenced the distribution of flora and fauna in the region. The world's oceans also looked different. With sea levels so much lower, many shallow continental shelves were exposed, creating new coastal plains that supported animal and plant life. Coral reefs adjusted to the changing sea levels, some dying off when the water receded too far, while others adapted to cooler waters. Glacial landscapes dominated the higher latitudes. From a distance, these regions would appear as vast white expanses, with the ice reflecting sunlight so intensely that it could blind an unprotected eye. Near the edge of the ice sheets, there was a transitional zone where melting during the summer carved out rivers and lakes. Moraines, ridges of debris pushed up by the movement of the ice, formed at the edges. Beyond them lay outwash plains, composed of sand and gravel carried by meltwater. In mountainous areas across the globe, glaciers extended into valleys, carving out U-shaped profiles that remain today as some of the planet's most dramatic scenery. This heavy, ice-sculpted jagged peaks, cirques, and sharp ridges, forming landscapes that many travelers now associate with alpine vistas. Animal life thrived in the steppe tundra environment. This biome, often called the Mammoth Steppe, stretched across Europe, Asia, and parts of North America. It was characterized by cold, dry conditions, but it still supported a surprising diversity of megafauna. Woolly mammoths, with their thick coats and curved tusks, are the iconic symbols of that era, but they shared the land with woolly rhinoceroses, musk oxen, reindeer, bison, and giant deer with enormous antlers. Predators like saber-toothed cats, cave lions, and dire wolves roamed these habitats in pursuit of herbivores. The Pleistocene was a time of giants, partly because the harsh conditions favored large bodies that could retain heat more effectively and travel long distances in search of food. In regions without permanent ice cover, humans also carved out a living. Groups of Homo sapiens, along with other human relatives in earlier times, tracked herds of game across the open landscapes. Shelters ranged from caves and rock shelters to simple huts constructed from bones, stones, and animal hides. Campfires provided warmth and a place to cook. Stone tools became increasingly sophisticated, reflecting the need for efficient hunting and butchering. Cave paintings and portable art found in parts of Europe serve as lasting records of how people viewed the animals and the environment around them. These images show mammoths, horses, and other creatures that once roamed what might have felt like an endless steppe. The vantage point of those ancient peoples would have been one of both challenge and opportunity. Abundant game in some seasons, but intense cold in others, demanding resourcefulness and adaptability to survive. In Africa, conditions were somewhat different during the Ice Age. Although the continent didn't host massive ice sheets outside of some high mountains like Kilimanjaro and the Rwenzori Range, changing temperatures and precipitation patterns led to expansions or contractions of deserts and grasslands. Some areas became drier, pushing wildlife and human populations into regions where water was more reliable. Elsewhere, lakes that are now much smaller swelled to large sizes. These fluctuations affected the migration routes of animals like elephants, antelopes, and zebras, as well as the predators that relied on them. Early human cultures adapted to these variations by developing new strategies for hunting, gathering, and using resources. In Asia, the ice coverage was extensive in the north, especially in Siberia, where permafrost locked the ground in a permanent state of freeze. Mammoths, woolly rhinoceroses, and other cold-adapted beasts roamed the Siberian plains. Farther south, the land bridge connecting Siberia to Alaska was open when sea levels were lower. Some researchers believe that this allowed a steady trickle of humans and animals into the Americas. Glacial ice also capped mountains in Central Asia, influencing river systems like those feeding into the Tarim Basin or the Indus River. The powerful effect of ice and meltwater shaped not just the land, but the very pathways that humans and animals could use to move from place to place. South America during the Ice Age had its own glacial regions in the Andes, where ice caps and glaciers expanded and then retreated. Large animals like giant ground sloths and saber-toothed cats roamed farther south into areas that are now part of Argentina and Chile. The drastic changes in elevation across the Andes created microclimates that varied from glacier-covered peaks to warmer lowland areas. This allowed a wide range of environments to coexist, each hosting different plant and animal communities. Over time, humans reached South America and adapted to these varied landscapes. The absence of a vast northern ice sheet meant that the continent had different climatic pressures, but it still felt the global influence of cooler temperatures and shifting weather patterns. Australia was somewhat of an isolated case. Even though it was never invaded by continental-scale ice sheets, glacial conditions affected rainfall patterns and temperatures, resulting in expansions of deserts and more arid conditions in many regions. Animals such as giant marsupials roamed parts of the continent, including the famous Diprotodon, which resembled an enormous wombat. Human populations had arrived tens of thousands of years earlier and settled across the continent, adapting to its diverse environments. When sea levels dropped, Australia was connected to New Guinea, creating a larger landmass called Sahul. This allowed species and people to move more freely between these regions. As global temperatures rose and sea levels rose with them, Sahul broke apart again, leaving Australia and New Guinea as separate entities. Many iconic geographic landmarks in the modern world are actually remnants of Ice Age processes. Regions covered by thick ice often have lakes formed from depressions carved by glaciers, known as kettle lakes or basins. The Great Lakes in North America, for instance, owe their size and shape to glacial excavation. In Europe, glacial valleys eventually flooded with seawater as ice melted and sea levels rose, forming fjords in places like Norway. Even today, the landscapes in those high latitudes carry the signature of that ancient carving, displaying U-shaped valleys, sharp ridges, and cirques that speak of long-vanished glaciers. For people living in the warm tropics during the Ice Age, the climate would have been cooler, but not necessarily as severe as in polar or temperate regions. Tropical forests in places like the Amazon basin or parts of Southeast Asia likely contracted somewhat, giving way to more savanna-like conditions in some areas. That shift would have influenced the distribution of species, isolating some in forest refuges while creating corridors of open habitat for others. These transitions paved the way for the dynamic biodiversity patterns observed today, including the idea that pockets of rainforest expansions and contractions spurred speciation. Overall, the world during the Ice Age was marked by stark contrasts. The poles and higher latitudes were locked in ice, turning much of the northern hemisphere into a realm of glaciers and tundra, while some equatorial regions, although cooler and drier, remained more habitable. Entire ecosystems stretched across continents, populated by megafauna well suited to cold environments. Humans spread across new frontiers, guided by shifting coastlines and land bridges. Rivers formed from melting ice carved out paths through the landscape, depositing fertile silt and sculpting valleys. Some of these river systems would become cradles of human civilization long after the ice retreated. The rhythmic glaciation and deglaciation over tens of thousands of years caused an ever-changing tapestry of habitats, constantly testing the resilience of life on Earth. In capturing what the world looked like during the Ice Age, it's essential to imagine a planet in the midst of colossal transitions. Over millennia, continents wore thick ice blankets that advanced and retreated in a cyclical dance. Creatures large and small adapted to a patchwork of environments ranging from forbidding permafrost to relatively temperate refuges. Humans learned to cope with frigid conditions, forging new survival strategies and pushing the boundaries of their known world. Every corner of the globe felt the influence of these cold pulses, whether through direct glaciation or indirect climate shifts. It was a time when the Earth's surface was literally being reshaped, leaving features that are still recognizable today, a testament to the planet's deep and dynamic history. Ice Age animals existed in a world that was both harsh and dynamic. During these times, enormous sheets of ice advanced and retreated, climates shifted rapidly, and habitats changed in ways that encouraged the evolution of fascinating creatures. Mammoths, saber-toothed cats, and a range of other large mammals roamed continents, that looked quite different from modern landscapes. There is a sense of awe that accompanies every mention of these gigantic beasts, partly because they seem so alien and yet so closely tied to life on Earth today. Some resembled oversized versions of creatures that are still around, while others had specialized features that are unlike anything found in modern wildlife. Scientists continue to unravel their secrets through fossils, preserved remains in frozen tundra, and the many remnants left behind in ancient tar pits. These animals thrived during an era when survival required constant adaptation to challenges such as frigid temperatures, shifting food supplies, and evolving predators. Mammoths, in particular, are often thought of as iconic ambassadors of the Ice Age. Their closest living relatives are elephants, but mammoths had unique characteristics that helped them cope with cold environments. Many people picture the woolly mammoth, a creature covered in thick fur with huge curved tusks. There were also other mammoth species, such as the Columbian mammoth, which inhabited more southerly regions of North America. In extremely frigid regions, mammoths had layers of insulating fat beneath their skin and a coat of hair that protected them from the piercing winds of glacial plains. Their tusks, which could curve dramatically, proved useful for foraging under snow, defending themselves, and performing social displays. Evidence suggests that mammoths lived in herds, looking after their young much like modern elephants do. These tight-knit groups likely offered a crucial measure of protection in a world filled with formidable predators. Saber-toothed cats, such as Smilodon, captured the public imagination with their elongated canine teeth that extend far beyond the jaw. The name saber-toothed tiger is often used in casual speech, but these creatures were not closely related to modern tigers. Instead, they belonged to a separate branch of felines that developed specialized hunting techniques. Their oversized canines were once believed to be used primarily for stabbing and slashing. However, more recent research suggests that the canines may have been used in a more precise way, perhaps to deliver lethal bites to soft areas like the throat of large prey. These cats needed to tackle creatures with robust muscles and thick hides, so a specialized killing method would have been advantageous. Fossil evidence points to strong forelimbs that may have helped them wrestle and pin down their prey. Like modern big cats, they would have roamed territories and competed with other large carnivores. The abundant remains of saber-toothed cats in places such as the La Brea tar pits in present-day Los Angeles suggest that these predators were quite successful for thousands of years. A range of other hefty mammals prowled the Ice Age landscape. There were giant ground sloths that could stand on their hind legs to reach vegetation, glyptodons that resembled massive armored armadillos, and short-faced bears that were taller than any bear species alive today. The giant ground sloths, like Megatherium, could grow to be longer than many modern cars from nose to tail. Their claws were strong and curved, and likely used for ripping branches from trees or for defense if threatened. Despite their size, these creatures were herbivores that feasted on a variety of plants. They moved relatively slowly, though that did not seem to hamper their survival for quite a long time. Glyptodons were another marvel. Their bodies were protected by an armored shell that resembled a turtle's carapace, but on a much larger scale. They were roughly the size of small cars, and their heavy armor made them less agile than many of their predators. Yet this defense was extremely effective. Early humans who came into contact with glyptodons may have attempted to hunt them for meat, or even used their shells as makeshift shelters. Fossils have been discovered with fractures or signs of blunt force trauma, indicating that these animals sometimes had violent encounters, possibly with predators or human hunters. Short-faced bears were among the largest carnivorous mammals on land. They had longer legs compared to modern bears, which might have allowed them to be surprisingly fast over open terrain. Their limbs suggest that they were more cursorial, meaning they could pursue prey across wide expanses. Studies of their skulls and teeth have led some researchers to think that they scavenged carcasses often, using their size to intimidate smaller predators. Others believe that they were active hunters, able to run down ungulates and other large animals. Their diet likely fluctuated depending on what was available, much like modern bears that vary their menu by location and season. Dire wolves lived in the Americas and shared territories with modern grey wolves, though the two were distinct species. Dire wolves were heavier and had a more robust skull, which might have given them a stronger bite force. They are frequently depicted as pack animals that hunted large prey, such as bison and horse. Much like saber-toothed cats, dire wolves appear in abundance at the La Brea tar pits, indicating that these tar pits were traps for predators and prey alike. Animals lured in by the promise of water or food would get stuck in the tar, eventually drawing in more predators that also got trapped. This process left behind a treasure trove of fossils that continue to inform researchers about the ecosystems of the late Pleistocene. Another notable member of the Ice Age fauna was the mastodon. At first glance, mastodons appeared quite similar to mammoths, but they actually belonged to a separate group and had distinct teeth adapted for chewing leaves and twigs. Mammoths often grazed on grasses, while mastodons browsed in more forested regions. Their bones are sometimes found in association with human-made artifacts, indicating that they were hunted, or at least scavenged, by early inhabitants of the Americas. Understanding the differences between mammoths and mastodons has been an ongoing study, highlighting the diversity that existed among large elephant-like mammals in that era. These animals inhabited an environment where climatic fluctuations demanded resilience. During glacial advances, vast ice sheets covered northern regions of Europe, Asia, and North America. In these colder intervals, creatures with fur coats, thick layers of body fat, and specialized feeding habits had an advantage. When the ice receded, plains and forests opened up new opportunities, but also changed predator-prey relationships. Many animals had wide geographical ranges, shifting southward as the glaciers advanced and moving north again during interglacial warm periods. One of the biggest mysteries surrounding Ice Age megafauna is why so many species went extinct around the end of the last major glacial period, roughly between 10,000 and 12,000 years ago. There are debates about whether human hunting pressure, rapid climate change, disease, or a combination of factors led to these extinctions. Some species like bison, elk, and caribou survived, adapting to changing conditions or finding refuges in more stable environments. Others, including the woolly mammoth and the saber-toothed cat, disappeared entirely. The story of the mammoth has been better understood in recent years thanks to discoveries in the Siberian permafrost. Scientists have found well-preserved carcasses with flesh, fur, and even stomach contents intact. These finds offer a vivid snapshot of what mammoths ate, what parasites lived on or within them, and what environmental conditions they experienced. There are ongoing studies examining the feasibility of bringing the mammoth back through cloning or genetic engineering. While that idea remains controversial and technologically challenging, it signals the depth of human fascination with these giants. Meanwhile, the saber-toothed cat continues to be an object of study because of its unusual skull and dental structure. Researchers use computer modeling and biomechanical analyses to understand how these animals could open their jaws to an impressive angle without dislocating them. The shape of their canines and the robust nature of their neck muscles suggest a very specialized hunting tactic. By analyzing bones discovered in tar pits or caves, paleontologists reconstruct how these cats cared for their injured, how they might have formed social groups, and how frequently they hunted. It is a field that keeps evolving with each new find, often challenging earlier assumptions. The megatherium, or giant ground sloth, also draws attention due to its sheer size and unique features. Some species were enormous, rivaling the mass of elephants. The idea of a slow-moving giant sloth that roamed open grasslands or woodlands might seem peculiar, but fossil evidence supports this. Their bones appear in South America, Central America, and parts of North America, showcasing the geographical range they once occupied. These animals likely altered the vegetation in their habitats by consuming massive quantities of leaves and stems. They may also have had a symbiotic relationship with smaller creatures that cleaned parasites from their fur or fed on insects near them. Many Ice Age animals coexisted in environments that sometimes varied between grasslands, steppe tundra, coniferous forests, or more temperate zones. The mammoth steppe was a particularly prevalent ecosystem that stretched from Western Europe across Asia and into North America via the Bering Land Bridge. This steppe was characterized by grasslands that supported herds of grazers such as bison, horses, and mammoths. Predators like saber-toothed cats and dire wolves capitalized on these herds for food. The interplay between these grazers and predators shaped the plant life, soil composition, and overall health of the ecosystem. Another fascinating chapter involves how these animals interacted with the ancestors of modern humans and other hominins. Cave paintings in Europe depict recognizable silhouettes of mammoths and other animals, suggesting that humans closely observed and revered them. Bones found in certain archaeological sites show cut marks, indicating that these creatures were hunted or scavenged. Evidence from places like Bluefish Caves in Canada suggests that humans may have encountered megafauna even earlier than once thought. This intersection between human cultures and Ice Age animals continues to spark discussion about how Homo sapiens, Neanderthals, and other groups might have impacted animal populations. In North America, for instance, the arrival of humans is thought to coincide with a sharp decline in many large species. The overkill hypothesis argues that human hunting drove some species to extinction. Others point to climate warming that melted ice sheets and changed habitats at a pace some animals could not cope with. Skeletal remains sometimes point to malnutrition or disease in the last generations of these species, hinting that changing environments were already stressing them before humans became a significant factor. Despite the many extinctions, a few robust survivors carry echoes of the Pleistocene world into the modern day. The muskox, for example, has changed little in some respects from its Ice Age ancestors. These stocky, woolly ruminants still survive in Arctic regions, forming herds to protect against predators. Their ability to endure extremely cold climates stands as a testament to the resilience of certain evolutionary adaptations. Reindeer, known as caribou in North America, also survived and still undertake long migrations across tundra landscapes. Much of what scientists know comes from fossils, footprints preserved in sediment, DNA studies, and stable isotope analyses that reveal details about diets and migration patterns. Advancements in technology have made it possible to examine microscopic wear on teeth, gleaning insights into the type of vegetation these animals ate. Researchers can also look at collagen in bones to determine how heavily certain species relied on grasses versus woody plants. In combination, these methods have helped paleontologists form a clearer picture of daily life in the Ice Age. At times, the idea of Ice Age animals can sound like a monolith, as though they all lived at the exact same time. In reality, different species thrived and declined at various points over tens of thousands or even hundreds of thousands of years. Climate changes came in waves, and glacial periods were separated by warmer interglacials. Some animals were well suited to the cold and spread widely during those times, only to retreat or face extinction during warmer eras. Others may have expanded their territory when forests spread or grasslands changed location. This ebb and flow of populations created a constantly shifting puzzle of distribution. The result is a fossil record that can be spotty and complex. The saber-toothed cat, for example, lived during multiple intervals of the Pleistocene. Scientists believe Smilodon fatalis and Smilodon populator were two separate species that occupied overlapping regions in the Americas, but at slightly different times. The woolly mammoth, Mammuthus primigenius, had a range that included northern Eurasia and North America. The Columbian mammoth preferred slightly milder climates further south. Some areas, like Beringia, served as major corridors for animal movement when sea levels dropped enough to expose land between Siberia and Alaska. Interactions among species were doubtlessly intricate and competitive. Larger predators like saber-toothed cats, dire wolves, and American lions jostled for the same prey resources. Scavengers such as hyenas and smaller canids likely followed in their wake. These relationships can be gleaned from examining fossil sites that contain multiple species. If remains of different predators are found near the same prey, it is possible they competed or at least frequented similar territories. Bite marks on bones can reveal which carnivores ate prey first and which ones arrived later to pick over the remains. Ice Age animals also left behind evidence in the form of dung deposits, footprints, and even hair that is sometimes recovered in cave deposits or frozen ground. Studies of preserved dung from giant ground sloths can show which plants were common in their diets, helping to reconstruct the vegetation of their environment. Footprint trackways can offer clues about group behavior, speed of travel, or interactions with other species. Each bit of evidence weaves into a larger tapestry of Pleistocene life. One aspect that draws ongoing interest is how these animals influenced their environments. Large herbivores, for instance, can transform landscapes by grazing extensively, knocking down small trees and dispersing seeds in their dung. The absence of these megafauna after their extinction might have allowed forests to spread more rapidly or altered the types of grasses that dominated certain regions. This means that modern ecosystems might look very different if those herds of mammoths, mastodons, and giant ground sloths had continued to thrive. There is also a modern ecological concept called rewilding that is partially inspired by the roles these extinct animals played. Some conservationists wonder if introducing analogues, such as large elephants or bison, into areas where Ice Age megafauna once roamed could restore some of the natural processes that disappeared when those original animals went extinct. Though controversial, these proposals highlight just how significant these extinct species were to the function of entire ecosystems. Across the globe, different regions had their own flagship Ice Age creatures. Europe had cave lions, woolly rhinoceroses, and steppe bison. Asia had diverse populations of mammoths and rhinoceroses adapted to cold climates. In the Americas, giant beavers, large camels, and unique horses once thrived. Australia had a suite of huge marsupials like Diprotodon, the biggest marsupial known to have existed, along with giant kangaroos and the marsupial lion known as Thylacoleo. The variety of mega-creatures is often surprising to those who assume the Ice Age only involved mammoths and saber-toothed cats. Although the era of giant sloths and saber-toothed cats has ended, their legacy lives on in our imaginations and in the fields of paleontology and archaeology. Each new discovery, whether a frozen mammoth in the Arctic or a newly identified fossil site in the desert southwest, brings renewed interest and occasionally rewrites parts of the narrative. The fact that humans overlapped with so many of these animals gives an extra layer of immediacy to their stories. They were not just ancient beasts in some long-forgotten epoch, but co-inhabitants of a planet that humans were learning to explore, populate, and change. In a sense, Ice Age animals connect modern people to the deep history of the Earth, reminding everyone that environments and creatures are always changing. While the images of mammoths marching across snowy plains or saber-toothed cats stalking giant bison seem distant, they are only separated from current times by tens of thousands of years in a planet that is billions of years old. That blink of geological time underscores how quickly climates can shift and how entire ecosystems can transform. Understanding the conditions and adaptations of these Ice Age animals helps shed light on evolution, extinction, and the many ways life finds a foothold in an ever-changing world. Humans during the Ice Age faced challenges that might be difficult to grasp in a modern context. The periods of intense cold, shifting glaciers, and unfamiliar landscapes called for ingenuity in almost every aspect of daily life. It was a time when survival depended on understanding the movements of animal herds, the cycles of plant growth, and the variations of climate, that could change a region's resources in just a few years. While technology today provides instant access to heating, cooking, and global travel, humans of the Ice Age had to craft their solutions from raw materials found in their environment. Despite these challenges, they spread to many corners of the globe, leaving evidence of their presence in caves, rock shelters, and open campsites across continents. One of the key developments that helped humans thrive was the crafting of stone tools and weapons. Before the advent of metals, people shaped flint, chert, obsidian, and other types of rock into cutting edges. Archaeologists have uncovered a variety of tool traditions, each revealing important details about how people lived and traveled. The Clovis culture in North America, for instance, is known for its distinctive fluted projectile points, which date back roughly to around 13,000 years before the Common Era. Similar developments occurred in other parts of the world, each adapted to local resources and game. The ability to create fire was also pivotal. Fire provided warmth in freezing temperatures, a way to cook and preserve food, and protection from predators. Archaeological evidence shows ancient hearths where bones, charcoal, and ash remain as testaments to communal gatherings, cooking rituals, and domestic routines. The presence of burned seeds or nuts can hint at what types of plants people gathered. Roasting meat not only made it safer to eat, but more digestible, allowing for better nutrition at a time when every calorie counted. Clothing was another crucial innovation. In frigid environments, staying warm could mean the difference between life and death. People likely relied on animal skins and furs to fashion garments. Needles made from bone or ivory have been discovered, suggesting that tailoring garments was a practiced skill. Some societies developed intricate sewing techniques using sinew threads to piece together multiple skins into coats, pants, hats, and footwear. Footprints in ancient sites sometimes reveal impressions that might indicate footwear of some sort, though direct evidence can be scarce due to the perishable nature of leather and fur. Shelter was equally important. Not all Ice Age groups were nomadic, but many followed migrating herds or moved seasonally to exploit different resources. Some constructed huts from mammoth bones, as evidenced by structures found in parts of Eastern Europe. Others used caves or overhangs as temporary or seasonal refuge. The use of these shelters can be inferred from layers of occupation debris, fireplaces, and the remains of meals. Over time, humans developed more permanent settlements in certain locations, especially during warmer interglacial periods or in areas where resources remained stable year-round. Hunting and gathering formed the backbone of subsistence. Large mammals such as mammoths, reindeer, bison, and wild horses were important sources of meat, hides, and bone for tools. Groups might have coordinated complex hunts using traps or driving herds off cliffs in well-planned events. This cooperation required communication and the sharing of knowledge, indicating that social bonds were deeply woven into survival strategies. In coastal areas or near rivers, fishing and shellfish gathering played significant roles. The discovery of fishhooks, harpoons, and nets in some archaeological sites shows that humans targeted aquatic resources whenever possible. Social structures likely varied widely from one group to another. There is evidence in some burial sites that certain individuals were given more elaborate funerary rituals, suggesting a hierarchy or special roles. Others show group burials that might indicate family units or communal tragedies. Art and personal adornments, such as beads, pendants, or carved figurines, have been found in different parts of the world. These artifacts suggest symbolic thinking, the importance of personal or group identity, and possibly spiritual beliefs. The famed Venus figurines, which date to the Upper Paleolithic in Europe, demonstrate a level of artistic expression that goes beyond mere utility. Language, though not preserved in direct form, would have been an essential tool for passing on knowledge about hunting techniques, tool-making, and cultural practices. While it is impossible to know precisely how their languages sounded, the complexity of their societies implies that they had well-developed communication. Myths, stories, and oral traditions would have been crucial to teaching younger generations about survival and social norms in a challenging environment. Cave paintings, such as those found in Lascaux and Chauvet in France, provide a glimpse into the creative minds of Ice Age humans. These murals of animals, hand stencils, and abstract signs might have held spiritual significance, recorded successful hunts, or served as teaching tools. Despite the frigid conditions of glacial periods, humans managed to migrate across vast distances. The Bering Land Bridge, which emerged between northeastern Asia and northwestern North America when sea levels dropped, allowed people to cross from one continent to the other. Over many generations, humans spread throughout North and South America. Similar movements occurred elsewhere as groups navigated land bridges or used simple watercraft to reach new territories. Each environment they entered demanded new adaptations. For example, near the ice sheets, people needed to cope with polar climates, while in warmer areas, they had to adjust to different plant and animal life. This constant movement and adaptation underscores the resilience and flexibility of human cultures. During interglacial warming, when ice sheets retreated, resources often became more abundant in some areas and populations grew. Artistic expressions flourished, including more elaborate carvings, jewelry, and musical instruments. Bone flutes discovered in parts of Europe show that humans had an appreciation for melody, rhythm, and possibly ritual. As communities grew, they formed broader trade networks, exchanging materials like obsidian, shells, or even pigments used for body painting or cave art. These exchanges facilitated the spread of ideas and technologies across continents, even at a time when long-distance communication was limited to face-to-face contact. Humans were not only hunters, but also scavengers at times. Fossilized bones with cut marks suggest that people took advantage of carcasses left behind by larger predators, especially when fresh kills were found. This opportunistic behavior reflected a deep understanding of the ecosystem. Some of the same places that preserve remains of Ice Age animals, such as tar pits or sinkholes, also reveal artifacts left behind by humans who visited those spots, possibly to obtain raw materials like bones or to scavenge from trapped animals. These interactions paint a picture of humans as adaptive omnivores who made use of whatever they could to sustain life. One of the enduring questions about humans during the Ice Age is how much they contributed to the extinction of megafauna like mammoths, mastodons, and giant sloths. The overkill hypothesis suggests that humans, armed with sophisticated hunting techniques, drove these creatures to extinction. Others point to rapid climate shifts at the end of the Pleistocene as a major factor. Most researchers now believe it was a combination of human pressure and environmental changes that proved too much for many large species to handle. The exact balance between these factors continues to be debated in scientific circles, spurring new research and discoveries. Regions such as the Fertile Crescent in the Near East started to see early forms of plant cultivation and animal domestication toward the tail end of the Ice Age. This transition from nomadic lifestyles to more settled communities laid the groundwork for agriculture, eventually sparking the Neolithic Revolution. While that revolution officially marks the end of the Paleolithic or Old Stone Age, the seeds of domestication and farming were likely planted during the final millennia of the Ice Age. Even so, the timing and rate of this transition varied across the globe, with some groups continuing hunter-gatherer lifeways for thousands of years after others adopted agricultural strategies. Life in glacial times was not uniformly grim and freezing. There were milder intervals within the larger cycles, and humans took advantage of them. Certain areas, sometimes called refugia, remained relatively hospitable even during the coldest glacial peaks. In these refuges, plant and animal life persisted, and human groups could survive. When the ice sheets receded, they emerged from these refuges and expanded into new territories, repopulating areas that had been under ice or otherwise inhospitable. Archaeological discoveries continue to shed light on the complexity of Ice Age cultures. For example, excavations in Denisova Cave in Siberia revealed an unknown hominin group, now called the Denisovans, who coexisted with both modern humans and Neanderthals. Genetic evidence shows that interbreeding occurred among these groups, further illustrating that the human story is not a linear progression from primitive to advanced, but rather a rich tapestry of interwoven populations. Similarly, the remains of Homo floresiensis, or the Hobbit, found on the island of Flores in Indonesia, challenge traditional ideas about human evolution and dispersal. Though these finds might not strictly fit the classic image of Ice Age peoples living among mammoths, they are part of the broader saga of how humans inhabited a world in flux. The spiritual and emotional lives of Ice Age humans are harder to reconstruct. However, objects like carved figurines, painted caves, and ceremonial burials suggest that they pondered matters beyond basic survival. Graves with grave goods imply beliefs in an afterlife, or at least a form of respect for the deceased that went beyond the purely pragmatic. Some burial sites show evidence of ochre use, possibly symbolizing blood or rebirth. These signs, along with the proliferation of art, indicate that humans were reflecting on life, death, and their place in the cosmos. The repeated depiction of certain animals in cave art might indicate reverence or a spiritual connection to these creatures, possibly linked to successful hunts or a sense of kinship with other living beings. The daily routines of gathering, hunting, cooking, and caring for children would have required teamwork. Kinship groups likely forged strong ties, as cooperation was vital for ensuring that everyone had enough food, protection from predators, and a stable social environment. Conflicts could arise, of course, over territory or resources, and archaeologists have found skeletons with wounds that hint at interpersonal violence. Yet, the remarkable spread of humans during this period attests to their ability to negotiate with varied landscapes and sometimes with other human groups. Trading shells or stone materials over long distances is evidence of both cooperation and curiosity. When one imagines humans during the Ice Age, it is important not to stereotype them as simply struggling to stay alive every day in primitive conditions. They were innovative, artistic, and adaptable. They used the resources at hand to meet the challenges of a changing world, whether it was designing sophisticated hunting strategies, creating complex social structures, or crafting beautiful works of art that survived tens of thousands of years. The seeds of modern human culture took root in these times, setting the stage for agriculture, cities, and eventually global civilization. By the end of the last glacial period, humans were on nearly every continent except Antarctica. As the ice receded, new landscapes opened up for habitation. Rivers changed course, coastlines shifted, and many megafauna species disappeared. Amid this upheaval, human communities evolved their customs, languages, and technologies. Some settled down to cultivate crops, while others continued to follow migratory herds. The remnants of their lives, buried in sediment or hidden in caves, continue to fascinate researchers and the public alike. The story of humans during the Ice Age is a testament to human resilience and creativity, traits that continue to shape the world today. Glaciers are enormous masses of ice that form over land from accumulated snowfall, compressing into thick sheets that can flow and reshape the terrain beneath them. During the Ice Age, glaciers extended across vast areas, carving valleys, sculpting mountains, and depositing sediments that would later influence agriculture, water sources, and entire ecosystems. Even in the present day, there are glaciers in polar and high-altitude regions, offering a glimpse into the processes that once dominated so much of the planet. Understanding how glaciers move and interact with their surroundings helps to explain how iconic landscapes like fjords, drumlins, and moraines came into being. A glacier forms when snowfall exceeds snowmelt over many years. Each winter's snowfall adds a new layer of snow, which gets compacted by the weight of subsequent layers. Over time, the pressure turns snow into dense glacial ice. Despite being solid, glaciers are not static. Under tremendous pressure, the ice can deform and move outward or downhill, depending on the terrain. Glaciers flow at varying speeds, some creeping just a few inches a year, while others can surge several feet a day in rare events. Even such slow motion exerts huge forces on the ground beneath. During the Ice Age, ice sheets like the Laurentide in North America and the Fennoscandian in Northern Europe expanded to cover millions of square miles. These colossal ice masses scrape the land, plucking rocks from the ground, grinding down bedrock, and creating deep depressions that would later fill with water to become lakes. Glacial abrasion occurs when fragments of rock embedded in the ice act like sandpaper, scouring and polishing the surface below. Glacial plucking, another erosive process, happens when meltwater seeps into cracks in the bedrock, freezes, and breaks off chunks of rock that become part of the glacier's base. The result of these processes can be seen in many modern landscapes. U-shaped valleys, such as Yosemite Valley in California, are classic glacial landforms. River valleys often have a V-shape because rivers cut down into the land in a more narrow path, while glaciers tend to carve a broader, deeper trough. Cirques, which appear as bowl-shaped depressions near mountain peaks, are where glaciers first accumulate snow and ice. Arêtes and horns form when cirques erode back to back, leaving sharp ridges and pointed peaks. These dramatic features speak to the immense power glaciers wielded as they advanced and retreated over countless years. Moraines are among the most visible glacial deposits. They consist of rocky debris and sediment carried or pushed by a glacier. When the glacier melts back or remains stable for a period, it deposits this debris in ridges. Terminal moraines mark the farthest extent of a glacier, while lateral moraines form along the sides. Medial moraines develop when two glaciers merge, combining the debris from each side. These accumulations can alter drainage patterns and river courses long after the ice has vanished. Kettle lakes, which are common in regions once covered by continental glaciers, form when chunks of ice become buried in glacial deposits, eventually melting to leave behind depressions that fill with water. Meltwater channels are another signature of glacial action. As temperatures rise, meltwater flows across, within, and beneath glaciers, creating a network of tunnels and streams. When this water emerges from under the glacier, it can deposit large amounts of sediment in outwash plains, forming braided rivers. The presence of features like eskers, snake-like ridges of sand and gravel, signals the location of these ancient subglacial meltwater channels. Drumlins, which look like smooth, elongated hills, also form under glaciers, though researchers still debate the exact mechanisms behind their creation. They usually appear in swarms, indicating the direction of ice flow. Glaciers can significantly alter sea levels. During the Ice Age, so much water was locked in ice that global sea levels dropped substantially, exposing land bridges like Beringia between Siberia and Alaska. This allowed animals and humans to migrate to regions that are now separated by oceans. When the climate warmed, glaciers melted, and sea levels rose, flooding coastal areas and reshaping shorelines. Over the past several thousand years, many of these submerged areas remain underwater, hiding archaeological and fossil treasures that once existed on dry land. The weight of ice sheets also pushes down the Earth's crust, a phenomenon known as isostatic depression. Once the ice retreats, the land slowly rebounds upward, a process that can continue for thousands of years after the glacier has disappeared. This rebound can create raised beaches, changes in drainage patterns, and the movement of shorelines over time. Regions such as Scandinavia still experience noticeable uplift today, a lingering effect of the Ice Age. Glacial periods typically alternate with interglacial warm periods. During each cold phase, glaciers expand, while in warmer intervals, they retreat. These cycles are influenced by Milankovitch cycles, which involve changes in Earth's orbital shape, tilt, and wobble. Variations in greenhouse gases, ocean currents, and volcanic activity also play roles. Even small changes in solar radiation can lead to large shifts in how glaciers grow or shrink, especially when feedback loops involving ice albedo, the reflection of sunlight by ice, amplify the effects. As glaciers expand, they increase the planet's albedo, reflecting more solar radiation back into space and cooling the climate further, which allows the ice to spread even more. During the height of the last glacial maximum, ice covered large parts of North America, Europe, and Asia. These ice sheets were sometimes miles thick, burying all but the tallest mountain peaks. They also forced animals and humans to retreat southward or seek ice-free corridors. The meltwater from these ice sheets fed enormous lakes, some of which do not exist anymore. Lake Bonneville, for instance, once covered a large area of what is now Utah, leaving behind the Great Salt Lake as a remnant. The shifting of glacial meltwater also affected ocean currents, potentially triggering abrupt climate events. Glaciers are essential to understanding how the Ice Age shaped ecosystems. As ice advanced, flora and fauna either adapted, migrated, or went extinct. Glacial refugia, pockets of ice-free land with tolerable climates, served as safe havens for plants and animals. Once the glaciers retreated, species expanded out of these refugia and recolonized the landscape. Genetic studies of modern species, such as trees and fish, can reveal patterns of recolonization that trace back to these ice margins. The interactions between glaciers, climate, and living organisms exemplify the interconnectedness of Earth's systems. In certain areas of the world, modern glaciers offer a window into past conditions. Scientists drill ice cores to analyze tiny air bubbles trapped in the ice, providing records of atmospheric composition, temperature fluctuations, and even volcanic eruptions. These datasets extend back tens of thousands of years, revealing how quickly the climate can shift. Glacial retreat patterns in places like the Alps, the Andes, and the Himalayas are indicators of current warming trends, sparking concerns about sea level rise, water supply for downstream communities, and the loss of iconic landscapes. Glaciers also remain a source of fascination and tourism in places such as Patagonia or Iceland. There, visitors can see massive icebergs carving off glacier fronts and crashing into the sea. Fjords, formed by glacial action, continue to enchant travelers with their steep cliffs and deep waters. Though these wonders serve as attractions today, they highlight processes that shaped continents and influenced human migration in the Ice Age. Many of the world's major river systems, such as those in Canada and northern Europe, owe their origin or shape to glacial scouring. In addition to landforms, glaciers can produce a fine silt called glacial flour, which enriches soil and can be carried great distances by wind. Loess deposits found in regions like the Great Plains of North America or parts of China originate from this glacial dust. Loess soils are often fertile, supporting agriculture even long after the ice has disappeared. These mineral-rich sediments have helped some civilizations flourish, underscoring the long-term influence of glacial processes on human societies. Another notable effect is the damming of river valleys by ice or by glacial deposits. When a glacier blocked a valley, it could create huge ice-dammed lakes. If the dam failed, catastrophic floods, known as glacial lake outburst floods, could occur. The scablands of Washington state, for example, were formed by repeated cataclysmic floods from glacial Lake Missoula. These floods ripped through the landscape, carving immense channels and depositing giant boulders many miles away. The scale of these events was initially met with skepticism, but now they stand as prime examples of how suddenly and drastically glaciers can shape the land. While the Ice Age is often thought of as a singular period, it consisted of multiple glacial and interglacial cycles spread out over more than 2 million years. Each glaciation rearranged landforms and ecosystems, layering new deposits over old ones and reshuffling habitats. In many parts of the world, the geological record contains telltale signs of repeated glaciation, such as stacked moraines or multiple layers of glacial till. These cumulative effects created the patchwork of soils, valleys, and watersheds that humans inherited. Glacial processes do not only occur on Earth. Other celestial bodies, such as Mars, show evidence of past glacial movement, although in different conditions. This highlights that glaciers are a natural phenomenon wherever conditions allow persistent ice to accumulate and flow. Studying glaciers on Earth has even helped researchers interpret features on distant planets and moons, bridging the fields of planetary science and terrestrial geology. For modern societies, glaciers serve as important freshwater reservoirs. Regions that rely on meltwater from glaciers for drinking water, irrigation, and hydropower are closely monitoring their retreat. The loss of glaciers can lead to water shortages in dry seasons, destabilize mountain slopes, and reduce the reflectivity of Earth's surface, leading to further warming. In a sense, present-day glaciers are carrying on the legacy of the Ice Age, continuing to sculpt landscapes and influence climate, but with a growing urgency as their retreat signals a rapidly changing planet. Ultimately, glaciers are among the most powerful agents of geological change on Earth. They grind up bedrock, transport massive boulders, and deposit fertile sediments. They also act as archivists, preserving evidence of past climates within their icy layers. During the Ice Age, glaciers dominated entire continents, dictating where animals migrated and where humans could settle. Today's landscapes, from rolling hills covered in rich loess to dramatic fjords and U-shaped valleys, bear witness to the incredible force and reach of glacial processes. By understanding how glaciers move and shape the land, one gains insight into both the past and the future of our planet. During the Ice Age, the planet's oceans underwent significant transformations that affected temperature, sea level, currents, and marine habitats. It helped shape the distribution of marine life in ways that influenced evolutionary paths, migration patterns, and food webs. Oceanic changes were part of the larger climatic shifts that defined each glacial cycle. As massive ice sheets grew on land, large volumes of water were locked away as ice, which meant sea levels dropped across the globe. This drop exposed continental shelves and created land bridges in many regions. At the same time, colder conditions meant that ocean currents were altered, and overall marine productivity in certain places could have looked very different than what is known from later, warmer periods. Scientists believed that during the peak of the last major glaciation, known as the last glacial maximum, sea levels fell by more than 100 meters compared to current levels. This dramatic decrease shaped the geography of coastlines and created connections like the Bering Land Bridge between northeastern Asia and what is now Alaska. This bridge allowed some human and animal populations to move across areas that became submerged again when the ice began to melt. It was a reminder that the ocean's edge was not fixed but shifted regularly with global temperature changes. In colder climates, ocean water tended to absorb more carbon dioxide, and this had implications for marine chemistry and organisms that built shells or skeletons out of calcium carbonate. Researchers studying deep-sea sediment cores found evidence that ocean temperatures and circulation patterns went through periodic swings during glacial cycles. Cold, nutrient-rich water upwellings in various parts of the world either intensified or weakened, which affected the availability of food for many marine species. Species that thrived in cooler waters expanded their range, while warmer water species experienced contractions or migrated to places where conditions remained more suitable. It was not just the temperature of the ocean surface that mattered. The shifts in circulation also rearranged the distribution of oxygen in deeper waters. Some scientists hypothesized that certain deep-sea basins might have been more prone to low oxygen or anoxic conditions during certain periods of the Ice Age. Marine creatures able to tolerate or avoid low oxygen waters had an advantage in those regions. Over time, as the ice expanded or receded, these conditions changed, allowing different species to dominate or forcing them to retreat to refuges. Marine mammals like whales, seals, and walruses had adaptations that allowed them to withstand the colder conditions. Many had thick layers of blubber that provided insulation, and some species shifted their migratory routes to follow food sources that changed location with the shifting ice edges. The presence of ice in regions like the North Atlantic or the Southern Ocean influenced what fish and plankton were available. Animals that fed on plankton, such as some whale species, depended on blooms that occurred during brief windows when sunlight and water temperature supported rapid algae growth. The formation and breakup of sea ice around the poles was especially significant for marine ecosystems. Sea ice served as a platform for animals like polar bears in the far north, although polar bears, as they are known in modern times, had slightly different distribution patterns during cold glacial intervals. Sea ice also provided habitat for algae that lived within or beneath the ice, forming an important foundation for polar food webs. Creatures further up the food chain, including fish, seals, and whales, depended on these smaller organisms. In glacial periods, the extent of this ice was larger in many places, sometimes shifting the habitat ranges for entire species. Coral reefs in tropical and subtropical areas likely faced challenges during glacial times. Lower sea levels meant that reefs were sometimes exposed or were forced to adapt to shallower waters. Cooler global temperatures could also suppress coral growth in certain areas. Nonetheless, evidence suggested that some reefs survived by migrating into deeper waters, or they persisted in pockets where local conditions were stable enough to provide tolerable temperatures and chemistry. After the glaciers receded, these coral populations recolonized large areas once sea levels rose again. Evidence for changes in Ice Age oceans came primarily from drilling into sediment layers on the ocean floor. Scientists studied fossils of microscopic organisms called foraminifera, which recorded shifts in water temperature and chemistry through their shells. By looking at the ratio of oxygen isotopes, or trace elements within these shells, researchers pieced together a picture of glacial and interglacial conditions. It was clear that the oceans played an active role in regulating Earth's climate. When the planet cooled, the oceans took in more carbon dioxide, which in turn affected atmospheric composition. During warming events, the oceans released more carbon dioxide, creating feedback loops that helped transition the planet out of glacial conditions. Besides carbon dioxide, salinity levels in the oceans could shift. When large ice sheets formed on land, fresh water was removed from the oceans. This process made the remaining seawater saltier. In some regions, higher salinity would have contributed to denser water masses that sank and drove deep ocean circulation. In other regions, melting glacial ice released fresh water that reduced salinity. These shifts may have disrupted the formation of deep water in certain ocean basins, altering global heat transport. Although the planet as a whole was cold, there were regional variations in climate that came partly from how the oceans distributed heat. Marine life responded in various ways. Plankton communities changed over time, with cold water species moving to lower latitudes and warm water species retreating closer to the equator. Fish populations were influenced by the shifting distribution of plankton and the availability of open water. Some larger predatory fish might have followed the schools of smaller fish that relocated with temperature shifts. In polar regions, ice shelves and sea ice expanded, providing haul-out sites for seals and changing access to certain feeding grounds. There were also important coastal ecosystems to consider. With lower sea levels, some regions that are now submerged continental shelves were exposed as coastal plains. Rivers cut across these plains, creating large estuaries farther offshore than where modern coastlines sit. Humans and terrestrial animals sometimes lived on these exposed landscapes, leaving behind traces that are now underwater. As the climate warmed and ice sheets melted, these coastal plains flooded again, forcing the populations of both animals and humans to move inland over time. It is one reason why archaeological evidence for human populations from glacial times can be difficult to uncover, as some of those sites are currently submerged. Cold water kelp forests might have expanded in some regions, providing habitats for fish, shellfish, and marine mammals that fed on these resources. Kelp forests are highly productive ecosystems, and when colder waters dominated, kelp could spread more easily in places that might now be too warm or too far south. These forests supported sea otters, fish, and invertebrates that all formed interconnected communities. In areas like the northern Pacific, such expansions of kelp forests could have provided pathways or resources for early human maritime travel, although direct evidence for this theory is still being explored. Another factor in Ice Age oceans was sea ice corridors that might have facilitated or restricted movements for certain species. Large tracts of ice could either open up routes for animals adapted to traveling over ice or block routes for species dependent on open water for migration. Overall, these changes made the Ice Age oceans a dynamic place, full of shifting conditions that tested the resilience of life. Despite the formidable cold, many species found ways to survive or even thrive, taking advantage of the new niches that arose when the climate oscillated between colder and slightly milder phases. As time moved toward the end of the last major ice age, temperatures gradually rose and the giant glaciers on land began to melt. This process poured vast amounts of fresh water into the oceans, driving sea levels up again. Coastlines retreated inland, submerging the land bridges that had been critical for migrations. Marine conditions changed once more, with warmer temperatures allowing coral reefs to rebound in many places. Fish and plankton communities adjusted their ranges accordingly. The slow retreat of sea ice in polar regions also created new feeding grounds for whales and seals. Over several thousand years, the planet entered the current interglacial period, which is often referred to as the Holocene. But the imprints of the Ice Age on marine life have been evident in genetics, species distribution, and the geological record. Many researchers have tried to understand how these past oceanic changes might help predict future climate scenarios. The Ice Age world was clearly a planet of extremes, and the oceans were a major driving force in modulating those extremes. The patterns of ocean currents, like the Atlantic meridional overturning circulation, were sensitive to changes in salinity and temperature, which can be affected by large inputs of fresh water from melting ice. Today's scientists have learned a great deal by examining how these processes operated in the past. Although modern climate conditions are not exactly the same as they were during glacial times, the fundamental physics and biology of how oceans interact with the atmosphere and continents still apply. In summary, the Ice Age oceans were far from static. They went through major variations in temperature, sea level, salinity, and circulation. Those variations were accompanied by shifts in marine ecosystems, driving the evolution and distribution of species that lived in the water. Sea life ranged from tiny plankton to large marine mammals, each adapting to the cold in different ways. Some regions probably served as refuges where species could hold on until conditions improved, while other areas were temporarily abandoned due to extreme cold or changes in sea level. This fluid environment was a foundation for life on Earth, playing a key role in climate regulation and offering a glimpse into how life can endure under challenging circumstances. As the massive ice sheets waxed and waned, the oceans remained a dynamic system, connecting regions of the globe and demonstrating that even in the darkest, coldest periods, there were pockets of resilience and opportunity for creatures that called the ancient seas their home. That concludes a broad overview of Ice Age oceans and the remarkable sea life that adapted to the shifting conditions. Scientists are still piecing together the full picture by examining sediment cores, fossil remains, and genetic studies of marine species. Each piece of evidence adds another layer to the understanding of how the Earth functioned under such drastically different conditions. The legacy of these changes has carried forward into the present, reminding everyone that oceans are intimately tied to climate and that marine ecosystems are shaped by temperature, sea levels, and the availability of resources. The Ice Age serves as a testament to the ocean's power to change and transform under the influence of global-scale shifts, while also offering a lesson in the resilience and adaptability of life. Giant mammals of the Ice Age captured the imagination of researchers and enthusiasts, because of their immense size and impressive adaptations. The frigid conditions that existed across large parts of the world favored mammals that could retain heat efficiently or navigate through snow and ice in search of food. The iconic woolly mammoth is often the first creature that comes to mind when discussing these megafauna. Its thick coat, layered with long guard hairs and insulating underfur, made it well suited for the harsh climates of northern latitudes. Its curved tusks were used for foraging beneath snow, fighting off predators, and possibly for social displays within herds. There were also mastodons, which looked somewhat like mammoths, but belonged to a different branch of proboscideans. Mastodons had different tooth structure, adapted for browsing in forests rather than grazing on grasses. They roamed parts of North America, feeding on trees, shrubs, and other vegetation. Although they resembled elephants, mastodons had a unique build and were part of that great tapestry of large Ice Age creatures that inhabited woodlands and other habitats. Their size and thick coats helped them retain heat in chillier climates, though mastodons were often found in slightly milder areas than their woolly mammoth cousins. Other remarkable giants included the saber-toothed cats. Smilodon is the most famous genus, known for its elongated upper canine teeth. Although many people picture it in icy, snowy environments, saber-toothed cats actually inhabited a range of ecosystems. Fossil finds suggested they lived in places with diverse prey. Their robust forelimbs and powerful jaws indicated a hunting style that might have involved ambush tactics. Some scientists proposed that these cats wrestled large prey to the ground with their forelimbs before using their iconic canines for a killing bite. They appeared physically imposing and lived alongside giant bison, camels, horses, and ground sloths in places like what is now western North America. The giant ground sloths were another remarkable group. Species like Megatherium in South America and Erematherium in parts of North and South America could reach sizes comparable to modern elephants. They had massive claws used for pulling down branches and vegetation, standing on their hind legs to reach higher foliage. Their slow metabolism and bulky bodies suited them for a plant-based diet in environments that included woodlands, grasslands, and open savannas. The idea of a sloth the size of an elephant wandering across Ice Age landscapes is still intriguing to many researchers who have discovered footprints and fossil remains that shed light on their range and behavior. Some evidence suggested these giant sloths may have been able to defend themselves against predators using their claws and bulk. Woolly rhinoceroses also roamed the cold steppes of Europe and Asia, with thick fur coats and large horns. They preferred grasslands or open habitats where they grazed on tough vegetation. Their horns might have helped them clear snow or defend themselves from predators like large cats and hyenas. Another impressive creature was the Irish elk, sometimes called the giant deer, known for its massive antlers that could span over 3 meters from tip to tip. Despite its name, the Irish elk was found in various parts of Eurasia, not just Ireland. Its huge antlers might have been used for display, dominance battles, or mate attraction. The body size of these Ice Age deer was equally noteworthy, allowing them to endure cooler conditions. Giant bears such as the short-faced bear roamed North America. This bear was taller than modern grizzlies and had long limbs that may have made it a fast runner for its size. Some paleontologists thought it might have been an active predator, while others speculated that it could have been an omnivorous scavenger with a preference for meat. Another formidable predator was the American lion, a relative of the African lion, though some believe it deserved its own classification. It was larger than today's lions and roamed the grasslands and open areas of North America in search of prey like bison, horses, and juvenile mammoths. The reasons behind the gigantic sizes of these animals varied. Some believed that colder climates favored large bodies because bigger animals retained heat more efficiently and could travel longer distances in search of food. Larger body size also provided better fat storage for prolonged winters. Others argued that evolutionary histories in isolated continents or certain ecological niches allowed megafauna to flourish without too much competition or predation pressure until conditions changed. In many cases, these animals developed coats, layers of fat, or other physical traits to withstand the chill. Their diets ranged from grass and shrubs to meat, depending on whether they were herbivores or carnivores. It was not only about surviving the cold. The animals that lived closer to the equator also grew large, like some species of elephant relatives that roamed Africa and Asia during glacial periods. Seasonal and environmental pressures shaped evolution, but it was not always about low temperatures. Megafauna existed in different habitats, benefiting from lower competition and abundant resources at various times. The term Ice Age often conjured up imagery of frozen tundra and snow-laden fields, but reality was more diverse. Many regions were cooler than today, but they were not always covered in glaciers. Instead, they had seasonal variations and open grasslands that supported large grazing animals. The presence of giant mammals also played an ecological role. They helped disperse seeds through their dung and movement. They created pathways through dense vegetation, shaping the landscape in ways that smaller creatures could not. Predators that hunted them had to be larger or hunt in groups, influencing the entire food web. Fossil sites where multiple species remains were found together gave clues about predator-prey relationships. Some tar pits, such as those famous ones in what is now California, offered a snapshot of how these animals interacted. Large herbivores got stuck, and carnivores trying to feed on them got stuck as well, preserving a snapshot of Ice Age biodiversity. Social behavior varied among these mammals. Mammoths were believed to have traveled in herds that resembled modern elephants, possibly led by matriarchs. Their young needed protection from predators, and the group dynamic helped them locate food sources in vast landscapes. Saber-toothed cats might have been solitary or social. Fossil evidence did not offer a complete picture. The same could be said for American lions. Giant ground sloths likely moved in smaller groups or alone, browsing for leaves and branches. Mastodons might have had social structures similar to elephants, though direct evidence was limited. Nonetheless, the large footprints they left behind, along with trackways discovered in some regions, suggested that at least some of these creatures traveled together. Human encounters with these animals took various forms. Early hunters might have tracked and hunted mammoths or mastodons for meat, hide, and bones. Some believe that certain giant mammals, like the mammoth, played a part in human culture and mythology, evidenced by cave art and carved figurines. Bones were used for shelter construction in places where wood was scarce. For instance, archaeologists uncovered rings of mammoth bones that might have served as the foundation for dwellings. These interactions hinted at a dynamic relationship that sometimes contributed to the extinction of certain species when hunting became too intense or when combined with the stresses of a changing climate. Paleontologists studying these massive creatures have relied on fossils, footprints, and even frozen remains discovered in permafrost. In some areas, mammoth carcasses were found with tissue, hair, and stomach contents intact, offering an extraordinary glimpse into their diets and environment. These finds revealed that mammoths consumed grasses, sedges, and other tundra vegetation. Isotope analysis of the bones and teeth helped determine migration patterns and seasonal movements. Scientists also examined growth rings in tusks to understand whether certain years brought dietary stress or successful feeding seasons. Giant mammals remained a symbol of the remarkable adaptability of life during extreme climatic swings. They prospered for thousands of years, spreading across continents and adapting to new landscapes. The huge variety of sizes and shapes among these species was a testament to the diverse niches available in the Ice Age world. Some were specialized for cold steppe environments, others thrived in open woodlands, and still others inhabited semi-tropical areas that existed even during glacial periods. Over time, these magnificent animals faced growing pressures from climatic shifts and, in many regions, the growing presence of human hunters. As the ice sheets began to melt and ecosystems changed, many of the largest species found themselves increasingly out of place, unable to adapt quickly enough to the new conditions or to the additional stress of hunting. In discussions about the Ice Age megafauna, the topic of why these giants were so large sometimes touched on what scientists called the Bergmann's rule, which stated that populations and species of larger size were found in colder environments. This was thought to help with heat retention and metabolic efficiency. For herbivores, a big body allowed them to store more energy and travel long distances in search of sparse vegetation. Predators that relied on these big prey animals might have grown larger themselves as they needed strength and size to take down massive herbivores. These evolutionary forces created a world where high-stature animals were relatively common. Although many giant mammals died out toward the end of the last ice age, some species of megafauna did survive into the modern era in reduced forms. Elephants, rhinos, hippos, and giraffes could be seen as successors to the once more widespread phenomenon of giant herbivores. Polar bears and brown bears might have shared certain ancestors with their giant bear relatives. Modern big cats were smaller than their Ice Age counterparts, but still carried a genetic and behavioral legacy from that period. In some islands or remote regions, species persisted longer after they vanished elsewhere. For example, small populations of mammoths lived on Wrangel Island in the Arctic Ocean until a few thousand years ago, outlasting mainland populations. Even though these animals were powerful and often well adapted to glacial conditions, they were not immune to the major changes that swept over the planet as the ice melted. Their fate is tied to the environment that shaped them. As the land warmed and forests replaced open tundra or grassland, many giant grazers lost their favored food sources. Predators that specialized in hunting them found it harder to secure enough prey. The puzzle of how each giant mammal disappeared is still being pieced together. In many cases, it was probably a combination of habitat change, human pressure, and possibly even disease. Some species likely held on in small pockets, gradually fading away as climate continued to shift. Today, the fascination with giant Ice Age mammals endures. Museums around the world showcase their skeletons and reconstruct their likely appearances based on fossil evidence. Researchers continue to find new sites that shed light on how these creatures lived. Sometimes, new technologies, such as ancient DNA analysis, reveal details of their genetic makeup, their evolutionary relationships, and even the presence of diseases they might have carried. The story of their existence and eventual disappearance offers lessons about how quickly environments can change and how species with specialized adaptations can face sudden challenges. Overall, the giant mammals of the Ice Age were extraordinary in their variety and scale. From towering mammoths and mastodons to powerful saber-toothed cats and enormous sloths, they demonstrated that when the planet's conditions allowed, evolution could produce awe-inspiring forms. Their impact on the landscapes they roamed was immense, and their interactions with each other and with early humans shaped entire ecosystems. Although they are now gone, their bones, footprints, and rare frozen remains keep their memory alive. Scientists and laypeople alike remain captivated by these creatures, studying them to gain insights not only into the past, but also into the present and the future of life on Earth. As the planet emerged from the last major glaciation, many of the world's largest and most iconic animals disappeared. This wave of extinctions is often referred to as the end of the Ice Age megafauna. It was a global phenomenon, though it played out differently in each region. In some places, species vanished abruptly. In others, there appeared to be a more gradual decline. Scientists dedicated countless hours to piecing together the causes, which often centered on climate change, human hunting, and possibly other factors such as disease or asteroid impacts. The reality might have been complex, involving overlapping stresses that converged during a period of rapid environmental upheaval. When the ice sheets began to melt, sea levels rose, temperatures increased, and vegetation zones shifted. Open grasslands or steppe habitats that had supported herds of mammoths, giant bison, and other large grazers slowly gave way to forests in many areas. Animals that specialized in cold, open habitats found resources scarcer. Their natural predators, like saber-toothed cats and large bears, also struggled to adapt. It was not simply about warming temperatures. Rainfall patterns changed, and plant communities reorganized themselves. Some species that fed on grasses found themselves having to switch to woody browse, which was not always suitable. Over a few millennia, the composition of entire continents shifted. Those that could adapt to forested or mixed habitats sometimes persisted, while others could not handle the new conditions. Human influence is also cited as a major driver. As humans spread into new territories, they brought advanced hunting techniques and formed organized groups capable of taking down large animals. In North America, the arrival of Paleo-Indian cultures correlated with the disappearance of mammoths, mastodons, giant ground sloths, and other formidable creatures. Although the extent of human responsibility is debated, there is little doubt that hunting pressure was a contributing factor in some regions. Bones with cut marks, kill sites, and other evidence suggested that people targeted these big animals for meat, hides, and bones. When combined with the stresses of habitat change, this hunting pressure may have tipped many populations into decline. Some scientists studied the possibility of a catastrophic extraterrestrial impact around the time that the megafauna began to vanish, sometimes called the Younger Dryas impact hypothesis. According to this idea, a comet or asteroid exploded over North America roughly 13,000 years ago, triggering massive wildfires and sudden cooling. While there was evidence of a cool period known as the Younger Dryas, not everyone was convinced that a comet impact was the cause or that it caused widespread extinctions. Critics argued that the evidence for such an event was inconclusive or that it did not line up perfectly with extinction timelines. Regardless of whether an impact occurred, it was clear that the climate became unstable around the onset of the Younger Dryas, placing additional stress on already vulnerable populations. Disease is another proposed explanation. Large, closely spaced herds might have been susceptible to outbreaks of pathogens, especially when stressed by environmental changes. However, direct evidence linking disease to the disappearance of any particular megafaunal species remained elusive, though it could have been a factor. At times, changes in climate patterns might have brought animals into contact with new pathogens or forced them into smaller, more crowded refuges where disease spread more easily. Still, most experts believed that the main culprits were a combination of climatic shifts and human activities. The extinction timeline varied by region. In North America, many large species were gone by around 11,000 years ago. In South America, extinctions stretched over a broader time range, with some species hanging on longer. In Europe and Asia, mammoths survived in certain pockets, such as on Wrangel Island in the Arctic Ocean, until maybe 4,000 years ago. That meant they coexisted with humans who had already established farming communities in some parts of the world. This prolonged survival in isolated areas suggested that direct human hunting was not the only factor, as populations on small islands might have been protected from intense hunting pressure. Yet they still eventually died out, possibly due to a combination of limited genetic diversity, continued climate warming, and shifts in available vegetation. Some smaller creatures adapted and survived. Deer, wolves, and smaller bears continued into modern times, albeit sometimes with shifts in their ranges. Bison managed to persist, though their numbers likely dropped in many regions. Horses disappeared from the Americas but survived in Eurasia until humans reintroduced them to the New World millennia later. Camels, which also existed in North America, vanished from that continent but lived on in Asia and Africa in domesticated or wild forms. These differential survival patterns hinted that the largest and most specialized creatures were at the greatest risk as they needed expansive territories and reliable sources of food. Environmental proxies like pollen records, stable isotope data, and sediment analysis revealed that the habitats used by large grazers changed rapidly. Grasses diminished in areas replaced by spruce, pine, or deciduous trees. The thick coats and large bodies that had been advantages on the cold steppe became liabilities in denser woodlands, where navigating in search of patchy food sources was challenging. Carnivores that depended on these grazers faced starvation if they could not switch to smaller or more elusive prey. It was a domino effect, in which the loss of one species set off consequences for the entire ecosystem. In some parts of the world, the demise of large herbivores might have altered fire regimes, as fewer animals grazed on grasslands that could then accumulate dry vegetation. This could lead to more intense wildfires, further transforming landscapes. The evolutionary relationships between plants and megaherbivores were disrupted. Some plants that relied on large animals for seed dispersal struggled to spread into new territories. Scientists examining the present-day ecology of certain regions found plants with large fruits or seeds that seemed adapted for consumption by big mammals that no longer existed. Archaeological sites sometimes shed light on interactions between humans and the last members of these megafauna species. But the picture remained incomplete. Scientists debated the significance of spear points found among mammoth remains or the timing of certain kill sites. Some believed that even modest hunting pressure on species with low reproductive rates could have been detrimental, especially as those animals were already stressed by climate shifts. Others contended that the environment alone was the primary driver, with humans only playing a secondary role. The debate persisted, though most studies acknowledged that multiple factors were at play. The end of the Ice Age megafauna represented one of the most significant extinction events since the disappearance of dinosaurs, though it was more gradual and less total. Many smaller species survived, and life continued in new forms. However, the disappearance of so many large animals changed the dynamics of ecosystems on nearly every continent. It influenced which plants dominated, which predators thrived, and how people made a living off the land. In some regions, people turned to smaller game, fish, or developed early agriculture, in part because the large creatures they once hunted were gone. People in later periods remembered or mythologized these creatures. Stories or art sometimes depicted giant beasts that were feared and revered. In some cultures, mammoth bones might have been interpreted as the remains of dragons or giant mythical beings. Evidence of humans constructing dwellings from mammoth bones suggested that these animals were deeply intertwined with early human survival. When the numbers of these animals diminished, it likely forced major adaptations in human societies. From a modern perspective, the idea that entire species of giant animals existed so recently reminded many of how dynamic the Earth's history has been, even within the relatively short span of human presence. Scientists in the present day continued to search for new archaeological and paleontological sites that might clarify extinction timelines. They also applied molecular techniques to study ancient DNA, trying to see whether populations had gone through bottlenecks or whether inbreeding contributed to their decline. In some instances, studies found that megafaunal populations were already declining before humans arrived, pointing to climate change as the main cause. In others, the timing of extinctions aligned closely with human colonization events, suggesting a stronger role for hunting. Ultimately, the global pattern was not uniform, which made it challenging to make one definitive statement about what happened everywhere. Looking at the end of the Ice Age megafauna provided a window into how ecosystems responded to rapid warming events. When the planet warmed and ice retreated, it was not a simple matter of all species shifting their range northward. The reorganization of vegetation, water availability, and interactions with humans resulted in a complex tapestry of local extinctions and survival stories. These findings offered insights for modern conservation, showing how vulnerable large animals could be when faced with rapid environmental changes and hunting pressures. Elephants, rhinos, and other large mammals alive today might be following a similar path if habitat loss and poaching continue unchecked. Reflecting on the disappearance of these creatures also highlighted the resilience of some species. Musk oxen, for instance, survived in Arctic environments, and caribou or reindeer persisted in northern latitudes. These animals were able to cope with the expanding tundra and taiga habitats that emerged after the glaciers withdrew. Bison in North America survived in reduced numbers, eventually recovering when protected. Human activity might have spelled doom for some species, but also allowed certain others to thrive under different circumstances. The global wave of Ice Age extinctions became a cautionary tale about the interplay between environment, climate, and human expansion. The planet's climate had always shifted, but the presence of humans with the capacity for large-scale hunting introduced a new factor. Once a species was gone, entire ecosystems had to adjust. This period of upheaval shaped the modern world in ways that are still being studied. The empty niches left behind by animals like mammoths and giant ground sloths were never truly filled. Instead, smaller animals took up new roles, and vegetation changed accordingly. In conclusion, the extinction events at the end of the Ice Age marked a profound turning point in Earth's history. Massive creatures, perfectly adapted to cold climates and wide-open habitats, disappeared as the world warmed and people spread across continents. Climate change reshaped habitats, while human hunters added pressure on struggling populations. Other factors like possible cosmic impacts and disease may have contributed as well. The result was a loss of biodiversity that forever altered the face of the planet. Although remnants of those giants persisted in some corners of the globe for a time, they too eventually succumbed. The Ice Age megafauna's end underscored the fragility of even the most imposing creatures when environmental shifts occurred rapidly and human influences were introduced. Today, their bones and rare frozen remains are reminders that Earth's history is marked by dramatic changes and that the balance of life can be more delicate than it appears. Evidence from ice cores and sediment layers has been one of the most significant ways researchers have learned about ancient climate conditions and the realities of the Ice Age. Ice cores can be thought of as frozen time capsules that hold traces of Earth's atmosphere, temperature patterns, and even microscopic life forms. Sediment layers in lake beds and ocean floors preserve pollen grains, shell fragments, and minute clues that show how the climate changed over thousands of years. These combined sources of information help paint a vivid picture of a world marked by vast ice sheets, dramatic temperature shifts, and evolving ecosystems. Over the past century, scientists have developed more advanced methods for drilling into ice sheets and collecting deep sediment samples. That progress has led to remarkable insights about how different glacial and interglacial periods influence not just temperature, but everything from ocean currents to vegetation belts. Ice cores come primarily from places where ice has remained stable for a very long time. These areas are usually found in Antarctica, Greenland, and high mountain glaciers around the world. The process of drilling and extracting an ice core can take a team of researchers an entire season, sometimes involving specialized rigs capable of going thousands of feet below the surface. Each new layer of ice they encounter represents a distinct slice of the planet's past. Over many years, snow piles up and is gradually compressed into ice, trapping air bubbles and other particles that were around when the snow originally fell. By analyzing chemical isotopes, dust particles, and various trapped gases, scientists can form conclusions about everything from the average global temperature to the frequency of volcanic eruptions. One of the first major breakthroughs in ice core research happened in the mid-20th century when researchers drilled into the Greenland ice sheet. Although the equipment was primitive by today's standards, the cores revealed clear evidence of alternating warm and cold phases, supporting theories about the repeated onset and retreat of ice ages. It was discovered that the ratio of heavy isotopes of oxygen to lighter isotopes changed depending on temperature. When the Earth was cooler, snow carried a different oxygen isotope ratio than when the planet was warmer. This ratio serves as a temperature gauge that stretches far back in time, sometimes hundreds of thousands of years. Scientists also found dust layers in the cores that hinted at windy, arid periods, likely correlating with more intense cold phases when vegetation was sparse and soils could easily be swept into the air. Antarctica's ice has proven even more informative in certain respects. The eastern Antarctic region has ice that in some spots is well over a mile thick, accumulated over many glacial cycles. Drilling projects at Vostok Station, for example, uncovered climate records spanning hundreds of thousands of years. In those cores, scientists identified a repeating cycle of glaciation and deglaciation roughly every 100,000 years, which lined up with Milankovitch cycles. That means Earth's orbital variations, combined with feedback effects from greenhouse gases and ice albedo, drive the planet in and out of ice ages. The air bubbles in the Antarctic ice revealed concentrations of carbon dioxide and methane. As the planet cooled, carbon dioxide levels tended to drop. As temperatures rose, greenhouse gas levels rose as well, though there has always been debate about which process truly initiated the change. The detail found in ice cores is more than just broad temperature swings. Researchers have identified shifts occurring within a matter of decades, indicating that certain changes in the Earth's climate system can happen quite rapidly. This challenges the old assumption that glacial changes must unfold slowly over millennia. Instead, the record suggests there have been abrupt climate flips, possibly triggered by changes in ocean circulation, volcanic eruptions, or sudden influxes of fresh water from melting ice sheets. For instance, certain layers in Greenland cores show dramatic warming events, sometimes in less than a century. These findings highlight how delicate the Earth's climate balance can be and how interconnected the components of the climate system truly are. Apart from drilling into massive ice sheets, scientists also collect ice cores from glaciers in places like the Andes, the Himalayas, and the Alps. These smaller cores do not necessarily go back hundreds of thousands of years, but they still shed light on local or regional climate histories stretching back tens of thousands of years. That data has been cross-referenced with the information from Greenland and Antarctica to create a more global understanding of temperature shifts. For instance, if one region experiences a shift in precipitation patterns, it may be reflected in the dust or chemical composition of the ice there. By comparing records from multiple continents, researchers can confirm whether a change was global or more localized. Moving on from ice cores to sediment layers, the method is slightly different but equally revealing. Sediment layers in lake beds, ocean floors, or coastal areas accumulate gradually as particles settle out of the water. When studied in cross-section, these layers can show transitions in local plant life, erosion patterns, and even dust deposition rates. In lakes that have remained relatively undisturbed, the sediment can capture annual layers known as varves, formed by seasonal changes in the mineral and organic content of the water. This layering allows scientists to count back through time and determine how climate shifts affected plant growth, erosion, and other factors. The presence of certain microscopic organisms like diatoms can tell whether the lake was cold or warm, deep or shallow, and fresh or brackish. In marine sediments, foraminifera shells provide important clues. These tiny organisms incorporate isotopes of oxygen into their shells, which are then preserved on the ocean floor when they die. Much like the isotopes in ice cores, the oxygen isotopes in foraminifera shells change with temperature. By analyzing the shell composition from different layers of sediment, scientists can build a timeline of ocean temperatures. This helps determine when glaciers were expanding on land, because expanding glaciers would draw more water out of the oceans and thereby change sea level. It also helps show how ocean circulation changed, which can have ripple effects on global climate. Cold periods often see stronger or weaker thermohaline circulation, altering how heat and nutrients are distributed around the globe. Pollen analysis is another facet of sediment study, Because plants produce distinctive pollen, sediment layers can reveal shifts in vegetation. If a lakebed sediment core from northern Europe contains a high percentage of spruce pollen from a particular layer, it may suggest that the climate at that time was cool and moist. A shift to more grass pollen might indicate drier and colder conditions, hinting at an environment where large conifer forests retreated. By aligning this data with ice core findings, researchers can see how plant life migrated or adapted during different stages of the Ice Age. Similar techniques are used in peat bogs, where layers of partially decayed plant matter can also be dated to reveal vegetation changes over time. Volcanic ash layers can also be found in both ice cores and sediment layers. Each major volcanic eruption deposits ash in various parts of the world. By matching the ash composition with known eruptions, scientists can precisely date certain layers. This cross-dating technique helps synchronize timelines from different sources, making it easier to correlate a specific climate event in Greenland with something that happened in Antarctica or the North Atlantic. These layers of ash can be quite distinct, sometimes visible even to the naked eye in the cores. For example, a major eruption might deposit a band of grayish ash among the usual white layers of compressed snow in an ice core, or a more dark-hued band in a sediment core. Beyond temperature and vegetation changes, ice cores can also preserve traces of cosmic events. Particles from meteor impacts or fluctuations in solar activity may appear as unusual isotopes in certain layers. High levels of beryllium-10, for example, can indicate times of increased cosmic radiation, sometimes corresponding to changes in Earth's magnetic field or to solar behavior. These are more specialized areas of research, but they show how versatile ice cores and sediment layers can be in preserving aspects of Earth's history that might not be available through other means. The combination of ice core data with sediment studies has rewritten the understanding of how swiftly and dramatically the Earth's climate can shift. Decades ago, scientists believed that major climate changes required tens of thousands of years. Now, thanks to the detail provided by these natural records, it is understood that abrupt shifts might take place within a few centuries, or even just a few decades. Sediment cores have also shown how sea levels rose and fell in tandem with the advance and retreat of ice sheets. During the peak of the last ice age, huge amounts of water were locked up on land, causing ocean levels to drop. This exposed land bridges, such as the one between Asia and North America, which allowed people and animals to migrate across regions that are now separated by water. One recurring theme in both ice and sediment data is the role of greenhouse gases in global temperatures. When ice core data shows a sharp rise in carbon dioxide concentration, it usually goes hand in hand with a warming trend. Similarly, sediment data might reflect a transition from cold-tolerant plant species to those favoring milder conditions, confirming that the climate was indeed warming. The exact timing and cause and effect relationship can be complex, but the overarching correlation between greenhouse gas levels and temperature emerges as consistent across these different natural archives. For those who wonder why scientists trust these data sets, there is a vast amount of cross-referencing involved. Independent labs around the world measure the same ice or sediment samples to confirm results. Different isotopic methods, such as oxygen-18 to oxygen-16 ratios or even hydrogen isotopes, are used to ensure the conclusions are robust. Radiocarbon dating might be employed for organic matter in sediment layers, while argon dating might be used on trapped gas bubbles in ice cores. When multiple dating methods and multiple lines of evidence all converge on the same story, researchers grow more confident that they are seeing a real reflection of ancient climate conditions. Over the years, the technical aspects of drilling cores have evolved. Early explorers in the mid-19th century faced tremendous challenges just trying to reach remote ice fields. By the early 20th century, hand drills that could only extract shallow cores were the norm. Since the 1950s and 1960s, mechanized drills have allowed teams to go deeper. In Antarctica, teams set up entire research stations for years, carefully drilling out long cylindrical sections of ice and shipping them to labs across the globe. Preservation of these cores is vital, so many facilities maintain specialized cold storage rooms to keep the samples at freezing or sub-freezing temperatures to avoid contamination or melting. Sediment cores are often collected by research vessels that use a coring tube to penetrate the ocean floor. Lake coring can be done from a floating platform or from frozen surfaces in winter. These processes also require a delicate touch because the layers can be disturbed if the tube is driven in too forcefully or at an angle. Once retrieved, the cores are split, photographed, and inspected for visible changes in color or texture. Scientists then take small samples at regular intervals to measure properties such as magnetic susceptibility, organic content, or specific isotope ratios. The data they gather is compiled into large databases, allowing for extensive comparisons between cores taken from different parts of the world. A major takeaway from ice and sediment research is that the Earth's climate system is both resilient and sensitive. Over hundreds of thousands of years, the planet has swung between frigid periods when ice sheets dominated the landscape and warmer interglacial periods when forests and grasslands flourished. Yet within these large cycles, there have been quick transitions that defy the notion of climate as a slow, lumbering force. Sediment cores show layers of sudden environmental change, such as intense flooding events or rapid expansions of a particular plant species, which demonstrate how fast local or regional changes can occur. This knowledge offers perspective on present-day climate concerns. While modern conditions differ in many ways from ancient ones, the patterns of cause and effect embedded in these ice and sediment archives remain relevant. In sum, ice cores and sediment layers are vital to understanding the evidence of the Ice Age. By drilling deep into glaciers and extracting long columns of the planet's frozen history, scientists have uncovered temperature fluctuations, greenhouse gas variations, and shifts in precipitation. At the same time, sediment cores from lakes and oceans have contributed rich details about the plant and animal life that struggled and thrived in those shifting climates. These archives do more than paint a static portrait of a cold world. They reveal how dynamic that world was, how interconnected its elements could be, and how quickly everything could change when certain thresholds were crossed. As technology improves, future generations of researchers are likely to refine these records even further, uncovering new chapters of Earth's climate story that have yet to be told. Life in Ice Age Europe was shaped by the cycles of advancing and retreating ice sheets that defined the continent's climate for tens of thousands of years. During colder periods, vast ice sheets stretched across the northern regions, while tundra and steppe environments extended much farther south than they do today. People, animals, and plants had to adapt to harsh conditions that included short growing seasons, limited resources, and sudden environmental changes. Although modern impressions might picture a bleak land of unending snow, there was actually a surprising diversity of habitats, ranging from cold tundra regions populated by hardy grasses to slightly warmer refuges where forests could survive. During the height of the last ice age, sometimes called the last glacial maximum, northern Europe was largely uninhabitable due to thick ice sheets. Human populations tended to cluster in more southerly areas, such as parts of the Iberian Peninsula, southern France, and the Balkans, where milder climates allowed for the survival of game animals and edible vegetation. In these regions, bands of hunter-gatherers developed strategies to deal with the cold. They fashioned clothing from animal hides, built shelters out of bones and wood, and developed specialized tools for hunting large mammals like reindeer, horses, and mammoths. Many of these peoples are known collectively as Upper Paleolithic cultures, which include groups like the Aurignacian and Gravettian. One notable hallmark of Ice Age Europe is the incredible cave art left behind by early inhabitants. The famous cave paintings of Lascaux in France and Altamira in northern Spain are just two examples of how these communities expressed their experiences with animals and the landscape around them. The images depict bison, deer, horses, and other creatures, many of which thrived in the cold, open steppe environment. The artistic skill displayed is remarkable, with shading and perspective techniques that suggest a sophisticated understanding of both art and the anatomy of animals. Although there is much debate about the exact purpose of these artworks, many believe they served spiritual or cultural roles, possibly relating to hunting magic or group identity. Europe was not a static place during the Ice Age. As conditions changed, animal populations migrated and human groups followed. When temperatures dropped severely, people abandoned northern territories, seeking refuge in the south. As the ice retreated during warmer intervals, they ventured back into newly opened landscapes, which were often rich in fresh grasses and returning herds. This cycle of expansion and contraction defined much of the region's demographic patterns. Over thousands of years, this back-and-forth movement led to cultural exchanges and evolving technologies. Various groups refined their stone tools, creating spear points, blades, and scrapers that improved their hunting efficiency. While large mammals like woolly mammoths and woolly rhinoceroses sometimes grabbed the spotlight, smaller species also played an essential role in the Ice Age ecosystem. In more temperate refuges, people had access to fish, birds, and small game, supplementing their diets when large game was scarce. Gathering edible plants, nuts, and berries during the warmer months was also part of survival. Although the vegetation was generally limited compared to today, certain hardy plant species were still available, especially in areas near rivers or in sheltered valleys. This variety of resources offered some flexibility, allowing communities to adapt to changing conditions. Neanderthals also figure into the story of Ice Age Europe. They had been present on the continent long before anatomically modern humans arrived. Neanderthals were well adapted to cold climates, with robust builds and strategies for survival in harsh environments. However, by the time the last Ice Age reached its peak, Neanderthals had disappeared, and modern humans were occupying most of the habitable regions. The reasons for Neanderthal extinction are still debated, with theories pointing to climate stress, competition for resources, or even interbreeding and assimilation with modern human populations. Technology evolved significantly over the course of the Ice Age in Europe. Early in this period, stone tools were relatively simple, but later on they became more specialized. Artifacts made from bone and antler emerged, such as needles, harpoons, and even simple musical instruments like flutes. Fire was, of course, central to daily life, not just for warmth, but also for cooking and protection from predators. Shelters might be built against rock faces or in caves, lined with furs or hides to provide insulation. Evidence from sites like Dolní Věstonice in the Czech Republic shows that people were forming complex communities with some degree of social organization, creating art objects, and even possibly firing clay figurines in rudimentary kilns. Ice Age fauna in Europe included plenty of megafauna, as well as medium-sized herbivores like reindeer, bison, wild horses, and red deer. Predatory animals like cave lions, hyenas, and wolves roamed the region. Early human groups had to be constantly aware of these threats, as a single lion or hyena attack could devastate a small band if they were not prepared. The distribution of animal species was heavily influenced by temperature and vegetation changes, so hunters had to adapt to wherever the herds went. During some periods, reindeer might be the dominant prey, while at other times, horse or bison could be more available. The last glacial maximum in Europe reached its peak around 20,000 years ago. Glaciers covered much of Scandinavia, northern Germany, and significant parts of the British Isles. The climate was cold and arid, making large swathes of land uninhabitable. Human populations mostly clustered in southern refuges like southwestern France, the Iberian Peninsula, Italy, and parts of the Balkan region. Within these refuges, people developed cultural traditions that can be traced through their distinctive tools and art styles. Some groups created portable art objects like carved figurines of animals or stylized human forms. Others focused on elaborate cave paintings. Despite hardships, these communities managed to thrive, suggesting a high degree of resourcefulness and adaptability. As the ice sheets retreated, Europe experienced significant transformations in its landscapes. Permafrost thawed, rivers changed their courses, and vegetation began to expand northward. Steppe and tundra gave way to grasslands, and eventually woodlands moved in. Large herds of reindeer and mammoth eventually retreated to cooler northern zones or died out, leading hunters to shift their focus to other species such as deer, boar, or smaller game. The transition from the Upper Paleolithic to the Mesolithic period saw the development of microliths, small stone tools that could be fitted into composite implements like arrows or harpoons. These technological changes went hand in hand with shifts in diet and settlement patterns, as people exploited lakes, rivers, and coastal areas for fish and shellfish. The movement of human groups during the Late Ice Age set the stage for the genetic makeup of modern Europeans. Studies of ancient DNA have shown that Paleolithic hunter-gatherers contributed to the gene pool, which later mixed with incoming farmers during the Neolithic. Ice Age migrations shaped linguistic and cultural distributions as well. Although direct evidence of language is scarce in prehistoric contexts, many linguistic theories suggest that repeated expansions and contractions of populations would have had a major impact on the dialects spoken across different regions. Archaeological sites, such as Grotte Chauvet in France, reveal that humans in Ice Age Europe had artistic sensibilities, religious or spiritual beliefs, and social structures that went beyond mere survival. The Chauvet cave paintings, some of which date back over 30,000 years, depict animals with remarkable detail. The presence of possible ritual artifacts in other sites indicates that people engaged with spiritual or shamanic practices, though the exact nature of these beliefs remains speculative. What is certain is that the challenging environment did not stop them from expressing creativity and forming social bonds that extended beyond basic group hunting. Europe's topography itself underwent constant reshaping. When glaciers grew, they ground down mountains and carved out valleys. When they melted, massive meltwater floods altered river systems and created fertile plains in some areas. The English Channel, for instance, was likely a land bridge for parts of the Ice Age, allowing animals and people to move between what is now Britain and continental Europe. Only later did rising sea levels inundate that land connection, isolating Britain. Doggerland in the North Sea was another region that connected modern-day Britain to mainland Europe before it was submerged. Such changes fundamentally affected migratory routes, settlement patterns, and resource availability. Housing structures during the European Ice Age could be quite varied. Some groups favored rock shelters or shallow caves, taking advantage of natural protection against the elements. Others built huts from mammoth bones, placing the huge curved tusks to form a framework that was then covered with hides and insulating materials. The remains of these bone huts have been found in places like Ukraine and southern Russia, though they are associated with the broader Ice Age environment rather than strictly Central or Western Europe. There are also open-air sites where evidence of post holes suggests wooden frames were used. In many of these shelters, hearths were carefully placed to provide warmth and to cook food. Charcoal remains and ash layers have helped archaeologists map out interior living spaces. Because winters could be long and harsh, storage and preservation of food became important. There is evidence that people in certain regions stored meat in cold areas, possibly near ice or buried in the ground to slow decay. Some may have dried or smoked meat as well. This made sense in a seasonal environment where hunting might be difficult in the worst of winter. The invention of tailored clothing, including sewn garments made of animal hides, was another major breakthrough that allowed people to endure cold conditions. Needles crafted from bone have been found at multiple Upper Paleolithic sites, confirming that sewing techniques were known and practiced. Life in Ice Age Europe was not a static or uniform experience. Different groups developed unique cultural traditions, sometimes separated by hundreds of miles of ice or tundra. Over time, they traded ideas, materials, and even genes. Ivory beads, shell ornaments, and stone tools from distant sources have been discovered, implying that networks existed for exchanging goods and perhaps forging alliances. Although the distances might seem great, glaciers sometimes acted as barriers that forced groups to move along similar corridors, creating opportunities for interaction. These exchanges likely contributed to cultural innovations, with new ideas spreading across wide areas. Death and burial practices also provide insight into these communities. While data is limited, some graves show evidence of deliberate placement of bodies with grave goods such as beads or tools. One famous example is the triple burial at Dolny Viestonitz, where the individuals were arranged in a specific way and sprinkled with red ochre, possibly indicating some form of ritual significance attached to death. Such findings hint at a social and symbolic complexity that goes far beyond mere subsistence. As the climate warmed near the end of the last ice age, many of the large ice age mammals started to die out or move north. Mammoths, woolly rhinoceroses, and cave lions disappeared from the European landscape. This extinction process was not instantaneous, and for a time, humans may have still hunted the last populations of these animals in certain refuges. However, as forests expanded, species like deer, wild boar, and aurochs became more prominent. This shift fundamentally changed the hunting strategies and lifestyle of people in post-Ice Age Europe, leading to new technological developments like the bow and arrow. By about 10,000 years ago, much of Europe was transforming into environments more recognizable to modern eyes. The glaciers had retreated to the far north, and lush forests covered large areas. Rivers teemed with fish, and coastal regions offered shellfish and other marine resources. Eventually, the Neolithic Revolution would bring agriculture and permanent settlements, but the legacy of the Ice Age persisted in Europe's genetic, cultural, and linguistic landscapes. The memory of the colder world is etched into its cave art, its archaeological remains, and even its myths and legends that speak of a time when giants roamed the land and vast ice sheets ruled the horizon. Ice Age Europe, then, was a land of constant change, requiring resilience and ingenuity from all life forms. People adapted to sweeping climate fluctuations, found ways to exploit sparse resources, and created cultural traditions that still resonate through some of the ancient art discovered today. Their footprints can be traced across the continent, from the cold northern steppes to the milder southern coasts, revealing an epic story of survival, migration, and creativity under the harshest conditions. The era was demanding, but it sparked innovations that laid the groundwork for much of human development on the European continent. Life in Ice Age. North America presented its own set of challenges and unique environments. Just like in Europe, massive ice sheets dominated the northern part of the continent during the peak of glaciation. The Laurentide ice sheet covered much of modern-day Canada and parts of the northern United States, while the Cordilleran ice sheet blanketed the mountainous regions of western Canada and Alaska. Between these two colossal sheets lay corridors that opened or closed at various times, influencing the movement of animals and people. In the far south, regions like modern-day Mexico, the southeastern United States, and the southwestern deserts had cooler and wetter climates than they do now, supporting an array of megafauna and early human settlements. One of the most widely discussed aspects of life in Ice Age North America is the migration of people from Asia across the Bering Land Bridge, also called Beringia. Because so much water was locked in the ice sheets, sea levels were significantly lower, exposing a stretch of land that linked Siberia and Alaska. This route allowed animals and eventually humans to cross into North America. For a long time, the prevailing theory was that the earliest arrivals, known as the Clovis culture, came through an ice-free corridor in central Canada around 13,000 years ago. More recent evidence suggests that people may have been in the Americas even earlier, traveling along the coastal routes or arriving in small waves over time. However they arrived, these early groups had to adapt quickly to the diverse environments they encountered, from tundra in the north to temperate forests and grasslands further south. North America's Ice Age fauna was rich and varied, featuring species like mammoths, mastodons, giant ground sloths, saber-toothed cats, and short-faced bears. Large herds of bison roamed the plains, but these were often larger and slightly different from modern bison. Early human groups found abundant hunting opportunities if they had the tools and cooperative strategies to take down these impressive creatures. The remains of mammoths with butchering marks have been uncovered at various sites, suggesting that humans engaged in organized hunts or scavenging. Clovis points, which are stone projectile points characterized by fluted channels, have been discovered alongside these remains, signifying the skill and ingenuity of these ancient hunters. In the western part of the continent, near the edge of the Cordilleran ice sheet, mountainous terrain created microclimates that supported a mix of megafauna, smaller animals, and plant life. Lakes and rivers fed by glacial meltwater were teeming with fish, while the forests on lower slopes offered deer, elk, and other game. Early inhabitants developed tactics suited to these niches, using stone tools tailored for fishing, hide scraping, and big game hunting. Rock shelters or caves in mountainous regions provided natural protection from the elements, and some sites hold evidence of seasonal occupation, indicating that groups moved between highland and lowland areas depending on the time of year. In the southern regions, such as present-day Texas, Florida, and northern Mexico, the climate was much more favorable for a year-round presence. Wetlands, lakes, and grasslands would have supported a variety of megafauna, making them prime hunting grounds. However, even in those more temperate areas, the climate was different from today's. Colder temperatures and altered precipitation patterns meant that deserts were less expansive, and certain areas that are now barren hosted lakes. Paleo-Indian sites in these areas show a culture deeply connected to large game hunting, but also collecting plant resources when available. Stone tools found in these regions sometimes share similarities with Clovis technology, indicating a wide spread of ideas and methods, likely transmitted through networks of trade or migration. One notable puzzle in Ice Age North America is the relatively rapid extinction of many megafauna species around the end of the Pleistocene. Mammoths, mastodons, giant ground sloths, and saber-toothed cats disappeared within a relatively short span of geological time. Researchers continue to debate whether climate change, human hunting, or a combination of both drove these extinctions. There is also the controversial hypothesis involving extraterrestrial impacts or airbursts that might have contributed to a sudden environmental collapse. Regardless of the exact cause, the disappearance of these large animals had a dramatic impact on the ecosystems and the lifestyles of the people who depended on them. By the close of the last ice age, around 10 to 12,000 years ago, significant changes were unfolding. The ice sheets retreated northward, freeing up huge swaths of land across Canada and the northern United States. Meltwater from the glaciers carved new river valleys and formed extensive lakes, such as Glacial Lake Agassiz, which covered parts of modern-day Manitoba, Ontario, and Minnesota. This transformation of the landscape created new habitats for plants and animals to colonize. Human communities, always on the lookout for rich resources, gradually moved into these emerging environments. Over time, distinct regional cultures developed, reflected in variations in their stone tool technologies, settlement patterns, and subsistence strategies. In the Great Plains, for example, people pursued bison herds on foot, using drive techniques to funnel animals into traps or over cliff edges. Archaeological sites like head-smashed-in Buffalo Jump in Alberta show how cooperative efforts could result in a significant harvest of meat and hides, which were crucial for survival in a place with extreme temperatures both in winter and summer. Farther east, around the Mississippi River basin, water resources and lush vegetation supported a different way of life. with a broader diet that included fish, shellfish, and various plant foods. The shift from heavily depending on megafauna to a mixed subsistence strategy happened gradually, but became more pronounced as giant mammals vanished. South of the ice sheets, in places like the American Southwest, conditions began to shift toward greater aridity as the Ice Age ended. Lakes that once covered large areas started to dry up, leaving behind salt flats and desert basins. Groups in these regions had to adapt by developing a keen knowledge of desert survival, locating reliable water sources, and exploiting seasonally available plants such as agave or mesquite. Cave sites reveal evidence of dried foods, baskets, and early storage methods that helped people cope with scarce resources. As with Ice Age Europe, North America was not a monolithic environment. While the far north was locked in ice or dominated by tundra, the coasts could support marine-based economies. Early coastal dwellers likely harvested shellfish, fished near shore, and hunted sea mammals where possible. Kelp forests along the Pacific coast might have been a corridor for people traveling by boat, though evidence for that theory is still being pieced together. If small groups moved along the coastline, they would have had a consistent source of food and milder temperatures, allowing them to skirt around large ice masses that blocked interior routes. Over thousands of years, these coastal travelers and interior populations might have interacted or gone their separate ways, adding further layers of complexity to the peopling of North America. One of the standout features of Ice Age North America is the variety of archaeological sites that reveal both the continuity and the change in human lifeways. Sites like Cactus Hill in Virginia or Meadowcroft Rock Shelter in Pennsylvania have yielded artifacts that might predate Clovis culture, sparking debates about exactly when people arrived and how they spread across the continent. Farther west, sites like Paisley Caves in Oregon have produced ancient DNA from coprolites that confirm human presence earlier than once believed. This suggests a longer, more complex timeline of exploration and settlement rather than a single wave of migration. Spiritual or cultural expression in Ice Age North America can be inferred from rock art, burial practices, and the arrangement of artifacts in living sites. Although not as famous as the cave paintings of Europe, petroglyphs and pictographs found across the continent may date back to the late Pleistocene. These images range from abstract symbols to representations of animals like bison or deer. Burials sometimes include grave goods, such as stone tools or beads made from shells, indicating a belief in an afterlife or a concept of individual status. While the specifics of these beliefs remain elusive, they show that Ice Age communities engaged in more than just the raw essentials of survival. Housing and shelter also varied widely. In regions where wood was available, people could construct simple huts or lean-tos. In more open landscapes, they might use animal hides stretched over frameworks made from bones or wooden poles. Some evidence suggests that mammoth bones were used to build substantial structures, similar to finds in Eastern Europe, though these are less common in North America. Caves and rock shelters were utilized when accessible, offering natural insulation and protection. Hearths would be located to provide warmth, and smoke holes or vents allowed for ventilation. Given the bitter cold of certain regions, effective shelter could mean the difference between life and death. By around 8,000 years ago, the transition from the Pleistocene to the Holocene was well underway. Temperatures rose, rainfall patterns changed, and the overall ecology of the continent shifted. Deciduous forests expanded in the eastern parts of North America, while grasslands dominated the center. The megafauna extinctions had reshaped ecosystems, and now deer, elk, and smaller mammals became the primary game animals. Freshwater fish and shellfish were also important food sources, especially in riverine and coastal zones. Over time, new cultural traditions emerged, often characterized by more finely made stone points and an increasing diversity of tools. In some areas, people started practicing rudimentary plant cultivation, laying the groundwork for more intensive agriculture. language and cultural diversity also increased. While there is no direct record of Ice Age languages, modern linguistic distributions and some genetic studies offer hints. The earliest groups may have spoken languages that evolved into the many indigenous language families found today. Over thousands of years, people separated into distinct groups, developing their own identities, belief systems, and ways of life, shaped by the local environments they inhabited. The melting glaciers also opened up corridors of travel, allowing for more interaction, trade, and possibly conflict among different groups. Ice Age North America was not a static place. It was in a constant state of flux as ice sheets advanced or receded, altering everything from river courses to animal migration routes. People responded with resilience and adaptability, inventing and refining tools that allowed them to hunt massive creatures or gather scattered plant resources. They spread across the continent, leaving behind traces of their journeys in stone points, butchered bones, and ancient campsites. While much of the continent's megafauna would not survive the end of the Ice Age, humans continued to adapt, moving into new ecological niches and developing broader diets. This resilience ultimately set the stage for the complex tapestry of indigenous cultures that Europeans encountered millennia later. In reflecting on all of these experiences, one gains an appreciation for the sheer resourcefulness required to navigate the uncertainties of Ice Age North America. The environment varied from frozen tundra in the far north to semi-tropical wetlands in the south, with shifting coastlines and interior plains subject to dramatic changes in rainfall and temperature. People figured out how to extract marrow from mammoth bones, craft needles from antlers, shape fluted spear points from carefully selected stones, and locate seasonal camps that put them within range of migrating herds or ripening wild plants. That ingenuity would continue as the climate warmed, eventually giving rise to new traditions, more permanent settlements, and even the domestication of local plant species. Although much remains a mystery, enough pieces have been uncovered to showcase a vibrant world filled with challenges and opportunities, a place where human determination met the stark realities of an ever-changing Ice Age landscape. During the last major glacial periods, South America experienced a wide range of environmental shifts that left a lasting impact on its landscapes, animal populations, and emerging human societies. The presence of the Andes, a dramatic mountain range that stretches along the western edge of the continent, played a significant role in shaping the climate and habitats available during colder epochs. Glaciers advanced across high-altitude regions, while lower elevations became home to a mosaic of grasslands, woodlands, and forests that were adapted to cooler and often drier conditions. It might be easy to picture South America as a land of rainforests and tropical climates, but during the last Ice Age, conditions were somewhat different. While there was still a variety of habitats, including tropical zones, the overall climate was cooler. In higher elevations and more southerly regions, particularly Patagonia and Tierra del Fuego, extended glaciers and ice sheets covered parts of the landscape. The interplay between mountains, ocean currents, and shifting global temperatures created a patchwork of environments that supported an array of intriguing creatures. Many of these creatures thrived only because of the cooler climates that prevailed during the glacial periods. One of the most iconic animals that roamed Ice Age South America was the giant ground sloth. These creatures were distant relatives of the modern tree sloths that inhabit tropical forests today. However, the ground sloths of the past were vastly larger. Some, like Megatherium, could stand nearly as tall as an elephant and weighed several tons. Their bulk was supported by strong limbs with massive claws used for stripping bark, reaching high branches and digging for tubers. Fossil evidence suggests that these sloths ranged across various environments, from open grasslands to lightly wooded areas, finding food sources in a variety of plants. They likely had few natural predators due to their size and defenses, at least until humans arrived. Another remarkable genus of South American megafauna included the glyptodons. These were enormous relatives of modern armadillos, bearing heavy, dome-shaped shells that offered protection against predators. Some glyptodons were about the size of a small car, with a rigid armored cap on top and a tail that sometimes sported a bony club. Paleontologists suspect that these creatures relied on grass and other vegetation for sustenance, roaming open habitats in search of food. Their thick armor likely dissuaded many carnivores from attempting an attack, but there is some evidence to suggest that early human hunters developed ways to exploit weaknesses in that natural shield. South America was also home to powerful predators during the last ice age. One of the most formidable was the saber-toothed cat, often referred to scientifically as Smilodon populator in South American contexts. While saber-toothed cats were not exclusive to South America, certain species in the region were known to be quite large and specialized in hunting large herbivores. The elongated canine teeth of these cats were not merely showy accessories. They likely played a role in dispatching megafauna quickly, especially in ambush situations. Although these cats thrived in cooler environments, they were not strictly creatures of icy conditions. Instead, their presence overlapped with a wide array of landscapes, from grasslands to forests, all shaped by the broader climate trends of the time. Another noteworthy group of animals that inhabited Ice Age South America included the litopterns, such as Macrauchenia. These odd-looking herbivores resembled something between a camel and a llama, with a short, trunk-like snout that might have assisted in browsing vegetation. Paleontologists continue to debate their exact ecological niche, but it appears that Macrauchenia was adaptable to various environments, including open plains and lightly forested regions. Its limbs suggest that it was capable of moving efficiently over large distances in search of food. As the glaciers advanced in the Andes, they influenced rainfall patterns and contributed to the formation of extensive lakes in some parts of the continent. The high-altitude regions became more challenging for life, as temperatures dropped significantly and vegetation was limited to hardy, cold-resistant plants. Meanwhile, valleys and lower elevations might have acted as refuges for many species, including early humans. The emergence of these refuges could have fostered unique evolutionary paths, allowing certain populations of animals and plants to develop new adaptations isolated from their counterparts in other regions. The arrival of humans in South America is still a subject of debate among archaeologists, with multiple theories pointing to different timing and routes. There are well-established facts suggesting that humans arrived in North America many thousands of years ago, crossing the Bering Land Bridge from Asia. South America would have been reached after these early populations moved through Central America and into the southern regions of the New World. However, there are some archaeological sites, such as those in Monteverde in southern Chile, that hint at an earlier human presence than once believed. Artifacts from Monteverde suggest that people might have been living in the region over 14,000 years ago, which would have placed them in the southern cone of the continent near the tail end of the last ice age. These early groups would have encountered a range of climatic conditions, but the cooler environment of the time presented both challenges and opportunities. On one hand, the presence of glaciers in the Andes and the variable climate might have limited accessible resources in some seasons. On the other hand, herds of megafauna, such as ground sloths and other large herbivores, could have provided abundant food if hunted successfully. The question of whether human hunting played a major role in the extinction of megafauna in South America remains open to interpretation, but many researchers believe that a combination of climate change and human pressure led to the disappearance of many large species. The forging of stone tools, the development of strategies for group hunting, and the ability to adapt to changing environments likely shaped the survival of these early populations. The Pleistocene era, which encompassed the last ice age, was a time of rapid shifts in temperature and precipitation patterns. Groups that settled in certain areas might have taken advantage of resources like freshwater lakes, migratory game, or nutritious plant life. Over time, as the climate warmed toward the end of the Pleistocene, glaciers receded, opening up new land for settlement and ecological expansion. In the southern reaches of South America, known as Patagonia, evidence of glacial activity is visible today in the form of carved valleys and fjords. During the Ice Age, glaciers extended further north than their current positions, and the region's climate was much cooler. Although often portrayed as a harsh environment, it supported herds of herbivores, including relatives of modern guanacos and vicuñas. Predators, including large cats and possibly canids, would have followed these herds. The interplay between predator and prey shaped the evolutionary pathways of many South American lineages. Along the coasts, marine resources may have played an important role in the subsistence of early inhabitants. Shell middens discovered at archaeological sites provide clues about the diet of these groups, which likely included fish, shellfish, and marine mammals, in addition to land-based prey. This adaptability would have been crucial in an era when climate shifts could alter terrestrial food sources. One fascinating element of Ice Age South America is the legacy of species that survived into more recent times. Modern-day llamas, alpacas, and vicuñas are descendants of wild ancestors that managed to endure through changing climates and human interactions. Similarly, smaller armadillos still roam parts of the continent, although their ancient glyptodon relatives are no longer around. These survivors serve as reminders of the once rich tapestry of megafauna that characterized the Pleistocene epoch. The question of how the end of the last ice age impacted South America can be approached by examining changes in vegetation patterns, water availability, and the distribution of fauna. As temperatures rose and glaciers melted, sea levels also rose, possibly isolating some coastal areas and changing routes of migration. Large lakes that formed in glacial basins may have shrunk or disappeared, forcing animal populations and human groups to relocate. Many large mammal species found themselves unable to adapt to the shifting environments or the pressures of human hunting, leading to their extinction. In some parts of the continent, volcanic activity and tectonic movements in the Andes continued to reshape the landscape. This ongoing geological dynamism added another layer to the challenges faced by both animals and humans, who had to navigate not only a changing climate, but also an ever-shifting terrain. Human groups that were resilient and flexible in their strategies might have moved through multiple ecosystems, taking advantage of abundant resources where they could be found. Another intriguing area of study is the diversity of cultures and technologies that developed across South America following the Ice Age. Over millennia, distinct societies emerged, from the highlands of the Andes to the vast lowland river systems, each adapting to local environmental conditions. The shift from nomadic hunting and gathering to more settled agricultural practices likely occurred in response to the stabilizing climate of the Holocene, which followed the last ice age. Domestication of plants like potatoes, quinoa, and maize, which arrived from further north, gradually revolutionized how communities sustained themselves. Throughout the continent, rock art sites depict animals that might have been known to Ice Age peoples, including silhouettes resembling large camelids or even extinct megafauna. These images hint at the cultural significance these creatures held and the intimate knowledge early inhabitants had of their behavior. Remnants of kill sites, where hunters took down large game, have also been uncovered in multiple places. These sites provide insights into group cooperation and the strategies used to exploit the resources available in a dynamic landscape. In recent decades, scientists have refined dating methods such as radiocarbon analysis and have compared stratigraphic layers to glean a more accurate timeline of events. By studying sediment cores from lakes in the Andes, researchers can see how pollen and other organic materials changed over time, revealing shifts in vegetation and climate. This helps paint a clearer picture of how environments evolved from the Ice Age into the present day. Understanding these transitions is crucial for comprehending the broad patterns of extinction and survival that shape the continent. Evidence also suggests that the movement of humans into South America was not a single wave, but rather a series of migrations that spread out over thousands of years. The complexity of these population movements becomes even more apparent when considering genetic data from modern indigenous groups and ancient remains. This research sometimes contradicts earlier assumptions about the simplicity of migration routes. It highlights the intricate tapestry of human history woven into the South American landscape. While many parts of the continent became increasingly hospitable as temperatures rose, certain areas were transformed in ways that reduced the habitats available to cold-adapted species. Steppe-like grasslands in the southern cone may have shrunk, forcing many animals to move or perish. Forests in some areas expanded, altering the composition of local ecosystems. The interplay between these ecological and climatic shifts created new opportunities for certain species to flourish, while others went extinct. One such example of adaptation can be seen in the survival of smaller animals that could find refuge in forests or adapt to broader diets. Rodent species, small deer, and other modest-sized mammals often fare better than megafauna during periods of ecological upheaval. This pattern holds true across continents, as large animals generally require more resources and are more vulnerable to habitat changes. By the close of the last ice age, South America was on a trajectory toward the climatic conditions observed today, yet echoes of that glacial past remain evident in the modern geography, biodiversity, and cultural narratives. The towering Andean peaks still bear glaciers, although these are retreating under current warming trends. Paleontological finds regularly remind scientists of the lost giants that once inhabited the continent. Archaeological discoveries uncover further details about how human societies made the best of the terrain, resources, and climatic conditions they encountered. In examining the Ice Age in South America, it becomes clear how interconnected climate, geography, and living beings truly are. The presence of colossal mountains, the influence of ocean currents like the Humboldt Current off the western coast, and the shifting global climate patterns all played crucial roles in shaping which species thrived and where they lived. Today, researchers continue to piece together the complex story of how this continent transitioned from a land teeming with giant sloths, saber-toothed predators, and thick-shelled glyptodons to the diverse modern tapestry of ecosystems and cultures. More than just a chapter in Earth's natural history, the Ice Age in South America stands as a testament to the adaptability of life in the face of monumental change. By reflecting on what happened to species that did not survive, it is possible to gain perspective on how current and future climate shifts might impact the biological and cultural richness of the continent. Evidence of the past can guide scientific inquiry and cultural awareness, reminding contemporary societies of the importance of maintaining ecological balance and respecting the delicate links between environment and survival. Those who explore the Andean peaks, Patagonian expanses, or Amazonian lowlands might still encounter geological formations and weather patterns that owe their existence to glacial ages long gone. Scientists who sift through fossil beds in Argentina, Chile, or Brazil uncover fragments of a lost world, unveiling new details about creatures that have left their footprints in prehistoric strata. This continual process of discovery ensures that the story of Ice Age South America, while ancient, remains an active field of exploration and research. The transitions of the past offer a lens through which to view contemporary environmental challenges. Though the Pleistocene epoch ended thousands of years ago, its legacy endures in the shape of the terrain and the genetic makeup of surviving species. South America's Ice Age chapter demonstrates that large-scale climate shifts can reorder landscapes and living communities in profound ways. In the end, understanding the Ice Age in South America is not merely about reconstructing a distant epoch, but also about recognizing how the continent's heritage of change, adaptation, and survival still resonates today. Africa is often associated with warm savannas, dense jungles, and expansive deserts, yet it was not immune to the effects of the last Ice Age. Although the continent's tropical and subtropical zones did not see massive ice sheets covering the land as in higher latitudes, climatic changes still altered habitats, reshaped migration patterns, and influenced human evolution. These shifts can be observed in geological records, archaeological sites, and the fossils of animals that roamed the continent tens of thousands of years ago. During the peak of the last glacial period, global temperatures dropped, and enormous ice sheets expanded across parts of the northern hemisphere. Africa did not develop the same kind of continental-scale glaciation, but mountain glaciers appeared in certain high-altitude regions. The most notable examples can be found in eastern Africa, including the peaks of Mount Kilimanjaro and Mount Kenya. Even these mountains did not accumulate the vast layers of ice seen in other parts of the world. Instead, smaller ice caps and glaciers formed near their summits, testifying to the cooler climate that prevailed. Over time, these glaciers have mostly retreated, but evidence of their former extent can be found in the shapes of mountain valleys and deposits of glacial sediment. Beyond the high mountains, the reduced temperatures had ripple effects on rainfall and vegetation patterns. When global climates cooled, the distribution of monsoon systems and atmospheric circulation patterns over Africa shifted. Some regions became more arid, while others experienced slightly more favorable rainfall conditions. Over the millennia, these fluctuations in moisture availability shaped the expansion and contraction of deserts, grasslands, and forested areas. The Sahara, for example, underwent repeated cycles of greening and drying during the Pleistocene. At times, it was lush, supporting lakes, rivers, and abundant wildlife, while at other periods, it expanded to become a hyper-arid barrier. The animals that inhabited Africa during the last ice age included many that are familiar to modern observers, such as various species of antelopes, zebras, elephants, and lions. However, some of these animals looked a bit different in the past, with certain populations developing physical traits suited to cooler or drier conditions. The elephant populations might have been smaller or larger depending on resource availability. Lions could have formed expansive prides that roamed across regions that are now heavily desertified. Alongside these familiar species, there were also extinct forms of megafauna, including giant buffalo and unique forms of hippos and rhinos adapted to varying degrees of wetness or dryness. One of the most striking aspects of Ice Age Africa is that it continued to be a major center for human evolution. Long before the last glacial maximum, early hominins had already emerged on the continent. By the time of the last Ice Age, anatomically modern humans, Homo sapiens, had spread throughout much of Africa. These populations were extremely diverse in their cultures, tools, and survival strategies. Archaeological sites reveal that, in some places, communities thrived near resource-rich coasts or along large river systems. The shifting rainfall patterns might have forced these groups to adapt continuously, seeking reliable water sources and game animals. In regions such as East Africa, the cooler, drier climate of the Ice Age may have opened up new corridors for human migration. Grasslands could have expanded, offering easier passage across areas that are now covered in dense vegetation or are heavily populated. Alternatively, arid phases may have blocked certain routes, influencing the flow of populations across the continent. The interplay between environmental constraints and human adaptability helped shape the genetic and cultural diversity of African populations. Some groups may have retreated to refuges with more stable climates, such as the Ethiopian highlands or coastal regions, while others might have adapted to more arid conditions. The genetic evidence suggests that multiple lineages of modern humans survived in various pockets of Africa during glacial periods, later merging as the climate improved. This process helped create the remarkable genetic diversity observed among present-day African populations. Archaeological records also indicate that technological innovations did not occur in a simple linear fashion. Instead, different regions saw the emergence of new tool types, subsistence strategies, and symbolic behaviors in response to local environmental pressures. Because Africa did not experience the same large-scale ice sheets as Eurasia or North America, many species of megafauna managed to persist through the Pleistocene and into modern times. Elephants, giraffes, and rhinoceroses continue to roam the continent. Nonetheless, there were still extinctions. Some species of giant buffalo, large carnivores, and other specialized animals vanished, presumably due to a combination of environmental shifts and human hunting pressure. These extinctions were less catastrophic than those seen in other continents, possibly because African fauna had co-evolved with hominins over millions of years. Having faced human predators for a much longer time, African wildlife might have been better adapted to evade or cope with hunting strategies. The Sahara Desert, today one of the most formidable deserts on Earth, provides an intriguing case study in how the Ice Age climate shaped Africa. Although it may seem counterintuitive, some intervals during the last glacial cycle were more humid in North Africa, partially due to shifts in the intertropical convergence zone and changes in sea surface temperatures. During these wetter phases, what is now desert was transformed into savanna or grassland, dotted with lakes and rivers. Animals like crocodiles, hippos, and various fish species lived in waters where today only sand dunes dominate the landscape. Rock art found in the Sahara reflects periods when wildlife abounded in the region. Depictions of giraffes, elephants, and even cattle suggest that people thrived in these areas when the climate allowed for sufficient rainfall. As glacial conditions retreated and global temperatures rose, rainfall patterns shifted again, leading to the expansion of arid conditions and forcing human groups to move elsewhere. This cyclical process repeated multiple times, leaving a complex archaeological record scattered across the desert. Further south, the Congo Basin maintained its tropical rainforest ecosystem, though expansions and contractions of the forest margins occurred due to changes in rainfall. In some cooler and drier intervals, grassland corridors may have penetrated the forest, facilitating the movement of species and people across areas that are now heavily forested. This could explain certain shared cultural or genetic elements found in communities that seem geographically isolated today. By understanding how these corridors formed and disappeared, researchers can piece together a mosaic of ancient migration patterns within Africa. The southern parts of the continent, including what is now South Africa, also experienced significant changes during the last ice age. Coastal areas might have been exposed when sea levels were lower, creating environments that are now submerged. Evidence from submerged cave systems and coastal terraces suggests that Pleistocene humans occupied areas that would be underwater today. These sites likely provided rich marine resources such as shellfish, fish, and marine mammals, which supplemented land-based diets. Meanwhile, in the interior, large herds of grazers roamed the grasslands, and the cooler climate may have made some regions more hospitable for certain species than they are in the modern era. In the highlands of Ethiopia and other elevated regions, cooler conditions may have resembled a more temperate climate, enabling unique plants and animals to flourish. These areas may have served as refuges not only for humans, but also for various species during times of environmental stress. Some researchers propose that these highlands were critical for sustaining certain lineages of modern humans who later dispersed across the continent once the climate warmed. The relationship between humans and the environment in Ice Age Africa was complex. Rather than simply migrating in response to each climatic shift, human populations may have developed flexible strategies that allowed them to remain in certain regions even under challenging conditions. The development of more sophisticated stone tools, the use of fire for managing landscapes, and social networks that facilitated trade or exchange of resources could have all played roles in human resilience. The concept of niche construction, where humans actively alter their environments, can be applied to these periods. By using controlled burning to manage vegetation, for instance, groups might have maintained favorable habitats for game animals, thereby increasing hunting success. Fossil evidence of human remains, as well as animal bones bearing cut marks, points to the significance of hunting in Ice Age Africa. But for many communities, gathering plant-based foods was just as important. In regions with reliable rainfall or near perennial water sources, wild grains, tubers, and fruits formed a major part of the diet. Knowledge of how to process and store these foods would have been key, especially during periods when large game was scarce. Some scholars argue that the relative stability of African ecosystems compared to the extreme glacial conditions in Eurasia allowed Homo sapiens more time to develop and refine cultural and technological practices on their home continent. The roots of symbolic behavior, such as art and ritual, can be traced back to sites in Africa that predate similar phenomena elsewhere. The interplay between changing environments and cultural innovation is apparent in the archaeological record, demonstrating that communities found ways to incorporate new methods of tool-making, personal adornment, and possibly even early forms of spiritual expression. As the last ice age gave way to the Holocene, many parts of Africa experienced increased rainfall and higher temperatures. Forested areas expanded, savannas shifted, and some deserts contracted. This transition allowed human populations to grow and spread into regions that had been too dry or harsh during colder periods. It also set the stage for the development of agriculture in parts of Africa, though that process took place at different times depending on local conditions. The domestication of plants like sorghum, millet, and yams, as well as the management of livestock, led to a more sedentary lifestyle in various parts of the continent. Over time, this shifted the dynamic between humans and the environment, creating a feedback loop where deliberate cultivation further altered landscapes. Yet the influence of the Ice Age did not entirely fade. Glacial legacies can still be seen in the genetic markers of African populations, the distribution of certain animal species, and the geological formations of high mountains. In addition, the cyclical patterns of wet and dry phases in regions like the Sahara continued into the Holocene, occasionally turning grasslands back into deserts and forcing new migration patterns. Understanding these historical cycles is crucial for comprehending modern-day challenges, such as desertification and water scarcity, which remain pressing issues in many African countries. One intriguing case study is the Nile River, a lifeline that has supported human civilization for thousands of years. During the last Ice Age, changes in rainfall in the Ethiopian highlands and surrounding areas affected the flow of the Nile. Periods of reduced precipitation likely meant lower water levels, influencing ecosystems along the river's length. Early human settlements would have been closely tied to these fluctuations, as the Nile provided both a reliable source of water and access to fertile floodplains. Over time, as the climate warmed and rainfall patterns became more conducive, the foundation was set for the rise of more complex societies along the riverbanks. Marine records off the coast of Africa also provide clues about Ice Age climates. By examining deep-sea sediment cores, researchers can detect changes in wind-borne dust, which often originated from the Sahara or other arid regions. When dust levels were higher in these cores, it suggests that the continent was experiencing dry and windy conditions. These findings correlate with data from terrestrial sites and help form a clearer picture of how regional and global climate systems interacted. Africa's role as the cradle of humanity is well known, but the continent's Ice Age story is often overshadowed by more dramatic images of northern ice sheets and glacial landscapes. Nonetheless, Africa's experience of the Pleistocene was unique in that it preserved a rich diversity of wildlife and sustained multiple human populations. This continuity provided an evolutionary and cultural laboratory where adaptability was key. While other parts of the world saw many large mammals go extinct soon after humans arrived, Africa maintained more of its megafauna because those animals had long been coexisting with hominins. That ongoing coexistence reduced the likelihood of massive, sudden die-offs, though it did not eliminate extinctions entirely. Exploring Ice Age Africa is a reminder that climate change does not always manifest as blankets of ice spreading across the land. Instead, it can involve shifts in rainfall, temperature, and vegetation that reshape the mosaic of habitats. These changes can be gradual or abrupt, and they force living beings to adjust their distributions and behaviors. In Africa's case, these climatic swings influenced the emergence of modern humans, shaped their evolutionary path, and guided the movements of animals across savannas, forests, and deserts. Modern research continues to uncover new details about Ice Age Africa through fields like paleogenetics, paleoecology, and archaeology. Ancient DNA extracted from bones or teeth can show how animal populations expanded or contracted, suggesting times of environmental stress or plenty. Plant remains preserved in sediments reveal which species existed in different areas and how their distributions changed. Stone tools found in cave sites can be dated and analyzed to see how technology evolved in response to shifting conditions. In the end, Africa's Ice Age story is one of resilience and transformation. While glaciers did not dominate the continent, the cooler global climate and associated shifts in rainfall had a profound impact on ecosystems and on the early human groups that called Africa home. The adaptation strategies developed in this era laid the groundwork for the cultural and genetic richness that defines the continent today. People learned to find water sources in arid times, track migrations of game animals, and cultivate plants when conditions allowed. Many species found ways to persist through difficult periods, and those that could not adapt eventually disappeared. This story of survival and change is essential for understanding both the past and future of a continent that remains incredibly diverse in its landscapes, wildlife, and human communities. Asia is the largest and most diverse continent on Earth, with a vast range of environments that spanned everything from Arctic tundra in the north to tropical forests in the south during the last ice age. Across this monumental landmass, climatic shifts influenced the habitats, megafauna, and early human populations that dispersed in search of favorable resources. One of the most fascinating chapters of this period is the migration of humans from Asia into the Americas, commonly believed to have occurred via the Bering Land Bridge when sea levels were significantly lower. Exploring the Ice Age in Asia and the paths that led to the New World offers insights into how environmental changes, animal movements, and human ingenuity came together in an extraordinary episode of prehistory. During the peak of the last glacial maximum, enormous ice sheets covered northern parts of Eurasia. In what is now Siberia, temperatures dropped well below freezing for much of the year, creating a landscape dominated by tundra and steppe. Mammoth Steppe, as it is sometimes called, featured hardy grasses and low-lying vegetation capable of withstanding severe cold and limited precipitation. This environment was home to iconic megafauna such as woolly mammoths, woolly rhinos, steppe bison, and musk oxen. These animals were adapted to the harsh climate with thick fur, layers of fat, and specialized grazing habits. They roamed across vast distances, following the seasonal availability of pasture. Not all of Asia was locked in ice or permafrost conditions. Further south, the climate varied significantly by region. Deserts like the Gobi in Mongolia expanded or contracted based on shifting precipitation patterns. Forested areas in East Asia may have been cooler and drier, leading to changes in the distribution of species. In Southeast Asia, sea levels fell, exposing land areas that are now underwater, including regions of what is known as Sunderland. The islands of Indonesia and Malaysia were more connected than they are today, facilitating the movement of animals and humans. Meanwhile, portions of the Himalayas and the Tibetan Plateau would have had glaciers and ice caps at high elevations, although not on the same scale as northern ice sheets. Human populations in Ice Age Asia were as varied as the environments they inhabited. Different groups developed their own cultural and technological solutions to the challenges posed by glacial conditions. In some areas, stone tool traditions reflect a focus on hunting large steppe animals, while in others, evidence suggests a diet supplemented by fishing or gathering plant resources. Caves and rock shelters in parts of China, Central Asia, and the Altai region preserve artifacts and sometimes even human remains that help archaeologists piece together migration routes and survival strategies. Genetic studies indicate that multiple waves of human expansion took place across Asia, eventually reaching places as far as Japan in the east and the Indian subcontinent in the south. One of the defining features of the last ice age was lower global sea levels. Large amounts of water were locked in glaciers, meaning that ocean shorelines were exposed in many areas. The Bering Strait, which currently separates Siberia in Russia from Alaska in the United States, was transformed into a broad land bridge known as Beringia. This region was not solely a narrow passage, but rather a wide stretch of steppe or tundra that supported populations of megafauna and eventually human travelers. The exact timing of human migration into the Americas remains debated among researchers, but it likely happened sometime before 15,000 years ago, possibly earlier, as new discoveries keep pushing the date back. Beringia's role was critical because it provided a relatively accessible route for people and animals to move between Asia and North America. However, crossing Beringia was not necessarily easy. Harsh climatic conditions, shifting resources, and glacial barriers in North America itself could have complicated the journey. Some theories suggest that a corridor opened between the massive Laurentide and Cordilleran ice sheets in North America, allowing southern movement once travelers crossed into Alaska. Other models propose a coastal route along the Pacific Rim, where people might have used boats to navigate between islands and ice-free shorelines. Regardless of the path, the first humans in the Americas almost certainly had Asian origins, tied to the populations that spread across Siberia during the Ice Age. The presence of woolly mammoths in Siberia is emblematic of Ice Age Asia. Mammoth bones and tusks have been found in large quantities, often showing evidence of butchery and human use. Some sites indicate that early hunters relied heavily on mammoths for food, shelter, using bones to construct frameworks for huts, and tools, fashioning needles or other implements from bone and ivory. The mammoth steppe extended across much of northern Asia, offering these nomadic groups a reliable source of protein if they had the skills to hunt such formidable creatures. Over time, climate change and human hunting pressure contributed to the decline of mammoth populations, with the last known dwarf populations persisting on remote Arctic islands thousands of years after they disappeared from mainland Asia. Another fascinating creature that lived in Ice Age Asia was the woolly rhinoceros. Fossil remains of these cold-adapted rhinos have been discovered in Siberia, China, and parts of Central Asia. Their thick coats and robust bodies help them survive in periglacial conditions, browsing on hardy vegetation found in steppe and tundra settings. Like mammoths, they eventually vanished, with various theories pointing to a combination of warming climates and human hunting as factors in their demise. Large predators, including cave lions and perhaps scimitar cats, roamed these frigid landscapes in pursuit of prey. The interplay between predator and prey was a delicate balance that shifted as temperatures fluctuated and humans entered the scene. In more temperate parts of Asia, animals like elephants, rhinoceroses, and tigers coexisted with humans during the Pleistocene. However, populations of these large animals likely moved or changed their ranges in response to cooling temperatures and altered vegetation. Fossils of extinct or now rare species found in areas where they do not occur today suggest how much the environment shifted from one phase of the Ice Age to another. The diversity of habitats in Asia, from the temperate forests of eastern China to the tropical jungles of Southeast Asia, created various refuges where species could survive in pockets, even if broader conditions were unfavorable. Archaeological sites across Asia shed light on how humans adapted to these varying conditions. In the Altai Mountains of southern Siberia, Denisova Cave has yielded remains and artifacts tied to both Neanderthals and Denisovans, two archaic human groups that overlapped with modern humans in some regions. Genetic evidence points to interbreeding events that left traces in the genomes of modern populations in Asia and Oceania. By the time of the last glacial maximum, modern humans were likely the dominant human group, but earlier hominins had contributed to the genetic tapestry. This mixture of lineages underlines how dynamic human evolution and movement were during the Ice Age. Across Central Asia, findings suggest that horse and camel species roamed the steppes. Humans may have hunted these animals or followed them along migratory routes. The ability to track herds, store food, and maintain group cohesion would have been essential in harsh climates. Tool assemblages often feature scrapers, blades, and sometimes specialized projectile points, indicating a focus on mobile hunting strategies. Campsites might have been established near rivers or other water sources, with some evidence of seasonal movement following the availability of game and plant resources. As conditions gradually warmed toward the end of the Ice Age, sea levels began to rise, submerging land bridges like Beringia and cutting off direct overland routes between Asia and North America. Populations that had already migrated into the Americas would have found themselves increasingly isolated from their Asian counterparts. Simultaneously, parts of Asia saw the retreat of glaciers and an expansion of forested zones. Rivers swelled with meltwater, creating fertile valleys that supported the development of agriculture in the millennia to come. In regions like China and the Fertile Crescent, though the latter is typically associated with West Asia, the domestication of plants and animals eventually led to permanent settlements, farming societies, and more complex forms of social organization. The window of migration into the Americas, therefore, intersected with a pivotal climatic transition. Humans who arrived in the New World might have carried traditions and tool forms from their Asian homelands, adapting them to new environments in Alaska, the Yukon, and beyond. Over generations, they spread across the Western Hemisphere, giving rise to a wide array of cultures and societies. The Clovis culture, once believed to be the earliest in North America, is linked to distinctive spear points that some have tried to trace back to possible Asian influences. However, newer discoveries suggest multiple migration waves and cultural variations that complicate the once linear narrative of a single migration event. In Siberia, the harsh climate began to ease after the coldest phase of the glacial maximum, but life in the region remained challenging. For thousands of years, people continued to live by hunting animals like reindeer and fishing in rivers and lakes that were seasonally or permanently cold. The cultural adaptations required for survival in these environments were substantial. Warm clothing made from animal skins, shelter designs that retained heat, and a deep understanding of animal behavior were essential skills. Over time, as the climate grew milder, populations expanded northward, only to be constrained again by the onset of the next cold phase. This cyclical pattern repeated itself throughout the Pleistocene. In East Asia, particularly in what is now China, the impacts of the Ice Age varied by region. The northern plains experienced cooler, drier conditions, influencing the distribution of grasslands and forests. Southern areas retained more temperate or subtropical habitats, allowing a variety of species to persist. Some archaeological sites show evidence of early rice gathering or experimentation with plant cultivation even before the end of the Pleistocene. These early steps toward domestication would lay the groundwork for later agricultural revolutions that transformed societies and led to population booms. The role of Asia in the grand narrative of human migration during the Ice Age is central, not only because of the routes that led to the Americas, but also because of the continent's tremendous geographic expanse and diversity. Environmental shifts on such a large scale forced repeated adaptations, cultural innovations, and population movements. Each time the climate swung from cold to relatively milder conditions, animals and humans redistributed themselves, taking advantage of newly available resources or fleeing inhospitable regions. Over countless generations, these movements interlinked populations, allowing genetic and cultural exchanges that shaped the human species. When examining the migration into the Americas, it is crucial to note that the Bering Land Bridge was not always open. Sea levels rose and fell in tandem with glacial cycles. During colder periods, more water was trapped in ice caps, lowering sea levels and revealing land connections. During warmer intervals, those pathways disappeared underwater. Understanding the timing of these events is key to piecing together the puzzle of how and when people first set foot in the Western Hemisphere. Archaeological discoveries in Siberia or Alaska that date to tens of thousands of years ago can shift assumptions about the earliest possible crossing date. Similarly, new finds in North or South America can reveal evidence of human presence earlier than previously recognized, spurring debates about alternative migration theories. Another intriguing aspect of Ice Age Asia involves the so-called Silk Road regions, though they were not called by that name at the time. Areas that later became pivotal trade routes between East and West have a rich prehistoric legacy. Mountain passes in regions like the Pamirs or the Tian Shan might have served as corridors for migrating animals and people. Even in prehistoric times, certain valleys and passes might have functioned as cultural crossroads where different populations interacted, exchanging tool-making techniques and genetic lineages. The movement across these rugged terrains would have been influenced by glacial conditions, as heavy snowfall and advancing ice could block passages. Artifacts discovered along these ancient routes hint at long-distance connections. Pigments, shells, or stone types that originated hundreds of miles away raise the possibility that early humans had complex social networks even during glacial periods. Whether these networks spanned just a few communities or large territories is harder to discern, but the presence of exotic materials indicates that trade or exchange occurred. This capacity for collaboration and communication across distances may have been one of the reasons Homo sapiens ultimately flourished compared to other hominin species. In Southeast Asia, lowered sea levels connected islands and created extensive landmasses. Animals and humans migrated across these expanded territories, leading to a mingling of species and cultures. Fossil remains of early humans and extinct megafauna on islands like Java and Flores give clues about how populations adapted to changing coastlines and ecosystems. Studies of stalagmites in caves help researchers reconstruct past rainfall patterns, revealing how shifts in the monsoon might have alternately facilitated or hindered movement in the region. Although most of Southeast Asia was never glaciated in a strict sense, cooler global temperatures still impacted plant and animal distributions, altering the resources available to human populations. By the close of the last ice age, Asia was on the verge of enormous cultural transformations. As the climate grew warmer, forests expanded in some areas, rainfall patterns changed, and sea levels began to rise, cutting off land bridges like Beringia and portions of Sundaland. Isolated by these rising seas, some populations turned to innovations such as seafaring to maintain connections or discover new lands. Elsewhere, improved climatic conditions allowed for the domestication of wild plant species, setting humanity on a path toward agricultural societies. Within a few thousand years, the foundations of some of the earliest civilizations would take shape along the great rivers of Asia. Throughout this period, the migration to the Americas remained one of the defining achievements of Ice Age populations, reshaping the globe's demographic map. From Siberia's steppe to Alaskan tundra and beyond, the crossing left a legacy that can still be traced in the genetics of indigenous peoples throughout the Americas. Studies of linguistic patterns, cultural artifacts, and oral traditions further enrich the story, although piecing everything together can be challenging. Scientists rely on radiocarbon dating, paleogenomics, stratigraphic analysis, and comparisons with other global data to refine timelines and understand how these prehistoric journeys occurred. In total, the Ice Age in Asia was more than just a cold spell. It was a complex tapestry of climatic zones, wildlife distributions, and human exploration, culminating in one of the greatest migrations in history. The varied landscapes, from permafrost-laden Siberia to the sunken plains of Southeast Asia, provided myriad challenges and opportunities. Humans responded with a remarkable repertoire of adaptations, venturing out in small bands that would eventually populate entire continents. Over time, the retreat of the ice reshaped shorelines, sealed off old routes, and opened new possibilities, setting the stage for the next chapters of human civilization and expansion. By the dawn of the Holocene, Asia had transformed once again, standing ready for the agricultural and cultural developments that would define the ages to come. Australia during the Ice Age was a place of dramatic changes that shaped the continent's landscapes, ecosystems, and the movement of its early peoples. In those days, sea levels were much lower than they are now, and that meant the landmass of what is now Australia was connected to other regions like New Guinea and Tasmania. Scientists often refer to the combined landmass of Australia and New Guinea as Sahul. This merging of land meant that animals and humans could move across areas that are now separated by oceans. The climate in Ice Age Australia was generally colder and drier, although certain regions varied. The central parts of the continent became more arid than before, with desert-like conditions spreading more widely. In the north, the climate was relatively more hospitable, offering regions of tropical and semi-tropical environments. These differences in local climate and terrain influenced which parts of the land were densely inhabited and which places were less occupied. Archaeological findings suggest that the early inhabitants of Australia adapted to these conditions through a combination of hunting, gathering, and the use of portable shelters. In the colder periods, glaciers were present in the highlands of southeastern Australia, notably in regions like the Kosciuszko area, but these glaciers were never as extensive as those found in parts of Europe or North America. The continent's position closer to the equator meant that Australia did not transform into a land fully covered by ice, but there were nonetheless significant temperature drops that affected rainfall patterns and vegetation. In the drier interior, lakes and rivers that once supported abundant life shrank or disappeared altogether. This meant that animals and people had to either migrate to better watered areas or find ways to endure harsh environments. Ancient lake beds, such as those found in parts of southern Australia, reveal traces of human occupation around what were once thriving bodies of water. Over centuries, as climates shifted and water resources dwindled, many of these regions were abandoned for greener, more reliable habitats. Australia's megafauna thrived before and during parts of the Ice Age. The continent hosted a fascinating assortment of giant creatures, including large marsupials and reptiles that have since become extinct. One remarkable example was Diprotodon, which resembled a massive wombat and weighed more than a small car. There were also giant kangaroos that stood taller than a person and huge flightless birds sometimes called mihirungs. While some of these creatures may have handled cooler climates, the increasingly dry environment and changes in plant life likely put pressure on their populations. Human activity may have also played a role in the decline of these larger species, as hunting combined with habitat changes can drastically affect the survival of animal populations. Fossils and archaeological evidence point to a period of overlap between humans and megafauna in Australia, suggesting that both factors, human impact and climatic shifts, contributed to the eventual disappearance of these remarkable beasts. The Aboriginal peoples who lived in Australia during the Ice Age were resourceful and adaptable. Although evidence of their early cultural practices is fragmentary, it is clear they developed methods for survival that responded to changing temperatures and rainfall. Oral traditions passed down through generations provide glimpses into a deep, continuous occupation of the continent that stretches back tens of thousands of years. Communities are believed to have utilized fire stick farming, controlled burning of vegetation, to encourage new plant growth, promote the presence of certain animal species, and reduce the intensity of uncontrolled wildfires. This relationship with the land formed the basis of a sustainable lifestyle that persisted through major environmental fluctuations. Rock shelters and caves often served as places of refuge and art production, where people created hand stencils and paintings that can still be found on rock walls. These art sites provide valuable insight into life during periods when the land was less forgiving. Another striking feature of Ice Age Australia was the presence of the land bridge between what is now Australia and Papua New Guinea. This bridge was made possible by dramatically lowered sea levels, which exposed continental shelves that are currently underwater. During times of more extreme cold, glacial ice locked up vast amounts of the planet's water, reducing global sea levels. As a result, the distance between Australia and Southeast Asia decreased, though deep ocean waters still presented a formidable barrier to migration. Humans are believed to have arrived in the continent by using simple watercraft to make necessary crossings, although the exact routes and timing of these journeys are still researched by archaeologists. Once settled, populations spread out across the varied landscapes, adapting to arid deserts, lush tropical zones, and temperate forests. The resulting diversity of Aboriginal groups, languages, and cultural practices reflects the multitude of environments they encountered. With the drier climate came changes in vegetation. Large swathes of grassland and woodland became more expansive in some areas, while lush forests retreated in others. This transformation likely influenced hunting and gathering practices, as certain animals moved to follow the availability of water and plants. Rivers and coastal regions supported more stable communities because they offered year-round food resources like fish, shellfish, and other marine life. Inland, survival depended heavily on knowledge of how to find waterholes, edible plants, and game. Scarcity of water would have prompted seasonal or even more frequent movements. Archaeologists have used sediment cores from ancient lake beds to reconstruct how vegetation changed over time, showing a decline in forest species and an increase in more drought-resistant plants, particularly during the peak of glacial conditions. This shift, while challenging, did not prevent human habitation, but rather shaped it in innovative ways. Another important factor in Ice Age Australia was the unique adaptations of local wildlife beyond the megafauna. Smaller marsupials and reptiles found ecological niches that allowed them to survive through periods of dryness. Some burrowing animals, for example, could escape daytime heat by sheltering underground. Birds that migrated seasonally could avoid the harshest conditions by following the shifting availability of food. In more temperate zones and the tropics of northern Australia, environments were not as severely impacted by cold as in higher latitudes. That allowed some regions to act as refuges, where both animals and humans could persist during the worst glacial conditions before spreading out again during warmer intervals. These pockets of relative stability served as genetic reservoirs for multiple species, ensuring that they would repopulate the continent after the climate improved. When considering how communities might have communicated or traded during the Ice Age in Australia, researchers often point to evidence of trade networks that spanned considerable distances. Materials like ochre, used for art and ceremonial purposes, have been found far from their points of origin, implying that people traveled or traded across hundreds of miles. While long-distance travel could be dangerous in a harsh, arid environment, groups likely formed alliances that allowed for shared resources. This not only aided in survival, but also allowed cultural ideas and practices to spread. Rock art sites sometimes feature similar motifs, even when found far apart, suggesting that there was a sense of connection and exchange among different groups. Questions remain about the timeline of human arrival and the role people played in environmental and ecological shifts during the Ice Age. Some theories propose that humans reached Australia as early as 50,000 years ago, or even earlier, while others place the date somewhat later. Either way, their presence coincided with a series of climatic events that included cooler phases, mild interludes, and shifts in rainfall. Some scientists suggest that repeated burning of landscapes might have influenced the types of vegetation that dominated, potentially making the environment less suited for large herbivores. Others point out that these animals had survived earlier climatic changes and that the added strain of hunting may have pushed certain species over the brink. The debate continues, and ongoing studies aim to shed more light on these complex interactions. Over time, as the global climate began to warm and the last major glacial period waned, sea levels rose once again. Low-lying coastal plains were gradually submerged, cutting off Tasmania and New Guinea from mainland Australia. The people living in these areas adapted to these changes by shifting their settlements and finding new resources. The once continuous populations were separated by rising seas, leading to regional differences in culture and language over thousands of years. The end of the Ice Age did not happen overnight. Rather, it was a gradual process with fluctuating temperatures and sea levels, but eventually, Australia reached a state more akin to modern conditions. This resulted in the distribution of flora and fauna that is more recognizable today, although still different from what existed before the last major warming trend. Australia's Ice Age story underlines the resilience of life in the face of environmental extremes. Even though it was never fully covered by ice sheets, the climate swings and lower sea levels profoundly shaped its ecology and the patterns of its earliest human inhabitants. The geological and archaeological evidence left behind provides a window into a time when giant marsupials roamed the land, deserts expanded and contracted with the climate, and Aboriginal societies innovated to thrive under challenging conditions. Each piece of data gleaned from ancient bones, pollen samples, or rock art adds another layer of understanding to how this continent changed during the glacial epochs. It also offers insight into how communities can adapt to environmental pressures. By examining the past, researchers get a glimpse of the resilience and adaptability that have long characterized human experiences in this unique land. Eventually, as the last major ice age drew to a close, transformations that had begun quietly over centuries became more pronounced. The rising temperatures facilitated the growth of forests in regions that had previously been too dry or cold. Glacial areas in southeastern Australia melted, contributing to changes in river systems and regional ecosystems. Coastal regions expanded their influence on human settlement as resources like fish and shellfish became more abundant. The stories passed down through generations of Aboriginal peoples echo these major shifts. Some oral traditions mention flooding events or the separation of land masses, which align with scientific reconstructions of sea level rise. These cultural memories serve as a testament to the deep connection between people and the evolving landscapes of Ice Age Australia. Australia's Ice Age legacy is still visible in certain landscapes today. Ancient lake beds, rocky outcrops with layered rock art, and the remains of megafauna are tangible reminders that the continent once had a markedly different face. While much has changed, the lessons learned from studying this period underscore the importance of adaptability and respect for environmental limits. The complexity of Australia's past climate, combined with the enduring presence of its indigenous communities, highlights how cultural knowledge and ecological understanding are intertwined. Researchers continue to uncover details about this era, piecing together clues that explain how both humans and animals survived in a place that was subject to extreme temperature shifts and widespread dryness. This deeper context enriches modern appreciation of Australia, shedding light on the resilience of life in a land that has always known how to adapt to change. Australia during the Ice Age was not a static environment locked in perpetual cold. It was a dynamic place, influenced by global climate systems, yet shaped by local factors such as geography, ocean currents, and prevailing winds. Rainfall patterns shifted across centuries, forcing communities to move or develop new strategies for food and water. The flora and fauna evolved and, in many cases, vanished, leaving behind skeletal remains and footprints in hardened mud. The movement of humans across the continent and into neighboring areas reshaped population distributions. Eventually, as the ice receded and sea levels rose, the modern outline of Australia began to emerge, with the continental islands returning to their isolated forms. This narrative of transformation is a vital chapter in Earth's story, reminding us that change is a constant and that survival often depends on adaptation and knowledge passed down through generations. Ice Age climate patterns were shaped by a complex interplay of factors that governed temperature, precipitation, and atmospheric conditions across vast regions of the planet. The period most people refer to when talking about the Ice Age is the Pleistocene, which lasted from about 2.5 million years ago until roughly 12,000 years ago. However, Earth's history includes multiple glacial and interglacial cycles within that span. These cycles were driven largely by shifts in Earth's orbital characteristics, known as Milankovitch cycles. The angle of Earth's tilt, the shape of its orbit around the Sun, and the wobble of Earth's axis all influenced how much solar radiation reached different latitudes. During times of reduced solar radiation in the northern latitudes, massive ice sheets grew and advanced, especially across North America and Eurasia. During intervals of increased solar radiation, these ice sheets retreated, leading to warmer temperatures and changing sea levels. One hallmark of Ice Age climate patterns was the expansion and contraction of glaciers. When temperatures dropped, snow accumulated over centuries, compressing into ice layers that built up into gigantic glaciers. These glaciers covered substantial portions of the northern continents, scouring the land beneath them and forming geological features like moraines and glacial valleys. In the southern hemisphere, regions like Patagonia in South America and parts of New Zealand also experienced glaciation. The shifting boundary of ice had a ripple effect on global weather patterns, as the white surface of ice reflected more solar energy back into space, reinforcing cooling trends. Conversely, when the climate warmed, melting ice introduced large amounts of fresh water into the oceans, affecting ocean currents and, by extension, climate systems around the globe. Shifts in atmospheric composition also played a key role. During colder periods, the oceans absorbed more carbon dioxide, and ice sheets locked away moisture, leading to lower sea levels and altered wind patterns. The cold, dry conditions often created vast dust storms, as uncovered land surfaces were more prone to erosion. Dust carried by the wind could travel thousands of miles, depositing layers of silt in faraway regions. In parts of Asia, thick deposits known as loess plains accumulated, supporting fertile agricultural lands in later epochs. This dust in the atmosphere sometimes affected how much sunlight reached the surface, contributing another feedback loop in climate dynamics. Monsoon patterns were also different during the Ice Age. In regions like Africa and South Asia, rainfall depended heavily on seasonal shifts in wind direction and ocean temperature. During glacial periods, the intensity of monsoons decreased in some places, leading to more arid conditions that forced vegetation and wildlife to adapt or migrate. In contrast, certain areas in the tropics experienced heavier rains, creating refuges for species that could not survive in the cooler, drier surrounding zones. This uneven distribution of rainfall contributed to patchwork habitats that shaped the evolution and distribution of plants and animals. Rivers and lakes changed their size and location in response to shifting precipitation, leaving behind geological evidence of shoreline terraces and ancient water channels. Ocean currents formed another major factor in Ice Age climate patterns. As glaciers melted or expanded, the density and salinity of ocean water changed, altering major oceanic conveyor belts like the Atlantic meridional overturning circulation. This circulation system, sometimes referred to as the Gulf Stream, transported heat from equatorial regions toward higher latitudes. During cold periods, disruptions in the balance of fresh and salty water in the North Atlantic could slow or divert this heat transport, causing more intense cooling in the northern hemisphere. The interplay between ocean currents and ice sheet dynamics often resulted in abrupt climate swings, such as the Dansgaard-Oeschger events identified in Greenland ice cores. These events saw rapid shifts in temperature over a few decades, indicating that Ice Age climates were anything but stable. Instead, they went through episodes of sudden warming or cooling that would have significantly impacted ecosystems. Another factor in the global climate during the Ice Age was the configuration of the continents themselves. Throughout Earth's history, the movement of tectonic plates has rearranged land masses, opening and closing ocean gateways. By the time of the most recent glacial cycles, the continents were in positions that allowed for extensive ice buildup in the northern hemisphere. Mountain ranges like the Rockies, the Alps, and the Himalayas not only were affected by glaciation, but also influenced atmospheric flow. Air masses traveling across these high terrains could be lifted and cooled, leading to heavier snowfall in some regions. The rain shadow effect also created areas of extreme dryness downwind of the mountains, contributing to desert expansion in certain locations. This topographical influence meant that Ice Age climate patterns were not uniform. Local geography often determined how severely a place felt the cold or dryness. Ice cores extracted from Greenland and Antarctica have been vital in reconstructing these intricate climate patterns. Scientists look at the ratio of different oxygen isotopes to estimate past temperatures, as well as the bubbles trapped in ancient ice layers to measure greenhouse gas concentrations. These samples provide a timeline that stretches back hundreds of thousands of years, revealing how temperature and atmospheric composition rose and fell in tandem with the advance and retreat of ice sheets. The data show repeated cycles of roughly 100,000 years, characterized by a gradual buildup of ice followed by a relatively rapid warming period. Superimposed on these glacial and interglacial cycles were shorter fluctuations that could happen over centuries or even decades, illustrating that the climate system can swing from one state to another more quickly than earlier scientists once assumed. The interplay of land, sea, and air also influenced migration routes for both animals and humans. During cold periods, sea levels could drop by as much as 120 meters or more, exposing land bridges like Beringia between Siberia and Alaska and Sahul between Australia and New Guinea. These bridges allowed species to cross into new continents. Conversely, as warmer temperatures returned and ice melted, rising seas submerged these connections. The distribution of flora also shifted as tree lines advanced or retreated in response to temperature and rainfall changes. In some places, steppe-like grasslands replaced forests, providing habitat for large grazing animals. In other areas, tundra spread, populated by hardy plants adapted to short-growing seasons. This dynamic patchwork of ecosystems was home to a wide range of megafauna, from the woolly mammoths of northern latitudes to the giant marsupials of Australia. Over the course of the Ice Age, repeated changes in sea level had major consequences for coastal environments. Large swaths of continental shelf were exposed, creating broad coastal plains where rivers ran further out to sea. Coastal caves and rock shelters that had once been far inland became beachside locations during glacial retreats and vice versa. Evidence from these areas often includes shells, fish remains, and other indicators of marine-based diets. Humans living in proximity to coastlines during interglacial periods likely found abundant resources, which could fuel population growth and cultural development. But as the next glacial cycle began and sea levels dropped again, these coastal areas might have turned into dry, inhospitable flats, prompting migrations inland. While much attention focuses on the northern hemisphere ice sheets, the southern hemisphere experienced its own distinct climate patterns. In South America, the Andes played a central role in glaciation. The Patagonian ice fields expanded, creating a cooler and wetter climate in their immediate vicinity, while regions further east became drier. Africa's climate also fluctuated, with deserts like the Sahara expanding or contracting depending on rainfall shifts. Parts of Africa served as refuges where biodiversity remained relatively stable through cold phases. The interplay of changing ocean currents in the Indian and Atlantic Oceans influenced rainfall along African coasts, shaping the distribution of savannas, forests, and deserts. In Australia, as mentioned, the reduced rainfall and lower sea levels tied that continent more closely to New Guinea, altering migrations and fostering unique ecological developments. One of the more intriguing aspects of Ice Age climate patterns is the abruptness of some changes. Scientists studying ice cores have identified events where temperatures rose sharply in just a few decades. These abrupt climate changes could have been triggered by large injections of fresh water into the North Atlantic from melting glaciers, altering ocean circulation. Volcanic eruptions or shifts in atmospheric dust levels might also have played roles. These sudden shifts forced rapid adaptations in both human and animal communities. Populations that were thriving in warmer conditions might have suddenly found themselves in cold, dry landscapes, leading to migrations and competition over diminishing resources. Conversely, warming events sometimes opened up new territories or made existing lands more habitable, allowing expansions and cultural flourishes in human groups. Ultimately, Ice Age climate patterns were a result of multiple overlapping cycles and feedback mechanisms, from the planetary tilt to ocean chemistry to the reflective properties of ice sheets. While scientists have developed sophisticated models to understand these dynamics, the complexity of the system means there are still ongoing debates about the precise triggers for major shifts and the extent to which different factors played dominant roles. Nonetheless, the broad outlines are clear. Variations in Earth's orbit set the stage. Greenhouse gas levels provided additional feedback, ocean currents distributed heat and influenced weather, and the arrangement of continents and mountains shaped local effects. This tapestry of climatic forces governed the environment for millions of years, creating challenges and opportunities for every living thing that called the planet home during these fluctuating eras of cold and warmth. As research continues, each new data source, whether from marine sediments, lake cores, or ancient pollen records, adds depth to the story of Ice Age climate patterns. Scientists can see how repeated cycles of expansion and contraction changed landscapes and forced species to adapt. These patterns also highlight the sensitivity of Earth's climate system to relatively small changes in factors like solar radiation and atmospheric composition. The repeated nature of glacial and interglacial periods underscores that Earth's climate has never been static. It has always oscillated, occasionally in dramatic ways. By understanding the forces behind these historical swings, researchers gain perspective on current climate dynamics. The lessons from the Ice Age confirm that significant changes can happen over centuries, decades, or even quicker, depending on the interplay of various natural drivers. That knowledge is valuable in discussing how the planet might respond to present-day changes, adding a geological perspective to the broader conversation about climate and the ways living things cope with whatever comes next. The end of the last Ice Age was a gradual process influenced by multiple factors that converge to warm Earth's climate and melt the expansive ice sheets. Scientists generally mark the conclusion of the Pleistocene glacial period around 12,000 years ago, moving into what is known as the Holocene epoch. This shift was not a single event, but rather a series of fluctuations in temperature that, over centuries, tipped the scales away from the colder conditions that had prevailed for tens of thousands of years. The primary drivers of this change included variations in Earth's orbital cycles, rising greenhouse gas concentrations, and shifts in ocean currents. Additionally, complex feedback loops sped up the warming once it began in earnest. Earth's orbit around the Sun does not remain constant through time. It changes shape, eccentricity. The tilt of its axis varies, obliquity, and the axis itself wobbles, precession. Collectively, these are called Milankovitch cycles. During the late stages of the last Ice Age, conditions aligned to bring increased solar radiation to the northern hemisphere in summer. With more sunlight hitting the northern latitudes, ice sheets began to melt at their edges. Initially, these changes might have seemed slight, but they set in motion a positive feedback loop. As ice receded, less sunlight was reflected back into space, and more heat was absorbed by darker land or ocean surfaces. This additional absorption of solar energy promoted further warming, leading to even more ice melt. Over thousands of years, the cumulative effect was quite large, fundamentally reshaping the planet's climate. Another major factor involved greenhouse gases, particularly carbon dioxide. As the oceans warmed, they could not hold as much dissolved carbon dioxide, which led to the gas being released into the atmosphere. This rise in atmospheric carbon dioxide intensified the greenhouse effect, trapping more heat near Earth's surface. Ice cores from Antarctica provide clear evidence of this sequence. Temperatures began to rise, and shortly afterward, carbon dioxide levels increased, amplifying the warming trend. Methane also played a role as wetlands expanded with warmer and wetter conditions, releasing more methane, another potent greenhouse gas. Together, these gases created a feedback cycle that supported further temperature increases. Melting ice sheets introduced large volumes of fresh water into the oceans, which affected global ocean circulation patterns. When freshwater floods regions like the North Atlantic, it can disrupt the conveyor belt of currents that typically transport warm water from equatorial zones northward. One example of a disruption was the Younger Dryas event, a period when global temperatures temporarily dipped after an initial warming. It is believed that the sudden influx of fresh water slowed the Atlantic meridional overturning circulation, halting the transport of heat to the north. This caused a rapid regional cooling in places like Greenland and parts of Europe. However, once this event ended and the currents resumed, warming continued and even intensified, leading to the final decline of the great ice sheets. Volcanic activity may also have played a role, although its exact contribution is debated. Large volcanic eruptions can inject ash and sulfur dioxide into the atmosphere, which can temporarily cool the planet by reflecting sunlight. However, long-term effects can differ. Some researchers suggest that increased volcanic eruptions during deglaciation may have influenced ocean chemistry and carbon dioxide release. On geological timescales, plate tectonics and volcanic activity alter the balance of carbon between Earth's interior and atmosphere, but these processes usually unfold more slowly than the rapid changes observed at the end of the last ice age. Still, even small variations in volcanic activity might have nudged climate in certain directions when combined with other factors. The retreat of ice sheets was not a uniform process. Some regions saw relatively swift melting, while others lingered under ice for centuries. For instance, the Laurentide ice sheet in North America was enormous and took thousands of years to vanish completely. Its retreat exposed new landscapes that were initially barren but eventually colonized by plants and animals. In Europe, the Scandinavian ice sheet followed a similar pattern, drawing back from the British Isles and northern Europe. As new ground emerged from under the glaciers, lakes formed in areas where meltwater was trapped. These proglacial lakes influenced local climates and provided stepping stones for flora and fauna to expand. Over time, forests advanced into territories once locked under ice, transforming open tundra into woodlands and altering habitats for countless species. Another factor that contributed to warming was the growth of plant life in newly ice-free regions. Vegetation has a significant impact on climate because plants absorb carbon dioxide during photosynthesis. As tundra transitioned into forests, darker tree cover replaced reflective snowfields, causing more solar absorption. Additionally, soils in newly forested areas stored carbon, creating intricate feedback loops with local and regional climates. Studies of ancient pollen preserved in sediment cores show how the composition of vegetation changed over thousands of years, indicating a gradual but decisive shift toward a warmer and more diverse environment. This expansion of plants reshaped entire ecosystems, paving the way for animal populations to move northward and repopulate the land once dominated by ice. glacial isostatic rebound also played a role in shaping the land during and after deglaciation. When ice sheets sat on top of continents, they pressed the land down under their massive weight. As the ice melted, the land gradually rebounded, sometimes rising hundreds of meters over thousands of years. This process altered coastlines, drained or filled certain areas with water, and influenced local climates by changing wind patterns and the distribution of land and sea. In places like Scandinavia, the rebound continues even today, raising shorelines at a slow but steady rate. Meanwhile, areas on the edges of the former ice sheets that were forced up are now slowly subsiding. These geological adjustments highlight how the planet continued to respond to the end of the Ice Age long after temperatures began to rise. The role of humans in ending the Ice Age was minimal on a global scale, despite local impacts on fauna and flora. Although early human communities hunted megafauna and may have changed landscapes through burning, their overall contribution to greenhouse gas levels at that time was small compared to the massive, planet-wide processes unfolding. Some scientists have proposed that the extinction of large herbivores in certain regions might have affected vegetation and carbon storage, but these local changes did not override the main drivers of deglaciation. Instead, humanity's bigger influence on global climate would come much later, during periods of agriculture and industrial activity that started only a few thousand years ago and accelerated in recent centuries. The final break from the Ice Age was accompanied by rising sea levels, which reshaped coastlines around the globe. Low-lying areas flooded, submerging land bridges such as Beringia, which had connected Siberia and Alaska, and Sahel, linking Australia to New Guinea. This isolation of land masses influenced the distribution of human populations, animals, and plants. Coastal communities that had thrived near the edge of the continental shelf were forced to move to higher ground. In some places, the relatively rapid rise of the seas sparked the creation of myths and legends about great floods. These stories, passed down through generations, hint at the transformative power of changing climate and rising waters on ancient cultures. As temperatures climbed, life flourished in many places. Forests spread across Eurasia and North America, offering habitats for deer, boar, and other woodland creatures. Human communities followed, adapting their hunting and gathering techniques to new environments rich in resources. Meanwhile, some large animals like woolly mammoths and saber-toothed cats struggled to survive as the open steppe tundra gave way to forests. While changes in climate played a key role in the decline of these megafauna, human hunting pressures and habitat transformation may have pushed them further toward extinction. The end of the Ice Age thus ushered in a new ecological balance, one that favored smaller, more flexible species and allowed human populations to expand across many parts of the globe. The warming trend was not entirely linear. Several abrupt climate events, like the Younger Dryas, created temporary setbacks. Still, the broader pattern was one of sustained warming. By around 8,000 years ago, the climate had stabilized into something relatively close to the conditions humanity has known for most of recorded history. This period of stability, often called the Holocene climatic optimum, supported the advent of agriculture in multiple regions, laying the groundwork for the first complex societies. As farming spread, human populations grew, intensifying their impact on local environments. But that influence remained comparatively small on a planetary scale until more recent eras. Understanding why the last Ice Age ended helps place modern climate questions in perspective. The planet is responsive to changes in sunlight distribution, greenhouse gas levels, and ocean circulation, and these changes can have global effects over timescales ranging from decades to millennia. The story of deglaciation illustrates how a shift in one part of the system, like increased summer sunlight in the northern hemisphere, can trigger a cascade of events that ultimately alter climate worldwide. This interconnectedness is a fundamental feature of Earth's climate system. Today, scientists combine data from ice cores, geological records, and climate models to form a comprehensive picture of what happened thousands of years ago and how it relates to the present. That knowledge informs discussions about current warming trends and how they fit into the broader tapestry of natural variability and human influence. In summary, the end of the last ice age was a multifaceted process set in motion by orbital shifts that increased solar energy reaching northern latitudes. This warming was then amplified by rising greenhouse gases released from oceans and wetlands, which further melted ice sheets. Large amounts of fresh water entering the oceans sometimes interrupted heat-transporting currents, causing short-lived reversals in the warming trend, but the overall trajectory remained upward. As ice retreated, vegetation and wildlife moved into new areas, and human communities followed, adapting to radically different environments. Over thousands of years, the planet emerged from the grip of extensive glacial conditions, setting the stage for the Holocene epoch with its more temperate and stable climate that enabled agriculture and the growth of civilizations. The story of how the last ice age ended is, at its core, a testament to the planet's capacity for change and the subtle but powerful forces that can tilt the balance between cold and warmth on a global scale. Ice Age landscapes are often associated with massive glaciers, bitterly cold temperatures, and animals that roamed a world covered in ice sheets and tundra. Although that ancient time has long passed, plenty of remnants remain in modern environments to remind everyone of those frigid epochs. Glacial valleys, carved with incredible force by sheets of ice, are found on different continents and stand as natural monuments to the power of slow-moving ice. Some regions exhibit deep U-shaped valleys instead of the more common V-shaped ones, and that shape is a sure sign that enormous glaciers once moved through, scraping and grinding the land beneath them. These valleys are often breathtaking to look at, with steep walls and wide bottoms that might now be covered in greenery or dotted with lakes. Their origins speak to a time when summer temperatures were lower and the ice never fully disappeared during any season. Over the centuries, water and erosion have changed these valleys, but that smooth U-shape remains recognizable to geologists and visitors who know what to look for. Fjords also serve as dramatic reminders of Ice Age processes. A fjord is a long, narrow inlet with steep sides that reaches far inland, typically created by a glacier that carved its way toward the ocean. When sea levels rose at the end of the Ice Age and glaciers retreated, these submerged valleys became inlets of salt water. Places like Norway, New Zealand, and parts of Canada are famous for their fjords that now host marine life and communities along their shores. Standing at the edge of a fjord can be awe-inspiring, knowing that giant rivers of ice carved out those deep cuts in the planet's crust. While the glaciers themselves may be gone or substantially reduced in size, the imprint they left behind is immense, and these bodies of water continue to support fisheries, tourism, and local cultures. Moraines are another common feature of Ice Age landscapes that still exist in many parts of the world. Moraines form when a glacier carries rocks and debris as it advances. When the ice melts, these materials get deposited in large mounds. Some moraines stretch across entire regions, forming ridges and small hills. Farmers in these areas sometimes unearth all sorts of stones and boulders that glaciers transported. In certain places, these rocks are oddly out of place, having been carried hundreds of miles from their original location. Geologists often trace these erratic boulders back to their bedrock origins and confirm they were moved by the tremendous power of glacial ice. These moraines have influenced agriculture, settlement patterns, and even road construction because of the hills and ridges they create. In some places, moraines form natural dams, allowing for the creation of lakes that can last for thousands of years after the ice has disappeared. Eskers are less well known than moraines or fjords, but are equally fascinating reminders of glacial times. An esker is a long, winding ridge of gravel and sand that was formed within a melting glacier. When water flowed in tunnels beneath the ice, it picked up sediment that was deposited as the glacier retreated. The result is a snake-like ridge that can curve through the landscape for miles. Eskers are so distinct that from an aerial view, they look like winding roads or natural embankments. They are often mined for sand and gravel in modern times, and there have been ongoing efforts in some regions to protect them as important geological features. These ridges can also serve as habitats for different plant and animal species, especially if they stand above the surrounding wetlands or valleys. Even the Great Lakes in North America are a testament to Ice Age power. Massive ice sheets once covered that area, and as they melted, they left behind depressions that filled with water. The basins had been deepened by glacial scouring, and once the climate warmed, meltwater flooded the region to create the lakes that exist today. People living around the Great Lakes may not think of them as direct results of Ice Age activity, but in fact, those large bodies of fresh water are essentially relics of that period. Their enormous surface area and depth, combined with the abundant resources, made the region an attractive place for human settlement, both in prehistoric and modern times. Over thousands of years, the shape and flow of these lakes have changed with water levels rising and falling, but their origins remain tied to the glaciers of the last Ice Age. Another striking example is the Finger Lakes region in what is now the northeastern part of the United States, where long, narrow lakes were formed when glaciers advanced and retreated across the terrain. These lakes get their name from their finger-like shape when viewed on a map. They illustrate how ice can carve deep channels in the bedrock, leaving behind narrow valleys that eventually filled with water. Today, the area is known for vineyards, agriculture, and tourism, but the long lakes are always there as a reminder of glaciers that once covered the land. Some of the steep hillsides around these lakes also show signs of past glacial erosion, with scattered boulders perched in unlikely places. In various parts of Europe, glacial landscapes can be found in alpine regions, most prominently in the Alps. The high peaks were heavily glaciated during the Ice Age, leaving behind cirques, which are amphitheater-like hollows on the mountainsides where glaciers once formed. These features often contain small lakes called tarns, where meltwater accumulated. Hikers who venture into the high alpine areas may notice these bowl-shaped depressions long after the glaciers that created them have vanished or significantly retreated. Cirques are generally very scenic, and some are now home to year-round snowfields or modern glaciers that are much smaller than their ancient predecessors. The legacy of the Ice Age also includes the presence of glacial erratics, which are large boulders carried far from their source by moving ice. An erratic might be found in the middle of a pasture or forest, sometimes seeming entirely out of place compared to the local bedrock. These giant rocks occasionally become landmarks or points of local curiosity. In some cultures, folklore sprang up around these erratics, with stories suggesting they were left behind by giants or spirits. Modern geology provides a more scientific explanation. Glaciers can transport enormous rocks for many miles and then leave them behind when the ice melts. In certain coastal areas, ancient shorelines reveal how sea levels have changed since the Ice Age. When large amounts of water were locked up in ice sheets, sea levels were much lower. In some parts of the world, raised beaches can still be spotted, sitting far above the current sea level. These features show where the shoreline once was, back when ice sheets dominated the poles and water remained trapped as ice. As the planet warmed, glaciers melted and the sea rose, submerging old coastlines and creating new ones. People who study these raised beaches can piece together patterns of glacial melting and how quickly the climate changed in different regions. Glaciated landscapes are also found in mountain ranges that still harbor glaciers, such as the Himalayas, the Andes, and parts of Alaska. Although modern glaciers are typically smaller than their Ice Age counterparts, they continue to shape the terrain, carving valleys and creating glacial lakes. These present-day ice masses are often studied to understand the climatic conditions of earlier times. The speed at which they are shrinking can also give insights into current climate trends. Observers who look at satellite imagery can still identify older glacial scars on mountainsides, indicating that some areas were once covered by thicker ice or had multiple glaciers merging into one another. Certain areas of the world, like Greenland and Antarctica, are essentially remnants of the Ice Age still in place. Though these massive ice sheets have existed for much longer than just the most recent Ice Age, they hold vital records of past climate locked in their layers of ice. When scientists drill ice cores, they can analyze trapped air bubbles and other indicators that show what the atmosphere was like tens of thousands of years ago. The sheer scale of these ice sheets reminds modern societies of a period when such ice coverage was more widespread across the globe. They also serve as critical gauges for how fast climate change might be happening in modern times, as the melting or growth of these ice sheets can shift global sea levels. Glacial outwash plains are another form of Ice Age legacy found in various parts of the world. As glaciers melt, they release large volumes of water that carry sediment. This sediment gets deposited and spread out, forming plains that can appear somewhat barren or feature a distinctive layering of sand and gravel. Such plains often have braided rivers and streams running through them, creating a dynamic environment that can shift rapidly over time. People who live near these plains might witness floods or changes in river channels, all tied to the natural process that began with the melting of ancient ice. Some desert areas also owe part of their current form to Ice Age conditions. While the image of the Ice Age might not typically include deserts, fluctuations in global climate led to shifts in precipitation and temperature patterns. During certain periods, regions that are now dry and arid may have received more rainfall, creating large lakes or lush grasslands. Over time, as the climate warmed and the Ice Age ended, these areas dried out. Ancient lake beds can often be found in the desert, with salt flats and sediment layers hinting at a wet past. These shifts dramatically changed local ecosystems, and fossil evidence can reveal the presence of species that now only exist in more temperate or tropical climates. Gorges and canyons in previously glaciated areas can also be traced back to the erosive power of post-Ice Age meltwater. As the ice sheets melted, floods of water rushed across landscapes, carving channels into rock in a relatively short geological time. These meltwater channels can be dramatic, with sheer walls and unique geological formations. Visitors might assume these gorges required millions of years to form, but in some cases, they were shaped much more rapidly by the tremendous outflows of glacial melt. Wetlands and peat bogs in northern regions are partly connected to the waterlogged conditions that followed retreating ice sheets. The ground in those areas sometimes remained saturated, creating ideal conditions for peat formation. Over thousands of years, plant material built up in waterlogged environments, forming thick layers of peat that preserve pollen, seeds, and even animal remains. By analyzing these layers, scientists can reconstruct how vegetation changed from the Ice Age to modern times. These wetlands are also home to unique ecosystems that evolved as the climate gradually became warmer. Loess plains are another interesting feature. Loess consists of fine silt and clay particles that were transported by wind and deposited in thick layers. During glacial periods, large expanses of land lacked vegetation and were subject to strong winds, which picked up dust and carried it over long distances. When these winds dropped their sediment, it accumulated into loess deposits. These deposits can form fertile soils, which are beneficial for agriculture. Some of the world's most productive farmland sits on loess plains that date back to the Ice Age. The Mississippi River Valley in the United States and parts of northern China are well known for their thick loess layers. Farmers in these regions benefit from the soil's fertility, even though erosion and other environmental concerns sometimes arise from this loose, wind-blown material. Mountains that experienced glaciation can show evidence of ancient periglacial features, such as patterned ground, rock glaciers, and frost-shattered peaks. Patterned ground might take the form of stones arranged in polygons or stripes, the result of repeated freezing and thawing. Rock glaciers occur when rocky debris is mixed with ice that slowly flows downhill, much like a true glacier, but with a different composition. These features exist in cooler mountain areas around the world, indicating that conditions were once cold enough for ice to shape the landscape more extensively. Some coastal landscapes feature glacial striations on exposed bedrock surfaces, where hard rocks embedded in the ice left grooves as the glacier slid over the land. Observers can run their hands along these grooves and imagine the powerful forces that created them. The direction and depth of the striations can offer clues about the glacier's path and speed. Geologists often use these markings to reconstruct ice flow patterns and estimate how thick glaciers might have been. Waterfalls can also be a legacy of glaciation. When glaciers reshape the land, they sometimes left behind ledges or cliffs over which rivers now plunge. Niagara Falls, for instance, sits in a region that was heavily influenced by glacial activity. Glacial erosion and the subsequent draining of meltwater helped establish the conditions for the falls to form. Even as the falls retreat upstream, they remain a living example of how the Ice Age shaped topography in ways that still evolve today. Tourism around Niagara Falls is in part an indirect celebration of those ancient processes. In summary, Ice Age landscapes that exist today are everywhere, from towering fjords to subtle hills of glacial debris. They are often striking to behold and serve as important clues that help geologists piece together Earth's climatic past. Many of these features continue to influence how and where people live, providing fresh water, fertile soil, and beautiful settings that attract visitors from far and wide. The Ice Age may seem distant, but its fingerprints remain etched into the land, reminding everyone that climate and geography are never static. Understanding how these landscapes formed can give perspective on the planet's history and perhaps shed light on how future climate shifts might reshape the world yet again. Life during the Ice Age is often imagined in terms of enormous mammals like woolly mammoths and saber-toothed cats. But plants and forests played a critical role in shaping the environment and supporting the diverse organisms that lived then. It might be easy to forget how vegetation responded to the cold climate, but plants are remarkably adaptable. Some regions were covered by thick ice sheets, making any kind of plant life impossible on that frozen terrain. Yet, in areas beyond the ice or along the edges, forests and grasslands managed to survive. Different species thrived in milder zones, while others adapted to frigid conditions with specialized traits that allowed them to withstand freezing temperatures and short growing seasons. Tundra vegetation was widespread across northern latitudes. This type of plant community is characterized by low shrubs, grasses, mosses, and lichens that can handle extremely cold environments. Tundra plants often have shallow root systems because the ground remains frozen most of the year, and they grow close to the ground to conserve heat. Some are covered in tiny hairs that trap warmth and protect against wind. Others produce small, waxy leaves to reduce water loss. During the Ice Age, tundra ecosystems stretched much farther south than they do today, providing grazing opportunities for large herbivores. Despite the harsh conditions, these plants formed the foundation of many food webs, supporting mammoths, reindeer, and other grazing animals that roamed the steppe tundra environment. In regions that were not covered by ice, boreal forests grew, dominated by coniferous trees like spruce, pine, and fir. These trees are well adapted to cold climates with their conical shape and needle-like leaves, which shed snow easily and resist freezing damage. The needles also have a thick, waxy coating that prevents moisture loss. During the Ice Age, boreal forests likely had a patchy distribution, with belts of coniferous trees in areas that received enough warmth and precipitation. This forest type would have supported a variety of fauna, from small mammals that fed on seeds to larger predators that hunted those mammals. The forest floor would have been covered by thick layers of decaying needles, mosses, and lichens, creating a soft, somewhat acidic soil environment. In some lower latitude regions or locations with milder microclimates, deciduous trees such as birch, poplar, and willow could persist. These species can drop their leaves in winter to reduce water loss and protect themselves from the cold. Even during the height of the Ice Age, valleys or certain sheltered areas might have hosted pockets of deciduous forest, offering habitat for animals that depended on a mix of resources. Over time, as the climate warmed, these stands of deciduous trees could expand northward or upward in elevation, replacing conifers that once dominated. Scientists track these shifts through pollen records extracted from lake sediments and peat bogs, which can reveal which tree species were present in a given location thousands of years ago. Grasslands also played a significant role during the Ice Age. Some expansive regions were covered by grass-dominated ecosystems, sometimes referred to as the mammoth steppe. This biome stretched across parts of Europe, Asia, and North America, and it supported large herds of herbivores such as woolly mammoths, horses, and bison. These grasses and small flowering plants were hardy and could survive cold, dry conditions, often helped by permafrost that stabilized the soil. When snow melted in the short summer, the grasses flourished, providing abundant food for grazing animals. The mammoth steppe is considered one of the largest biomes of its time, and it has fascinated researchers for decades because of its ability to support so many large mammals. Seeds, spores, and pollen from the Ice Age have been found preserved in sediments and permafrost, allowing researchers to reconstruct plant communities in remarkable detail. Even the remains of entire plants can be discovered, frozen and mummified in the cold ground. These preserved specimens sometimes appear as though they were just dropped there, offering an incredible opportunity to study ancient genetics and morphology. By analyzing these remains, scientists learn about the resilience of certain species, how ecosystems might respond to climate change, and how plant-animal interactions shape the environment. Forests in mountainous regions also shifted during the Ice Age, with tree lines descending to lower elevations. Alpine zones that are now bare rock or short grass might have been home to trees that could tolerate a colder climate. As glaciers retreated, these tree lines began to move upslope, slowly reclaiming space that was once under ice. The pace of this migration depended on climate stability, seed dispersal, and soil development. Some mountain valleys remained ice-free and served as refuges for plant and animal species, allowing them to survive even during the coldest intervals. These refuges became genetic reservoirs, where distinct populations evolved and then spread out again when conditions improved. During warmer interglacial periods, forests expanded significantly, sometimes reaching latitudes far north of where they thrive today. These expansions were often rapid in geological terms, as trees took advantage of newly thawed land and favorable growing conditions. Every time the climate cooled again and glaciation returned, plant populations had to retreat south or to lower elevations. These repeated expansions and contractions influenced the evolution and distribution of many species. Some plants that were able to adapt quickly or disperse their seeds effectively had a better chance of surviving. Others went extinct or were pushed into very limited areas where they might still exist as relict populations. Fire also played a role in shaping Ice Age forests and grasslands. While the climate was generally colder, periods of dryness and the presence of dead vegetation could still lead to natural wildfires. These fires helped clear old growth, returning nutrients to the soil and making way for new plants. This process would have influenced the composition of forests, sometimes favoring species that are fire-adapted or that grow quickly in open areas. In some grassland regions, fire was part of a natural cycle that kept woody vegetation from taking over. Large herbivores also played a part by trampling and grazing, which helped maintain open grasslands in places that might otherwise develop into shrubland or forest. Human activity began to influence these plant communities as people spread across the globe. Even before the end of the last Ice Age, humans were using fire and clearing land for various purposes. Although large-scale agriculture would come later, Early foragers might have modified the growth patterns of certain plants by selectively harvesting or burning areas to encourage the growth of edible species. Over time, human impact became more pronounced, especially as the climate warmed and people established more permanent settlements. Nonetheless, plants during the Ice Age had already proven themselves to be capable of surviving dramatic shifts in climate and environment. One surprising aspect of Ice Age plant life is how quickly some species recolonized areas that had been under ice. Once the glaciers melted and soils developed, pioneer species such as mosses and lichens were often the first to appear. These organisms can survive on bare rock, gradually forming pockets of soil and preparing the way for larger plants. Next came hardy grasses and shrubs, followed by coniferous trees, and eventually, in some places, more diverse forest ecosystems. Within a few thousand years, entire landscapes could transform from barren, glacially scoured rock to flourishing forests, a testament to the resilience of plant life. Pollen analysis, also known as palynology, has been a game-changer in understanding Ice Age vegetation. Lakes and bogs accumulate layers of sediment over time, and these sediments trap pollen grains that drift in from the surrounding vegetation. By extracting cores from these sediments and identifying the pollen types within each layer, researchers can chart how forests expanded and contracted, how grasslands took over, and when certain species appeared or vanished. This method provides a timeline of plant community changes that can be correlated with climate data from ice cores and other sources. If pollen data shows a sudden spike in spruce, for example, it may indicate a shift to cooler and wetter conditions favorable to that tree. There were times when the climate saw rapid swings, such as during the Younger Dryas, a period of sudden cooling that happened roughly 12,000 years ago. Plant communities responded accordingly, sometimes showing abrupt changes in pollen records that reflect a quick return to tundra or boreal conditions. When the climate stabilized again, vegetation re-expanded or shifted once more. These fluctuations highlight how sensitive plant communities can be to temperature and moisture levels. They also show that adaptation and migration were ongoing processes for Ice Age flora. In some cases, plant species that thrived during the Ice Age have become rarer in the modern world, found only in specific niches that mimic ancient conditions. Alpine or Arctic plants might survive on high peaks far to the south of their main range, protected by cool microclimates. Relict populations of certain trees can be found in sheltered canyons or north-facing slopes that offered refuge when the world warmed. These outliers are living reminders of how drastically the climate has shifted and how plants have fought to persist. Many people might not immediately connect modern temperate forests with the Ice Age, but there is a lineage that stretches back to those glacial times. Some species survived in refuges and then repopulated large areas, while others arrived from entirely different places as conditions changed. The complexity of these migration pathways can be seen in genetic studies that reveal relationships between populations separated by thousands of miles. The resilience of plants and their ability to move across landscapes over millennia is a story still being uncovered by researchers. Forests also stored carbon during the Ice Age, just as they do today. Although there was less total biomass on Earth during the coldest intervals, what vegetation did exist played an essential role in carbon cycling. The expansion of forests during warmer periods would have increased carbon storage on land, while the contraction of forests during colder times would have reduced that storage but increased peat formation in some wet, cold areas. Understanding these past carbon cycles can help scientists predict how current forests might respond to ongoing climate change, as the principles of growth, dieback, and redistribution of species still apply. Today's diversity of plant life is, in many ways, shaped by the Ice Age. The distributions of trees, shrubs, and even crops can be traced back to glacial refuges and post-glacial expansions. Agriculture itself might have been influenced by the changing conditions as the Ice Age ended and the climate stabilized in many regions. making it easier for humans to experiment with planting and harvesting. The domestication of wild plants likely happened in areas where conditions were favorable enough to support stable communities, which in turn led to the rise of civilizations. Ice Age plants and forests stand as a testament to life's tenacity. Even when confronted with continent-wide ice sheets and colder global temperatures, vegetation found ways to persist, shift location, or evolve. The interplay between cold-adapted tundra species, hardy conifers, resilient deciduous trees, and vast grasslands gave rise to a range of ecosystems that supported the large mammals people often associate with that era. In essence, these plants were just as crucial as the megafauna, providing sustenance, shelter, and a framework for complex food webs. Without them, the Ice Age world would have been barren indeed, and the journey of life through those challenging times might have taken a very different path. Permafrost is ground that remains at or below the freezing point of water for at least 2 consecutive years. It is commonly found in high latitudes, such as parts of Siberia, Alaska, Canada, and Greenland, as well as in high mountain regions. During the Ice Age, permafrost was much more extensive, covering larger swaths of land. That legacy continues to shape ecosystems, landscapes, and even archaeology in the modern day. One of the most striking aspects of permafrost is its ability to preserve organic matter in a near-frozen state for thousands of years. This preservation has allowed for incredible discoveries, offering a glimpse into ancient environments, extinct species, and past human activities. Scientists studying permafrost often extract cores to learn about climate history. By analyzing the layers of soil, ice, and sediment in these cores, they can piece together records of temperature changes, atmospheric composition, and vegetation dating back tens of thousands of years. This information complements data gathered from ice cores drilled in places like Greenland and Antarctica, helping researchers form a more complete picture of the planet's climatic fluctuations. One particularly fascinating aspect is how permafrost traps ancient air pockets and biological materials like pollen or insects, making it possible to reconstruct entire ecosystems that once thrived under very different conditions. These reconstructions can explain how certain species managed to survive the Ice Age, or why some eventually went extinct. In recent years, melting permafrost has brought to light astonishingly well-preserved remains of animals such as woolly mammoths, woolly rhinoceroses, cave lions, and even Ice Age puppies. When these creatures died thousands of years ago, they became buried in sediment that froze soon after. Because the ground remained frozen year-round, their bodies were spared from the usual processes of decay. When excavated, some still have fur, skin, and internal organs intact, providing researchers with invaluable opportunities to study Ice Age fauna up close. The discovery of these remains can shed light on the animal's diet, diseases, and genetics. In some instances, there has even been talk of using these genetic materials to explore de-extinction possibilities, though that remains speculative and ethically complex. Permafrost is also significant for human history. Archaeological sites in frozen ground can preserve artifacts made of organic materials like wood, bone, or leather that would normally decompose over time. In cold climates, these artifacts might remain in near-pristine condition, offering insights into the daily lives, tools, and cultural practices of ancient peoples. Some of the oldest traces of human habitation in the Arctic regions come from permafrost sites, where even subtle remains, such as plant fibers or fragments of animal hide, have endured for millennia. Researchers can examine these items to learn about the diets, clothing, and hunting strategies of Ice Age communities. The melting of permafrost sometimes reveals new sites that were previously hidden under frozen ground, sparking both excitement and concern among scientists, as rapid thaw can damage or destroy valuable evidence before it can be properly studied. Another intriguing angle is the study of ancient microbes locked in the permafrost. Some bacteria and viruses have been found dormant for tens of thousands of years, only to show signs of life when thawed in the lab. This raises fascinating questions about the limits of life on Earth and how organisms can survive in extreme conditions. At the same time, it prompts worries about the potential risks of pathogens being released if permafrost continues to melt. While such scenarios are still not well understood, they highlight the interconnectedness of climate change, microbial life, and global health. Researchers continue to investigate permafrost cores to understand which microorganisms might be lurking beneath the surface and whether they pose any threat to modern ecosystems. The physical presence of permafrost affects the landscape in profound ways. In some regions, melting permafrost causes the ground to slump or sink, creating thermokarst landscapes that can transform forests into swamps or lakes almost overnight. Large areas of land might develop sinkholes, and roads or buildings constructed on permafrost can buckle as the once solid ground thaws. For communities living in the Arctic, this presents major challenges, as infrastructure needs to be designed or adapted to cope with shifting soils. Historically, people in these regions understood the nature of frozen ground and built homes on stilts or used construction techniques that reduced heat transfer to the soil. In modern times, more comprehensive engineering solutions are necessary, but they become complicated when the rate of thaw is accelerating due to rising temperatures. Certain distinctive landforms, such as pingos, are also associated with permafrost. A pingo is a mound of earth-covered ice which grows as groundwater is pushed upward and freezes. Some pingos can reach considerable heights, and they serve as visible markers of permafrost conditions below the surface. If the ice core in a pingo melts, the mound may collapse, leaving a circular depression. These features, alongside patterned ground formations, are part of the unique visual language of periglacial landscapes. They reveal how water, soil, and ice interact over time, creating shapes that can shift and evolve with changes in temperature. The thawing of permafrost has implications for climate change too. Large amounts of organic material are locked in frozen soil, including plant debris accumulated over millennia. As the soil warms, microbes break down this material, releasing carbon dioxide and methane, both potent greenhouse gases. This creates a feedback loop. Warming accelerates permafrost thaw, which in turn releases more greenhouse gases, leading to further warming. Scientists are trying to quantify how much carbon could be released from permafrost over the coming decades to better predict future climate scenarios. The scale of this potential release is significant, as permafrost regions hold enormous stores of carbon, rivaling the amount currently in the atmosphere. Understanding this process is crucial for accurate climate modeling and for developing strategies to mitigate greenhouse gas emissions. Some researchers see the possibility of protecting or even refreezing certain permafrost areas by restoring ecosystems that favor cold-adapted herbivores. The concept, often referred to as Pleistocene Park in a real-world experimental effort in Siberia, involves reintroducing large grazers like bison, musk oxen, and even horses. The idea is that these animals keep the ground cooler by trampling the snow, making it less insulating and allowing more heat to escape into the atmosphere. This might sound counterintuitive, but a thin snow cover can lead to cooler soils. Though the concept is still under investigation and remains controversial, it hints at creative approaches to dealing with permafrost thaw. From a cultural standpoint, permafrost holds significance for indigenous communities in the far north. For centuries, it has influenced traditional practices like food storage, as underground permafrost cellars provided natural refrigeration. Hunters and fishers often rely on stable ice in rivers and lakes for travel, but melting permafrost can alter water flow and patterns, affecting fish populations and migration routes. The ground itself can sometimes reveal ancient burial sites or sacred locations that were frozen in time. As the landscape changes, these communities face the challenge of adapting centuries-old knowledge to rapidly shifting conditions. Frozen discoveries in permafrost also extend to natural treasures beyond ancient animals. Plant seeds preserved for thousands of years have been successfully germinated by scientists in laboratory settings. In one famous example, seeds from an Ice Age campion plant were retrieved from squirrel burrows in Siberia and were coaxed back to life, producing flowers that had not bloomed for over 30,000 years. These breakthroughs have profound implications for understanding seed longevity and the potential for preserving genetic material. They also offer a sobering reflection on the fragility of Earth's biodiversity and the remarkable endurance of life in extreme conditions. In the world of paleontology and anthropology, every new find in the permafrost can rewrite the textbooks. A single well-preserved mammoth or an extinct steppe bison can yield data on muscle tissue, stomach contents, and parasites that would be impossible to obtain from fossilized bone alone. For humans, permafrost can reveal details about clothing fibers, footprints in soft ground that later froze, and even entire structures built by ancient peoples. These clues can clarify migration routes, interactions with megafauna, and adaptations to harsh climates. The pace of these discoveries has increased in recent years as permafrost continues to thaw, adding urgency to efforts to document and preserve whatever appears before it degrades or disappears. On top of that, the study of permafrost is integral to fields like space exploration. Researchers look at permafrost environments as analogues for conditions that may exist on Mars or other celestial bodies. Understanding how microbes survive in frozen soil on Earth can shed light on the possibility of life in similar conditions elsewhere. Permafrost terrain also poses challenges reminiscent of extraterrestrial environments, such as how to drill cores or design habitats on unstable, icy ground. Insights from the Arctic, Antarctic, and high-altitude permafrost areas can guide future missions aimed at searching for life or establishing research stations on other planets. Despite the wealth of knowledge and intrigue it offers, permafrost is under threat from a rapidly changing climate. The rate of thaw has accelerated in many regions, causing a host of environmental and infrastructural issues. Scientists and policymakers are collaborating to assess risks, monitor changes, and develop adaptation strategies. These include altering building codes, creating better drainage systems, and considering new approaches to land management that might slow or mitigate the loss of permafrost. Even though some thaw is now unavoidable due to current warming trends, understanding the scope of the changes can help communities brace themselves for the future. Permafrost and frozen discoveries illustrate a unique intersection of geology, biology, and history. The ground under one's feet in these cold regions is not just soil and rock. It is a time capsule holding stories from thousands of years ago. Whether it is the body of a woolly mammoth, an ancient microbe, or the remains of a human settlement, the frozen soil reveals something about the resilience of life and the shifting climates that have shaped it. As temperatures rise and the ice retreats, there is a sense that a window into that ancient world is gradually closing. Yet for as long as it remains, permafrost continues to yield discoveries that transform the understanding of Earth's past and present, reminding everyone how delicate the balance can be when dealing with ancient ice and the secrets it holds.